Hello everyone, welcome to Scalar's YouTube channel. In today's session, we're going to look into data structures and algorithms. Before moving on and understanding the topics that will be covered in this particular session, please make sure to subscribe to Scalar's YouTube channel so that you don't miss our upcoming videos. And also, if you want to learn technologies and frameworks from industry experts, we conduct free masterclasses on Scalar events page, and that link is in the description below. Now, let's understand the topics that will be covered in this session. To start off with, we'll be looking into how to solve a DSA problem. That is, how to approach a problem and how to solve it step by step. Once that is completed, we'll start off with the data structures and algorithms concept. First, we'll start with algorithms. We'll be looking into sorting algorithms. In sorting, there is bubble sort, selection sort, there is quick sort, there is also merge sort, and so on. We'll be looking into all of those concepts. And after that, we'll move on to data structures. We'll be looking into stacks, we'll be looking into linked lists, and finally, we'll be looking into hashing. And the last part of this particular session would be dynamic programming. So these are the things we'll be covering in this particular session. Now let's start off with the first topic, that is how to solve a DSA problem.
Tip 1. Don't panic. Make sure you stay hydrated while solving the problem. Tip 2. Read the question carefully. If you feel comfortable after reading the question, your chances to solve the problem increases tremendously. You and your friend Mac love the DSA class, which is n minutes long, and the professor shares AI concepts during the ith minute. Mac is really interested in class but can't keep awake for the entire duration. Okay, so we will be having an array A which will be of the size n, and each of the element in the array will store an integer which says the number of concepts taught by the professor during that minute. Great. Array T is a binary array. Okay, so it's going to store only zeros and ones, where 0 means Mac is sleeping at that time. Okay, so this is also going to be of size n, and T is equal to 1 means Mac is awake. When Mac is awake, he writes all the concepts but none while sleeping. Okay. You, being a good friend of Mac, know a ninja technique to keep Mac awake for k straight minutes of the lecture, but it can be used only once. Okay. You can start using it from any minute beginning from I to n minus k plus 1. Okay. So this means that I need to use all the k minutes to keep Mac awake. I can't use less than k minutes. Your goal is to find out the maximum number of concepts Mac can write during the lecture, because you are ultimately going to use these notes for exam preparation. This is definitely true. I always use my friend's notes. Based on the understanding of the problem, make sure that you prepare some test cases so that you can dry run your approach on before jumping onto the code. Let's write the requirements first. A is the array input, concepts, size is n, T is 0 or 1, whether he is sleeping or awake. This is also of size n. Now we will be given n as the input, k is going to be the number of consecutive minutes I can help Mac stay awake. We are going to get A and then T. Okay, so test cases. Let's prepare some test cases. Okay, how should we get started? Let's create two random arrays. First example can always be a random one. 3, 2, 7, 6, 5 and 8. So here n is equal to 6, k can be 3. For t, let's keep it random this time. We will prepare some more test cases. So what will be the answer for this particular test case? We need to select k consecutive minutes which I can help Mac stay awake. So it can be this k, this k, this k and this k. For each one of them, my answer is going to be 12. Okay, so one thing I can observe here is that we will definitely be taking all the ones, because since Mac is awake at that time, we will be selecting this in our answer always. So the sum will start from 16. On top of that, our options are 10 for this k consecutive, or it can be 7 for the next k consecutive, or it can be 12, or it can be 5. So obviously the maximum one among this is 12. So the answer is going to be 16 plus 12, 28. Let's again have a look which k consecutive we are taking. We are going to take this. Mac is awake. I will wake him up here. He is still awake. I'll wake him up here and he is still awake. So these 3 minutes I will help Mac stay awake so that I can maximize the number of minutes he is awake and he writes the maximum number of concepts. So if you just calculate 2, 7, 9, 20, 28. Okay, 28 is the right answer. So I think my understanding of the problem is pretty clear at the moment. Let's prepare some more test cases. We'll start with the previous one. 3, 2, 7, 6, 5, 8. 6, 5, 8. 0, was it 0 first or 1 first? Okay, 0, 1, 0, 1, 0, 1. Another test case which we can think of. 1, 2, 3, 4, 5, and all of them are ones. Another test case can be 4, 3, 2, 1. All of them are zeros. And I think these examples should be sufficient for us to get started. We can dry run our approach once we have decided what algorithm we are going to use, and we can think about other edge cases further down the lane if need arises.
Tip 4. Take some observations from the problem. Based on the patterns that you have observed, choose a core data structure and algorithm. Find out if there are multiple solutions possible and make a trade-off based on time and space complexity and choose the one which is the most optimal one.
So here one observation I can make is that we are always going to choose the elements where Mac was awake. So we are definitely going to choose 2, 6 and 8. Now the entire deal is what values I pick among the remaining ones. So I'm left with 3, 7 and 5, and I obviously can choose only the k consecutive ones. So based on the patterns that I have observed solving a lot of other questions, if there are k consecutive elements, we want to choose the maximum among them. It's kind of a maximum sub-array problem, and I can use a sliding window approach. I can use a doubly ended queue perhaps, where I can start with the first k elements. Let's show how the doubly ended queue will look like. So this is a doubly ended queue. Let's start with the first k elements, and here note the first k elements are definitely not 3, 7 and 5 because there is a empty space in between. So what we can do is we can replace all the values when Mac was awake with 0 because we have already considered those values in our sum. So after we have considered 2, 6 and 8, we know our sum is definitely going to be greater than or equal to 16 in this case. So we can replace all of those values with 0. Now this is our new updated array, and what we can do is we can just iterate over it and choose the maximum sub array of size k. Amazing. I think I am able to understand the core algorithm which we can use. It's something in the lines of sliding window. So let's start with the k elements. Okay, so rightmost side is the front of the doubly ended queue and the leftmost one is the back of the doubly ended queue. Now we will keep a sum of the elements inside the queue as well. So at the moment the sum is 10.
Now we will remove 3 from the queue because like we are shifting the sliding window by one element, and after that it is 0. Okay, let me change the color. Okay. Now the sum of the remaining elements is 7, which is not greater than 10, so we will not update the maximum value. Now we can remove the element in the front as well. Adding the new element, it's 5 onto the back of the queue. Now the sum is 12. This is greater than 10, so I think I should be updating the maximum value of the k sub array from 10 to 12. Now I can remove 7 as well and add the last element, which is 0 in this case. This is the last element. We are not going to process it further because the question clearly mentioned it was from 1 to n minus k plus 1. If we consider the question, here it was mentioned that we can start our k consecutive minutes only from 1 to n minus k plus 1. Now the answer of the remaining k elements is 5, which is less than 12, so we'll not update the maximum answer, and hence our solution will be 12 plus 16, which is going to be 28. So we got the solution, and I think this should work for the remaining examples as well, because here if you see all of them have the value 1. So we will do the sum of all of these values, and this is going to be 15. And now when we update all of these values to 0, obviously the maximum k sub array for the remaining elements is going to be 0 because all the values are 0, and hence our answer is going to be 15 for this. Let's note the answers down as well. And for the last one, there are no minutes when Mac is awake. So we are not going to update the array. It's going to remain 4, 3, 2 and 1. And if I do the sliding k window approach, my options are 4, 3, 2 and 3, 2, 1 only. And definitely the answer, the greatest answer is going to be 9. So my solution for this is going to be 9. So I think my algorithm will work, but there is just one little issue. The space complexity for the sliding window with a doubly ended queue is O of k. Let's note the space complexity as well. It's O of k because the size of the doubly ended queue is going to like have k elements at any moment. The time complexity on the other hand is order of n because we are processing through all the elements one by one in the array. So it's not going to exceed more than n. How can we optimize it further? Are there any other potential solutions? How can we implement sliding window apart from a doubly ended queue? I think we can keep a track of these elements using a 2-pointer. Don't you think so? Like my first pointer and the second pointer will be at the 0th index, and then we will move the end pointer 3 values away. So this is going to be my pointers, and the sum between both the start pointer and the end pointer is going to be 15, and then we will iteratively move the pointer. We will move both the pointers one step to the right. Okay, I think we can eliminate the space complexity by this. We are still using 2 pointers, so it's order of 2, which is a constant order. So the solution will work, but how do we deal? Okay, we can again update the array values. We can use this array itself on the 2-pointer approach as well. So yeah, I guess we can eliminate the doubly ended queue, and this solution can be improved from O of k to O of 1. It's actually O of 2, but since constant order is obviously written as O of 1, we will keep it order of 1. Time complexity, again, like if you have a look, both the front pointer and the end pointer, both of them are going to move n values. None of them are repeating the elements. So both of them will move n times. So it's like order of 2 times n, but since 2 is again a constant, it's going to be order n. So this is not going to change. The time complexity is going to remain the same. Now, obviously, I don't think we can optimize it further. But looking at the k consecutive elements, there is one more solution which comes to my mind, and I think it would be good to discuss it at least, even though it might not be the most optimal one. So let me again write the example 327658. Okay. So one thing I observed is we are trying to find k maximum subarray, and one of the solutions which I have seen for such kind of questions, it's based on prefix sum. So what actually does the prefix sum mean? Prefix sum means that if my prefix sum of I, this means sum of all the elements till I minus 1 or I. It depends on the nomenclature, whatever you are following. We don't really mind like if you include the ith index in this sum or not. We usually keep I minus till I minus 1, so it's all right. Sum of all elements till I minus 1, we can keep it I as well. I have absolutely no issues with that. So if I am going to create a prefix sum array out of this, I am also going to show how we are going to find the maximum k sub array using this. So if I am going to translate this array, so what's going to be prefix sum of 0? It's going to be sum of all elements till 0 minus 1, which is minus 1. We don't have any element, so it's going to be 0. Okay, P of I is going to be sum of all elements till the 0th index, so it's 3, and let's keep on adding the elements. 5 plus 7 is 12, 12 plus 6 is 18, 18, 23, and 31. Well, let me just create some delimiters so that we don't get confused what the number is. Now, for example, if I want to find the sum of k consecutive elements, it's going to be, for example, if I want the sum of the first 3 elements, okay, 3 plus 2 plus 7, it's 12. So what I will do is, this is the 0th index, 1st index, 2nd index, 3rd index, 4th, 5th, and 6th. So what I will do is, for first 3 elements, I will compute P of 3 minus P of 0. For the next 3 elements, is going to be P of 4 minus P of 1, and so on. So if you see P of 3 minus 0, it's 12 minus 0, which is 12, hence it's correct. For 2, 7, and 6, it's 15. So if you take a look, P of 4 minus P of 1, 18 minus 3 is 15. So this logic will work as well. But one issue over here, and I definitely said that this is not going to be the most optimal one, but it's that the space complexity again is O of n. And why it's O of n? It's because we are going to use a prefix sum array in this, which is going to store n plus 1 elements. So it's actually going to be n plus 1, which will be order of n only. And time complexity, if we take a look, to prepare a prefix sum, it's going to be n times we are going to iterate through the array once, and we are again going to iterate through the prefix sum array to calculate the maximum k sub array. So it's going to be order of 2 times n, which is going to be again order of n. So this is not a optimal solution over the 2-pointer solution, but definitely we considered some other variant as well. Now, going through all the solutions, I think we should proceed with the 2-pointer solution one and jump onto coding, because we have definitely done the dry run on some of the examples as well for the 2-pointer one. So perhaps we can start the coding part of this.
Tip 5. Once you have decided your core data structure and algorithm, organize your thoughts around it, marinate them if required, and prepare a proper design approach for the solution.
Now what we decided was a 2-pointer solution. That is going to be our core algorithm. We are not using any data structure, we are just using 2 integers I and j to be the 2 pointers. So we don't need to actually worry about the data structure. Now if I again take a look at the example, just to prepare the design approach, 327658. 327658, and it was 0, 1, 0, 1, 0, and 1. Okay, so now one problem that I observed with the 2 pointers as well is that we were actually updating the original array. what we were doing was we were updating this array to look something like this, on which we were performing that algorithm. We were updating the values where Mac was awake to be 0. Now, what if there is a requirement in which you cannot update the array? Okay, it is very much possible that we cannot update this array because the array is immutable. So let us think if we can use the two-pointer solution to mitigate this issue or not. So think about the solution. In the beginning, our I pointer and j pointer is at I is at the 0th index basically. So what we'll do is initially okay, I'm not writing a code, this is just a pseudo code, okay. So initially I and j are at 0. For the first part, what we will do is we will move j to k positions further. We will move j incrementally k times and add each of these values. Whatever position our jth pointer is at, we are going to add that value, and whenever we move out of the ith pointer, we are going to subtract that value. Let me show what I actually mean. So let me again write the example with more space. Now I and j are both at the 0th position. So the sum will have 3 because j is at the 0th index, so we are going to have that. Sum is equal to 3. Now as we move the pointer ahead, we are going to remove j and move it ahead to the first index. Since we moved the pointer from 3 to 2, we moved the j pointer, we are going to add that value to sum. We are going to do this 3 times. Okay, j is at the 0th index, so we actually need to do it k minus 1 times. That was a mistake. So we move the jth pointer to 7. Now since we moved j to 7, we are going to perform this addition as well. And initially our sum is going to look like it's 12. Okay, so now this is the initial state from where we will begin. All right. So what we will do is we will now incrementally move both the pointers I and j further. We will move I to the first index and j to the 4th index. Let me note down the indices on top of this as well. And we have 0, 1. Okay, let me write this as well. This is when Mac is awake and sleeping. So let me just create a boundary so that, cool. So we will move j to the 3rd index. Now note over here that in the 3rd index, Mac was already awake. Okay, so what we can do is instead of adding 6, okay, we can perhaps rewind onto the solution. Let's take a look back. Let's remove this. I just realized we can get rid of updating the values. Okay, our I and j pointer. We can start with them at -1th index. So now when we move the jth pointer, the initial state is going to have values, all the values when Mac was awake. So initially it's going to be 16 like the previous time, but we are not going to update the value this time. Whenever j moves forward, we will have a look at whether Mac was awake or not. If Mac was sleeping, we are going to add that value. But if Mac was already awake, then we are not going to add that value because that we have already considered in 16. Okay, so when we move j from -1 to 0, we are going to do this k times now because we have updated our initial indices. We will start from -1. We will start from -1 instead of 0. So when we move j k times, we will move 3, 2 and 7. But we are not going to add the solution where 2 is also there because 2 is already considered in 16. So when I is over -1 and j is at the index 2, we will add 3 to it and 7 to it, and ultimately our answer is going to be 26 for the first 3 indices. Now what we'll do is, this is the initial state. Now we need to incrementally move both I and j. For the first part we just moved j k times ahead. Now we will move both I and j one time each, and we will remove the value where I previously was and add the value where j is going to. Okay, so when j moves from second index to the third index, we see, okay, at the third index Mac was already awake, so we are not going to add 6 to it because that was already considered in 16, right? So we will move I ahead as well. I was initially at -1th position where there is no value present, so we don't need to subtract anything from it. We will just move I ahead without doing anything else. Now if we move one step further, we are going to 5, okay, and we are removing I from the 0th index and pushing it to the first index. So we will actually subtract 3 over here because Mac was sleeping at that time. So we will subtract 3 from 26, we are going to subtract 3, and we are also moving j one step ahead, moving it to the 4th index, and here Mac was sleeping, so we will again add it, and here the answer will be updated to 28. Now this is greater than 26, so our updated solution will be 28. In this way you can move I and j one step ahead again and find out if it creates a better solution or not. It will not, because I and j are currently at, like when we move j to the 5th index, Mac is already awake, so we don't need to add 8. When we move I from the first index to second index, we don't need to update that as well because 2 was already considered. 2 is already considered in our initial sum. It was already counted, so we don't need to remove that as well. So a note to make is, whenever we move I and j, when we move I, we subtract the old value. When we move j, we add the new value. So the important thing here is, if Mac was not awake, we are going to add and subtract those values. If Mac was already awake, we are not going to do anything at all. So this is going to be our design approach, where we are not updating the array as well, we are not utilizing O of n space as well, and we are having a decent, I think it's the most optimal solution that comes to my mind at the moment. So with this approach, I have dry run my solution on. I am very confident with this approach. And tip number 6 is that once you have performed your dry run on the test cases that you had created, if you feel confident after that, you can move on to the coding part. So let's move to the coding part. Whew, we finally completed the coding part. Tip number 7. Once you have finished your coding, make sure that you do a dry run on the code as well, because sometimes it happens that there is some gap between the solution that you thought before and the code that you have implemented. So let's do a quick dry run to see if there are any mistakes or not. Upon doing the dry run, I identified 2 mistakes, and there are a few important edge cases that we should be considering. What if the value of n is 0? If the value of n is 0, then we will not be storing anything in either of the vectors. We will not be updating anything to the sum as well. But what if the value of k is not 0? Then we should be checking the minimum of n and k, and then make a decision based upon that in this for loop. Otherwise, we'll try to iterate through k elements. K can be greater than n as well, and if we try to access t of k, it would not exist and it would throw a segmentation fault. So this was one mistake which I found out by adding a new test case, which was an edge case, like k was greater than n. Another mistake which I found out while doing my dry run was in this line. We are trying to update the value of sum if t of k is equal to 0. Now what I missed out was that we were supposed to increment the value of k before we actually did that computation. So we have to increment the value of k before this statement and then check if t of k is equal to 0, which means Mac was sleeping, then we should update our sum. Now for the j, if t of j is equal to 0 and j is greater than equal to 0, because our initial statement says j is equal to -1, so we don't want to perform a calculation over there. Only then, if j is greater than equal to 0 and Mac is sleeping, we need to remove that value from the sum and then we will increment j further. So I think this solution looks good to me. Let me know if this solution is incorrect and what test case did you actually think of to identify there is a mistake in this solution.
Very quickly introducing what we're going to cover today, right? So today we're going to talk about sorting. And why is sorting important? I mean, sorting is essentially nothing but arranging data that you have in a particular order, right? For example, if I have a few numbers, I could say I want to arrange them in an increasing order. Or if I have people, let's say I want to arrange them in the decreasing order of their height or increasing order of their height, etc. The ordering, because you are able to order something, helps you in a lot of things. For example, sorting might then help you do binary search on that data if you want to look for something. Or if I give you queries around, hey, tell me how many numbers are bigger than a specific number. That also, I mean, if the array is sorted, you can just look for the index of the element, first element bigger, and then you know how many numbers are bigger, etc. So sorting helps in those contexts if it is ordered. In fact, most NoSQL DBs, they actually try to maintain data in a sorted form. Sorted set is what it is called, because it makes searching for data, looking for data, doing a bunch of analysis on data easier and easier, right? So today, we're going to, just to elaborate, we're not going to talk about searching. I'm going to talk more about sorting. Sorting is arranging data in a particular order, right? So for example, if let's say give you 5 numbers, I give you numbers, let's say 5, 10, 3, 2, and 8. These are numbers in no particular order, right? Now, if I say arrange these numbers in an increasing order, where the smallest number comes at the front of the list and so forth, that part is called sorting. So, I mean, if you sort this, then you'll have 2, 3, 5, 8, and 10. It's an arrangement of the given numbers so that they are in some particular form or order. As I said, like, the reason why it is important is because it helps you do a bunch of different kind of operations on the data fairly quickly if what you have is sorted. And I gave the example of NoSQL databases where they maintain data in sorted sets because it lets them do a bunch of different kind of queries in a sorted form. In fact, we will talk about some form of MapReduce when we go to system design modules. There also you'll see like a lot of things are generated in sorted forms. because it allows for certain more operations to happen later on. Does everybody understand like what sorting is? So maybe like the way I would explain sorting is taking just like in binary search, I took the real world example of searching in a dictionary, what we normally do in real life. I'm again going to be taking the example, a real life example of what we might have done in our lives before, right? All of us went to school, and in school we were made to stand in increasing order of our heights. Now let's take that example, which is I have a class full of people and I want to arrange them in increasing order of their height. Right now, assume they are standing in some random order. What are the different ways in which I can actually arrange them in increasing order of their height? And I'm going to take various sort of approaches I would have taken. And then I would sort of map it to what that approach is in real life. So approach one could be that I ask everybody to come one by one. And I mean, let's say if I have a few people already standing in the line, let's say I have few people that I've already arranged in the line. And let's say there is this new guy with this height that comes. In fact, it is better to imagine, I mean, maybe I can write the height of each of those individuals. Let me just write the height. So imagine I had somebody with height 1, 5, 12, and 27 already in the line. Somebody with height 7 comes. One thing which I can do is I can find the right position for this person, which is between 5 and 12. And I insert 7 there, which means then I'll have 1, 5, 7 here. And then 12 and 27, I'll push one space back. Right? So 12 comes here, 27 comes here, right? And then as people keep coming, let's say there is a person called 32. I'll figure out where 32 should lie here. I'll figure out 32 should come here. I'll insert 32 here. Everything up after 32 would be pushed one space back to make space for 32. Here there is nothing. This is called insertion sort. This technique where I get numbers, I figure out what is the right location for them. I can do that through binary search, or I can do that through a linear scan. Either is fine. Once I find out what their location should be, I shift all of the other numbers one space to their right, and then insert this number, new number, at the new location. Now, that is called insertion sort. If I have to write the approach for this, or the steps for this, basically assume that I am maintaining my sorted array in, let's say, sorted array list. That's a sorted list, which is initially empty. And imagine I keep getting a few numbers, right? What I do is I start from the end of this list. For example, here, if I had 1, 5, 12, and 27, and I wanted to insert 7, I'll start from the end. Is 7 already bigger than 27? It is not. So what I would do is I'll shift 27 one space to its right. So imagine this was the array. I have one space left here, so I'll shift 27 to its right. So 27 comes here. Then I go and again check 12. Is 7 bigger than 12? No, it is not. So I'll shift 12 to one space to its right. 12 comes here. Then I check the next number, which is 5. Is 7 bigger than 5? Yes. That means this is the location of 7 and I insert it here. That is, I keep doing this with every new number that I encounter, and that makes for what is known as insertion sort. What is the best case complexity here? Best case time complexity here. And what is worst case time complexity here? Best case for sorting. Order 1 would be the time complexity of inserting a new element, best case, right? Because you start with 7, you'll find that, let's say the new element that we are inserting in this new array, let's say that is 32. Best case is I look at the first element and I find that 32 is bigger than that, and therefore 32 just gets inserted here. It is for the addition of the last, like the new element. Order 1 is the best thing that you can do, but you'll have to add n such elements. So therefore, if you do order 1 for n elements, you will end up with order n best case complexity. So in the best case, insertion sort will take order n time. What is the worst case? When do we get the worst case? what is the worst case and in what kind of data would we get worst case. If the array was reverse sorted, which means if let's say I was giving you numbers, I first give you number 5, you insert 5, then I give you 4, you insert 4 here, right? Because you'll have to shift 5 1. Then I give you 3, you'll figure out that actually 3 is smaller, so you'll shift 5 here, and you'll shift 4 here, and then 3 comes here. Then I give you 2, you'll again like shift 5 here, you'll shift 4 here, you'll shift 3 here, and then 2 will come here. And then again, you'll do one more shift and to get 1 in if 1 is the next number, right? This ends up taking, I mean, for the first number, you take 1 step. For the second number, you take 2 steps. For the third number, you take 3. And for the fourth number, 4 and 5 and 6 and so forth. So this becomes almost order of n square. So worst case, this might take order of n square when the numbers are sorted in decreasing order. A very interesting question, which is, does the time complexity affect if we take linked list? There are 2 parts here, right? Like one is, I mean, there are 2 things that we're looking for. One is, what is the right index where this new number should go? And the second is shifting greater numbers to make space. One place right. So your linked list will save you on this time. So this time will become 0. However, finding this 1 in a linked list, because you can't really jump to a random location, you'll have to do a linear scan to figure out where the number should occur. Right? So that might still end up taking order of n square, because searching for the right index, the step number 1, that might end up taking order n. You can't apply binary search in linked list because you can't just jump to a random location in the linked list. Right now, the way I explained insertion sort was that you were getting a stream of numbers and then you're sort of sorting it by putting them in the right location. Now, whatever I said, that can also be applied to an existing array as well. Let me explain. Right now, the way I detailed insertion sort is by saying that, like 5, I am getting 5, then I'm getting 4, then I'm getting 3, then 2, then 1. Imagine I was already given an array, right? So imagine I had the array as, let's say 5, 8, 3, 2, 18, hypothetically, right? And I asked you to sort this array in place without using extra memory. I do not want to use any extra memory. Can you sort this array without using extra memory? Insertion sort. So I don't again have the flexibility of creating a new array. I am doing this in place. How do we do that in place? Even when you're doing in place, imagine I start from 5, right? So first I'll start with 5. I'll say I only have to sort this. 5 is the new number that I've gotten, right? So I have one place, 5 is the new number I've gotten. Obviously, it will go at this position. So 5 comes here. Then I go to the second number. And I say, let's put this in a temporary variable. Temp is equal to 8. Now, 8 is the new number I'm trying to insert in the first 2 locations, right? So first I'll compare with 5. Is 8 already bigger than 5? Yes, it is. So it will come here. Then I look at sorting the first 3 numbers. I pick 3. So I delete 3 from here, imagine. And it is, this 3 is the new number to be inserted. So first I check with 8. Is 3 bigger than 8? No, it is not. So 8 will come here. Is 3 bigger than 5? No, it is not. So 5 will come here. And then 3 gets inserted here. So now if you look, I mean, by now I have the first 3 numbers sorted. Now I'll take this number 2, which is I'm trying to sort the first 4 numbers. I'll take the new number 2 and imagine that 2 is the new number that I was getting. So I put this in a temporary variable. I'll do the same comparison. Is 8? No. So 8 comes here. Is 2 bigger than 5? No. So 5 comes here. Is 2 bigger than 3? No. So 3 comes here. And then 2 comes here. And then finally 18 is bigger than 8. So 18 will directly come here. Does that make sense? So same approach. All I'm doing is I'm saving on the additional space if an array is given to me already. The worst case time complexity is still the same. Nothing has changed in the approach. I'm just using the same space that was there in the array instead of creating a new array. Okay, so if we apply binary search for position, it will contain more computations, right? Finding plus swapping. Yes. If you do apply binary search, you'll first take log n time to find the right location. And then in worst case, order n extra time to create the space. I mean, right shifting all of the elements to create space for this other element, right? So it will end up taking n plus log n every single step instead of just n every single step. So this log n is additional. Overall time complexity will still remain n square because you'll do this n times. So instead of n into n, you'll get n into n plus log n, which is basically n square plus n log n, which is still order of n square. But why do that? I mean, why do this additional operation? Why not just start from the end? You have to shift the bigger elements one step to the right anyway. So just start from the end, shift the elements to the right, and then like fit the element wherever you find the first place. All right, everything clear till now? So that is one way in which you would sort, let's say, your classmates, right? The second approach that I have is, let's say I have an array, right? Like let's say the same array. I had, in fact, let me go with the original 5, 10, 3, 2, 8. So 5, 10, 3, 2, 8. And I put this in an array. Now what I know is that in the sorted array, the smallest number has to come at the beginning of the array. Do we all agree with that? Smallest number has to come at the beginning of the array, right? So one thing that I can do, which is not very optimal, but still works. So it is every single time I look at what is the minimum in my given array. For example, if I run this loop, I'll figure out that 2 is the minimum. I say, okay, great. If 2 is the minimum, let me push 2 to the beginning of the array. So 2 comes here. And then I can just swap it with 5. So 5 comes at the place of 2. So when I do this, 2 comes here, 5 comes here. Now what I know is that now 2 is at the right position. I only have to sort the remaining 4 elements. And I repeat the process. For the remaining 4 elements, I again look for the minimum. Find 3. So I swap 10 with 3. And then I sort the last 3 elements. And then again, like I look for the minimum 5, I put 5 here and then so forth, right? The only downside of this approach, while this approach works, the only downside is it is order of n square no matter what the input. So in the best case, worst case, everything is order of n square. The good thing with insertion sort was that there is a case where the best case was order n. So therefore the average performance could have been better. If we do this, it is always order of n square. I mean, basically the steps were find minimum. 2 is put in start of array and then start plus plus. That was the approach. If the array is already sorted, even then to find the minimum in the array, you'll have to look at all n elements. So every single time finding the element is taking you order n, right? So that approach is a precursor to bubble sort. So while this approach works, the question is, can we do something so that if the array is already sorted, then we don't have to go through all of the elements all over again, right? Like every single time finding the minimum takes me a lot of time. How do we decide when to break? Check whether the array is already sorted or not. Let me maybe give some other case, right? So insertion sort will still be order n if, let's say, only one element was not in its right position. Every other element was in the right position. For example, if the array was, let's say, 1, 2, 3, 4, 0. The array is just very simply some random elements. Bubble sort is a variation of exactly this. Bubble sort is, as the name suggests, it is like bubbling something to the top, right? So what you do is you compare all adjacent elements one by one. And wherever you have a pair of numbers, so what you do is, for example, let's say people are standing in some random order in the line, right? So for example, I have people standing as 5, 10, 3, 2, 8. Let me just write it like this: 5, 10, 3, 2, 8. My objective is somehow bubble the smallest number 2 to the top. So what I do is I say the last person standing in the line, hey, you compare yourself against the next person to you. You obviously know how to compare yourself against the next person. You can check your height versus the other person's height. Obviously, if you're standing behind and you're smaller, then you should swap yourself, right? So I say 8, look at 2. If you're smaller than 2, then swap yourself. 8 says, I'm not smaller. Great. Then I say 2. Look at the next person ahead of you. If you're smaller than that, then swap. And I do see that 2 is smaller than 3, so I swap. So 3 comes here, 2 comes here. Then I say 2, swap yourself against the next person if the next person is smaller. I figure out 2 is actually smaller than 10. Sure, I mean, should get swapped. So 2 comes here, 10 comes here. And then I again say 2. Again, compare yourself against 5. If you're smaller, swap yourself. So 2 again gets compared with 5. 5 comes here, 2 comes here. So what has happened in this one order n loop? The smallest number has bubbled itself to the top of the array. This is why, because the smallest element is bubbling to the top, it is called bubble sort. Even this approach in the worst case will take order n square. There is one difference here though. If there are no swaps that happen all throughout in this order n loop, then we just stop there. Which means if the array was already sorted, then we would not do the next iteration. We'll keep doing the next iteration as long as there is swap happening. So let me elaborate again. What happens is, imagine you're standing in the line. I start from the last person. I say, compare yourself against your neighbor. You compare yourself against the neighbor. If you are smaller, then you swap yourself. And then you do that till the start of the array. One thing which is guaranteed in this loop, whatever is the smallest number will bubble up to the top of the array. Then you're left with sorting only the remaining part of the array. And you also know if there is any iteration where I went from the last person to the first person, there was no swap happening between the neighbors, then I know that elements are already in the increasing order. I can just stop. I do the same process again. Now 2 I don't care about. I already know 2 is in the right position for the remaining elements. So I again start from 8. I say 8, are you bigger than 3? 8 will say, yes, I am. And I say 3, are you bigger than 10? No, I'm not. So we'll swap. 3 comes here, 10 comes here. 3, are you bigger than 5? You're not. So sure, then let's again swap. So 3 comes here, 5 comes here. Again, if you see, 3 has bubbled up to the top, which was the next smallest element. And then you're left with sorting only the last 3 elements. Any iteration where you don't have any swaps, your array is already sorted, you can just stop. Since we had 1 or more swaps in the first traversal, we'll start again from 8, but will not go till 2. 2 will be ignored. The first element is already sorted, so we'll be ignored. We'll stop here. Now that in the second iteration, we know that the first 2 elements are fixed, we'll start again from 8, but we will stop at after 3. We'll not look at 3 and 2 anymore because we know that they are in the right position. Every single iteration, what is happening is the smallest element is bubbling to the top. And any single iteration, I know that there is no swap that has happened. I can just break. And therefore, I do have a best case complexity, which is if the array was already sorted, I will do an order n iteration to figure out are there any swaps. But post that order n iteration, I can just break. Or if I reach a stage where, intermediary stage, where let's say I did these and then the remaining numbers were already sorted, then also I'll just break, right? So I'm not really spending time sorting if the array is already sorted. Does that make sense? Let me actually write the pseudocode for this. What I'm going to do is I'm going to start. So here's my inner loop, right? So I'm going to start from the last element. Let's say there is a j that starts from n minus 1, goes to, imagine I'm doing a loop of I from 0 to whatever. I'll tell you what 0 to whatever is. It goes to I. Imagine that like numbers till I are sorted. Right now, nothing is sorted. So n minus 1 to I. What I do is here I compare a of j with a of j minus 1. Now I know that in the right order, a of j should be bigger. So if it is smaller, if there are 2 numbers where the second number is smaller, then obviously they should be swapped. The second number, if it is smaller, if this is smaller, then they should be swapped because they are not in the right order. So I just say swap a of j, comma a of j minus 1, right? By the end of this, a of I will have the smallest element anyhow. I is starting from 0. A of I will have smallest element anyhow. I also keep track of one variable here. Has there any swap that has happened? Let's say there is a flag, which is initially 0. Whenever there is a swap that happens, I make flag as 1. If at the end of it, if I see that flag is 0, then I just break, which means this element was already sorted. There is no need to look at other elements. And then I goes from 0 to n minus 1. Yeah, sorry, this is I plus 1. Correct. So again, like what is happening in the algorithm is the smallest element is bubbling to the top, and you're just taking in the process, making sure that if the remaining elements are in the right place, there was no swap, then the element is array is already sorted. So let's just break. Yeah, actually we don't need the n minus 1. When we come to n minus 1, I plus 1 would anyhow, this j loop will not run. So I can just do n minus 2. again, let's look at what is the best and worst case complexity of this algorithm. Best case is order n, which is my array was already sorted or almost sorted. And then, I do this iteration, flag becomes 0, I break. And the worst case is when it is reverse sorted. So every single time I have to do a lot of these swaps, and it is actually order of n square. All right. So this is, by the way, called bubble sort. Find the smallest element, move it to the beginning. This is called selection sort. In selection sort as well, it's what we were discussing, where we were selecting the smallest element and moving it to the beginning of the array. That is selection sort. The reason why we are discussing this is these are intuitive ways of how we think about sorting, and the technique can come into use later on. Let's do a dry run with bubble sort just to see the best case, right? So imagine I asked you to sort this array 1, 2, 3, 4, 5. Imagine this was my input, correct? Selection sort is sort of a greedy algorithm, because what you're doing is you're saying that I know the smallest element should come at the beginning, so let's find the smallest element. You put it in the beginning, and then you sort the remaining array. Let me, however, show how the bubble sort is still best case order n. Selection sort, by the way, we can also make order n in one case. I'll also go over that. Selection sort, just slight variation, and it can become best case order n. Let's first look at how it becomes order n best case in bubble sort. Imagine this was your input, right? You start with I as 0. I is 0. J, your flag is also 0. J basically goes from, so you have your index 1, 2, 3, 4. J will start with 4 and it will go till 1, 4 till 1. And what do? Every single time you just compare A of J with A of J minus 1. So you check, is 5 less than 4? The answer will be no. So then you move on to the next J. So from 4 you will go to 3. From 4 you will go to 3. Then you compare 4 with 3. Is 4 less than 3? No. Then you will compare 3 with the previous element. Is 3 less than 2? No. Is 2 less than 1? No. So at no point this if condition gets executed. So there is no swap, and therefore flag never becomes equal to 1. So when this loop finishes, when the J loop finishes, you come to the point where flag is still 0, and therefore you break. So just after the first iteration with I 0, you end up breaking, because you figured out there was no swap involved in my array. So my array is already sorted. Why look at things again? So that's why you get the best case as order n. Worst case is obviously n squared. Now let's look at what is the case, or how do we make sure that even my selection sort, which is very greedy, can I modify it somehow so that also becomes or best case order n? Let's see. Let's take some random input, right? So I had 5, 3, 8, 4, 6. Now the way selection sort works is you go from the beginning, you look at you try to find the minimum element in the array. This is the approach just before bubble sort that I had talked about. You try to find out the minimum element in the array. In this case, I find 3 as the minimum element. And for this, I take an order n loop, right? In order n, I find minimum of the array. Now, if in this iteration only, I would have figured out that the array is sorted in this order n, if I figured out that the array is sorted, which is all of ai is less than ai plus 1, then my work is done. However, if it is not, then the smallest number that I found, which is 3, I try to swap it with the previous element. Basically, I try to put it here and shift all of the remaining numbers one step to the right, which means the array now becomes 3 here. I have 5, 8, 4, 6. In fact, let me just change the array a little bit so that it becomes slightly better. Imagine if the array was 4, 5, 6, 8. When I do the swap, then the array becomes, or when I push it here, then it becomes 3 comes to the beginning, and then I have 4, 5, 6, 8. Now, again, I know that at this point of time, 3 is at the right position. I still need to sort the remaining array. I'll again have to do an order of n minus 1 loop, this, and this to figure out the minimum number. In this case, it is 4 as the minimum number. But by the way, in this order n minus 1 loop, I figured out the array is already sorted. So I can therefore stop my process. The key thing to do here is when you find the minimum element, you don't just swap, but you shift the prefix of the array one step to the right, create space for this new element, and then you put it in the right place. If you do that, then the selection sort also becomes best case order n. One thing is, in most cases, you will neither be using bubble sort or selection sort or insertion sort. Actually, insertion sort maybe in certain cases, but most cases you'll not be using these. These are algorithms that are good to think about. The approach that we utilized here, this might come into use later on in some or the other kind of context or in some or the other kind of problems. But the sorting algorithm that is currently in use in most of the libraries that you use are either merge sort or quick sort. Quick sort as being the most popular one because it has better average performance, does not use additional memory. But those are the ones because they sort of perform in order of n log n time. All of these are worst case order of n square. Average case is also order of n square almost. Java 8's array.sort also uses quick sort. But like bubble sort, insertion sort, 3 algorithms that I talked about, they're good to know from their approach standpoint because there are some problems that might utilize this approach. These are not necessarily the sorting algorithms you'll use in day-to-day. Sorting algorithms that you will use, I'll talk about that in a few moments. But just so that I, again, complete my discussion on selection sort, let me write the pseudocode for selection sort. Pseudocode is very simple. Right now, if I have to sort, imagine when I is 0, I need to sort everything from 0 to n, right? So what I do is I take, this will go to some number, I'll figure out what. I'll take the loop from I to n. I'll figure out the minimum. In fact, let me actually also track its index. I can just keep it as a of I, and index is equal to I. And this loop can run from I plus 1. So if, let's say, a of j is less than min1, then minimum is equal to a of j, index is equal to j. Here, one of the other things which I also track is if a of j is greater than a of j plus 1, then there's a flag that I set to, let's say 1. Let's say there's a flag here, which is also 0. And once I have found my minimum, then all I need to do is all of the other numbers, they are shifting one space to the right. So I, again, once I have found the minimum, I will take a loop of j is equal to, and then at the end you have a of I is equal to min1. That is one way of shifting. Basically what I'm doing is if I have an array, let's say I have 5, 6, 3, 2, 8. I'm going through once to figure out what is the minimum. Once I find the minimum, I bring minimum to the front, which is 2 comes here. And then 5, 6, 3, I shift one space to the right. And then I try only sorting this piece, where every single time I have a flag to check, is this piece already sorted or not? If at all at any point of time I find that there is a section of array that is already sorted, then I just break out and I'm done. Here, I mean, I could very well also have done, instead of doing all of this, I could have done swap a of I, comma, a of index. I could have done this as well. As long as I'm checking that for the remaining array, is the array sorted or not? If the array is sorted, then I just break. That is the only optimization that I put in, nothing else. Now I'm going to be covering a few other sorting algorithms, and then we'll do a few problems on these. Count sort is the easiest one. Count sort is when the elements that you are sorting, they are limited in range. Limited in range meaning, for example, I tell you, hey, you have characters A to Z. You have a lot of characters and you need to sort them. Or you only have numbers 0 and 1. Or you only have numbers from 1 to 20. Then what you do is, instead of counting or basically maintaining like numbers themselves, you just count how many numbers. For example, I gave you an array of zeros and ones, right? So bunch of 0, 1, 0, 1, 1, 1, 0, etc., etc. And I told you to sort this array. One very simple way would be I calculate the frequency of 0 and frequency of 1, which is basically exactly what count sort means, right? Like you're maintaining the count of the numbers themselves. So you say like, I'll count how many times 0 came. Let's say 0 came 10 number of times. And I'll count how many number of times 1 came. Let's say it came 5 number of times. Then I know my sorted array. My sorted array is 0, 0, 0, 0, 0, 10 times. And then 1, 1, 1, 1, 1, 5 times. So one very common application of this is, if I give you 2 strings and I ask you, are these strings anagrams of each other? Anagrams is like 2 strings are anagrams if they are just some or the other permutation of the same string. For example, if I give you a string banana and I give you another string, let's say, this is not really a word, but I give you these 2 strings, right? And I ask you, are these anagrams of each other? Your answer will be yes, because they have the same count of n. There are 2 n's here, there are 2 n's here. they have same count of A. They have 3 A's here. There are 3 A's here. And they have same count of B. You know that you only have 26 different characters. So in a 26 array of size 26, you can maintain the counts of number of A's, number of B's, number of C's, and so forth. And you can just compare the counts, right? So count sort is very simple. If you have limited number of numbers, if your range is very limited, you maintain the count of every single number you encounter, and then like you just print those numbers, those many number of times you go from start to beginning. So we are going to maintain a new array for 0 and 1. However, 0 and 1 are just two numbers, two variables. So it is still order 1 space. If you only have, let's say, 20 numbers, then it's just order of 20 space, which is not order n, right? Like it is not dependent on the number of numbers that you have in total. Let me maybe give you an example, right? And then I'll write code for it that will make it clearer. Very simple. Imagine I give you a string of characters, and I just asked you to sort that string of characters. For example, let's say the string is congratulations. Let's say that is the string. And then there were a bunch more characters as well. But like, let's just say that this is the thing. There could be, let's say, thousands and thousands of characters here, thousands, hundreds of thousands of characters. Now, one conventional way of sorting is like doing the bubble sort or the selection sort, etc. Right? Which is a selection sort would be you figure out which is the smallest character, which is A. You shift A to the front. However, I mean, if there are a lot of characters, that will take a lot of time. So what I say is, hey, by the way, I know that the kind of letters could only be from A to Z, correct? I have A, B, C, D, E, F till Z, correct? There are only 26 characters possible, 26 different characters possible. So if I somehow maintain the character count, right? I have only 26 characters. If I have an array which has the count of what are the number of A's here, what are the number of B's here, C here, and so forth. For example, when I encounter C, I say, let's increase the count of character C by 1. So C's count becomes 1. And I mean, this could just be an array, right? Because any character can be mapped from a number from 0 to 26. So I just maintain an array of size 26, which is all initialized to 0 to begin with. When I encounter C, I increase the count of C by 1. Then I encounter O, let's say O is somewhere here, I increase the count of O by 1. When I encounter N, I increase the count of N by 1. With R, I'll again increase the count of R by 1. A will become 1. Let's say when I encounter A again here, A's count will become 2. So that way, I mean, I'm just maintaining count of every character, right? Like, and if I have to write code for this, I would just do very simple. I would say that, you know what, like I have a array of size 26, which is initialized to 0. This is C++ format, but like Java, etc., it will be similar. And then I just say, you know what, like, let's assume that the character is ch, and I go over this string str, and I just say that arr of ch minus a, which will now give me a number from 0 to 26 plus plus. At the end of it, I'll have frequency count of every character. And then like sorting is very simple. I just go character by character, right? So I just go from for I is 0 to 26. I look at the count of the current character. Like for example, when I is 0, then I'm looking at the count of A. So what I do is I take a loop from 0 to arr of I, whatever is the count, and I print A plus I, those many number of times. So what will happen is if the count of A was 2, then this will print A twice. Then let's say if the count of B was 1, then it will print B. If let's say the count of C was 3, then it will print C 3 times, and so forth. So all I'm doing is I'm just counting the numbers, frequency of the numbers, and then I'm just printing in them those many number of times, going in the order of numbers. Does that make some sense? Count sort, how is it working? As long as the range is limited. For example, let's say if you have numbers from minus 20 to 20, even then you can use the array, right? Because you can just say that every single number num corresponds to the index num plus 20. So when you encounter num, you just say, you know, arr of num plus 20 plus plus. And when you print, then like for arr of i's count, you print I minus 20. In general, if you see for doing this, if you have a range of numbers, let's say the range is R, count sort takes order of R memory, right? If the range from min to max of the array, if the range max minus min, if this is R, then it takes you order of R memory, right? Because you need those many number of counts variable, right? If R is small-ish, for example, let's say if R is 1,000 or 10,000 or 100,000 or 1 million, if let's say R is up to 1 million, then you can use count sort because you can maintain the counts and therefore like it will still run. However, let's say if the numbers were not limited, if there could be any integer, then you can't use count sort. Count sort is only applicable when the numbers are limited in the range. As I showed with counting characters in a string, because characters are limited. Characters can only have 26 different values. So it is not done in place in the sense that you're still counting the number of A's, number of B's and C's, and then you can fill it in the same array. For example, if you said, tell me here instead of printing A plus I can just say, you know what? Let's have an index variable, which is 0. And I have, let's say my original string was str. I can just say, you know what? Str of index plus plus is equal to I plus A. I can fill it in the same array instead of printing, but I mean, you'll still have to maintain counts, etc. Merge sort is if imagine you had to sort a deck of cards. One possible way, which is, by the way, also called divide and conquer, could be that I break down this deck of card to half deck of card and half deck of card. So I divide into two parts, right? Like half goes, let's say, to the left, half goes to the right. I sort those individually, right? So half deck of cards, I sort them somehow by some magic. And right side also I sort somehow by some magic. So now I have two sorted deck of cards. I have two sorted deck of cards. Now the problem becomes, if I have two sorted deck of cards, can I merge them so that they still remain sorted? Imagine, let me give you an example, right? So let's say I have an array, 2, 3, 5. Let's say I have another array, 1, 6, 8. If I was given these two arrays, can I merge them into another array which is completely sorted? Is that possible or not? If that is possible, then this could become another algorithm, which is like whenever I need to sort an array, I can divide it into two parts, recursively sort them, and then I can merge them. So merge becomes the important step. The question is, I have given you a problem. You have two arrays, not necessarily of the same length. Let's say this is of size A, this is of size B. Can you create another array of size A plus B, where all of the elements come from A or B, and they're all sorted? Is the question clear? Like you have some A number of arrays in array A, you have B number of elements in array B. Array A and B are individually sorted. So A is a sorted array, B is also a sorted array. You have to merge them into another sorted array. How would you do that? Basically, if I have been given two numbers, let's say I have an array A, 2, 3, 5, and I have an array B, which is, let's say 1, 4, 8. And I have to create a sorted array, right? Which is of size 3 plus 3, which is 6. 1, 2, 3, 4, 5, 6, correct? This is the eventual sorted array I have to contain or create. One thing is, the first element in the sorted array is going to be the completely minimum of everything in the array, right? So given array A is sorted, minimum from array A is on position number 0, correct? Minimum from array B is also on position number 0. So therefore, whichever is the minimum of these two, I don't need to look at any other element. Whichever is the minimum of these two is going to be the first element in the sorted array. Is that something you all agree with? And what is the minimum of these two? Minimum of these two is 1. So 1 comes here. Now, if I have inserted 1 here, then it is as good as saying that now I remove 1 from B. It is the same thing, right? So what I just do is, how do I remove 1 from B? I just change this pointer to now point at this number 4. This is as good as saying that I'm now merging two arrays, one array which is A and one array which is B, but B is starting from this point onwards. And I again do the same thing. What is the next number that should come here? It should be the minimum of numbers here and minimum of numbers here. What is the minimum of numbers here? Array at this pointer. What is the minimum of numbers here? The array at this pointer. Whichever is smaller, which is 2, comes here, and this pointer moves one step forward. So in short, the approach becomes that you have two pointers. Let's say there's a pointer 1, which is for array A. There's a pointer 2, which is for array B. And you just say the following: while pointer 1 is less than whatever is the size of A, and pointer 2 is less than size of B, you do the following. You figure out which one is smaller. You just check. If A of pointer 1 is smaller than equal to B of pointer 2, then simple. This is what goes in the sorted array. So let's say sorted of, let's keep an index A of pointer 1. You increment the pointer 1 plus plus because now pointer 1 has been assigned here. Else you put pointer 2 element here. So sorted of, again, index plus plus is equal to B, pointer 2 plus plus. The only thing is, when I'm done with this while loop, it is possible that all of the smaller elements were in one of the array. Imagine like this array was 1, 2, 3 here, and there were, let's say, 4, 5, 6 here. My pointer 1 will end up going here, and I'll end up breaking out where I've only filled in 1, 2, 3 in the sorted array. 4, 5, 6 is yet to be filled. So I'll have to check for that, which is at the end of this while loop, if whichever pointer is not done. So I just check while pointer 1 is less than size A, I just keep adding sorted of index plus plus is equal to A of pointer 1 plus plus. And very similarly, I do the same thing with pointer 2. While pointer 2 is less than size of B, same thing, sorted B of pointer 2 plus plus. Right. That will cause the merge to happen. Does this make sense? Right. Now, if that can happen, which means now if merging can happen, and what is the time complexity of this merge? Imagine I have two arrays of size n and n each, n plus n, right? Like, so it takes me order n time to merge. If in fact the array A was of size m, this was of size n, it takes me order of n plus n time, right? That means if I have a order n array to be sorted, if I divide it into two parts, I say that sort the first part separately, sort the second part separately. Once they are sorted, then merging them will take me order of n by 2 plus n by 2 time, which is order n time. So merging them will take me order n time. Now, how do I sort the first half of the array? I can do the same thing with the first half as well. I can say that even to sort the first half, again break it down into two parts, and then sort the first half, sort the second half, merge it. With the end condition being that once I have an array of only size 1, it is already sorted. How about I modify this and I say that I have 3 arrays that need to be merged, right? Imagine I have an array 2, 5, 10. Imagine there is another array 1, 8, 9. And imagine there's another array 3, 4, 12. Let's say there were 3 arrays, right? How would you merge these 3 arrays into one array, which has all elements are sorted? We can do 2 at a time, but we don't necessarily need to, right? Like, we look at this, right? What is the first element going to be in the merged array? It is the smallest of all. Where does the smallest come from? It is either the first element from here, or the first element from here, or the first element from here. Whichever is the minimum from here, that becomes your smallest. So I can have 3 pointers. Pointer 1 pointing to the 0th element, pointer 2 here, pointer 3 here. Whichever is the smallest of these 3, which in this case is 1 comes here. And then all I do is I move this pointer 1 step to the right. And I again repeat the same thing. Whichever is the smallest of these 3, which is 2 comes here. And then 2's pointer moves 1 step to the right. Now again, 5, 8, 3, whichever is the smallest, 3 is the smallest, 3 comes here. And 3's pointer moves to the right. 5, 8, 4, 4 is the smallest, so 4 comes here. And its pointer moves to the right. 5, 8, 12. 5 is the smallest, so 5 comes here. And 5's pointer moves to the right. And then so forth, right? In the case of merge sort, it is only 2 arrays. An extension of the previous question. Then instead of 2, if there were 3 arrays, how do you go about merging 3 arrays? I mean, you can merge 2 arrays at a time. You can merge these 2 at a time, and then you end up merging these 2. But you'll end up using more memory, because to merge these 2, you'll need an additional array of size 6. Then you'll create an array of size 9. What I'm doing is I'm just directly creating an array of size 9 so that I reduce the amount of memory required to maintain that intermediate re-array. Also, I reduce a step. Okay, all right. Coming back to the merge sort. How does merge sort work? As the name suggests, it's divide and conquer, which is basically, now that I know that I have the superpower of taking 2 sorted arrays and merging them, what I can do is, given an array A, I sort the first half. So sort A to 0 to n by 2, sort A of n by 2 plus 1 to n, and then merge these guys. That can become my approach. And this, how do you sort the first half? This also can happen in the same way. where you again divide it into two parts, 0 to n by 4, and then n by 4 to n by 2, and again, then you merge, etc., right? And if I have to write code for this, it becomes fairly simple, which is, let's say if the question was, how do you sort array A from index I to index J? If obviously like the size of the array is already 1, which means if J is equal to I, let's just put that, then your array is already sorted, so you can just directly return. If not, then what you do is you basically sort the first half, which is you say, I'll go from A of I to mid, where my mid is I plus J by 2. Then I'll sort A from mid plus 1 to J. And once these two guys are sorted, then I will need a temp array where I'll merge the array from I to mid and mid plus 1 to J. And then I'll make sure that A of I to J becomes equal to temp. I'll just do that. But basically, I'm just applying recursion here. And what I'm saying is, if you want me to solve, by the way, let's say there are 4 numbers, right? 5, 3, 2, 6. Let's say those were the 4 numbers. I say that first sort the first half. So let me call the function to solve these 2 numbers, 5 and 3. Somebody sort this and then give it to me. And then sort the second half separately. So somebody sort 2 and 6 and give it to me. And once I have them sorted, then I will actually merge them, right? Now to sort 5 and 3, I again do the same thing. I split it half. I say somebody sort 5 for me and somebody sort 3 for me. Here also somebody sort 2 for me and then 6 for me. Once they are sorted, then I'll merge. 5 is sorted, 3 is sorted. How do I merge? In my merge step, the same way we had seen, we have 2 arrays. We have to merge. When we merge, this will become 3, 5. And that is what I replace my original array with. So this array becomes 3 and 5. Very similarly, 2, 6 remains 2, 6. And then once I have 3, 5 and 2, 6, then I merge them to find 2 comes first, then comes 3, then comes 5, then comes 6. And this becomes my actual sorted array, which I replace this with. Just out of curiosity, why do we divide them into equal halves? Although in the end, we move 2 single elements and merge them in sorted order. Can't we take pairs in the array and do the same way of merging? Let's say I have more numbers, right? So imagine I had 5, 6, 8, 1, 2, 13, 15, 12, 3. How many do we have? We have 4. And let's imagine I remove 12 from here. Question is, if we have to sort anyway, why don't we take pairs by pairs, right? So let's just take pair 5, 6, 8, 1, 2, 13, 15, 3. And let's just first sort them. So we end up sorting them. And for example, we end up finding that this is 5, 6. This becomes 1, 8. This is 2, 13. And this becomes 3, 15. Right. Now, the problem is like we've done pairwise sorting, but the array is still not sorted. Then we'll have to do sorting of 4 elements each, right? How do we do that? We say that, you know what, like there are first 4 elements here. The first half is sorted. The second half is also sorted. Let's merge somehow, which again, I'll take another array and then I'll merge, etc. So this will get sorted. Then I'll do again the same thing, which is I take 4 elements, half is sorted, and I'll do the same thing. And then finally, I'll look at all of the 8 elements. So you're going just in the reverse order. What I just said, you're just going in the reverse order, which is also correct. It's just harder to code because the previous approach can be coded using recursion, which I'll just show. In your approach, what you're doing is you're building bottom up, right? Like you're sort of saying that let's first sort all pair of elements. Once they are sorted, then let's look at all 4 size elements. Great. Once they are done, then let's look at all 8 size chunks. Once they are done, then look at all 16 size chunks, and then 32 size, and then 64 and so forth. Right? And finally, I'll have the entire array sorted, which works. It's just harder to code. What I said was the other way around, that instead of going from 1 to 2 to 4 to 8 and so forth, let's start from n. Let's divide that into n by 2 parts, then n by 4, then n by 8, and I'll finally reach the 1 part anyway. And then my recursion function will keep returning and I'll have the eventual answer. So if you look here, my recursive function, this will do the same thing. My recursive function here will also do the same thing. Let me also just write it as merge step. So what is happening is, if I have an n-sized array, I'm dividing it into 2 arrays of size n by 2 each, n by 2 each. I'm sorting it using the same methodology, which is this n by 2 will create arrays of size n by 4, n by 4. Here also again same, n by 4, n by 4. These will create arrays of size n by 8, n by 8, again n by 8, n by 8, same thing. And this n by 16, n by 16 and so forth. How many levels will you have here? I mean, we go from n to n by 2, n by 2 to n by 4, n by 8, 4 to n by 8, n by 8 to n by 16. How many levels? Log n levels, right? So in every level, n is becoming half of what it was. As we have seen the same pattern in binary search, etc., etc. I mean, as you go, if n is becoming half of what it was, it takes you log n steps to finally come to 1. At every step, what is happening? At every step, basically, I have n by 2 sorted array. I'm merging them, which takes me order n time. This takes me order n time. N by 2 plus n by 2 and order n. What happens on this level? These two guys merge and it takes them n by 4 plus n by 4, which is n by 2 time. These two guys merge and it takes them n by 2 times. If you add them up, it will take you order n time on this level as well. Very similarly, on the other level as well, where you have n by 8, there are 8 instances of n by 8. It will again take you order n time. So the total time taken on every level, it takes you order n time. There are log n levels. The total time taken is n log n. That is an intuitive way to understand. I can also explain the mathematical way of explaining this. But the intuitive way of understanding the time complexity of merge sort is that on every level, you're doing one merge. The merge is order n. Number of levels is log n. And therefore, in fact, if you look at Arvind's approach, if you were to implement it, in every iteration, what you're doing is you're first creating pairs and you're merging the pairs. Takes you order n time. Then you're looking at all 4 blocks, right? Like blocks of 4 each. In one order n operation, you will have sorted blocks of 4 each. Then in again one order n operation, you would have sorted blocks of 8 each. And you'll keep doing that till you cover the entire array. So the number of steps to cover the entire array would be log n. And every single iteration is an order n iteration. So it takes you an order of n log n. I can explain the math behind it as well. Is it n log n in every case? Best case is, sure, I mean, you can probably put an optimization that if the array is already sorted, if a half is already sorted, you don't need to do all of the splitting, etc. So best case, you can still make order n. But yes, worst case is order n log n. Worst case, it takes you order n log n. And you can put a check to make sure that you're not doing the entire splitting, etc. if the array is already sorted. All right, what is the space complexity of merge sort? So if you look at the implementation here, we are allocating this additional memory temp to calculate this merged part, right? Why? Because when we are merging two sorted arrays, we need this temporary space where we put in the result, which is not a part of the original array. This is additional space. If I have to look at this tree, in this n by 2 part, I would have taken a temp array, which was of size n by 2. Here, I would have taken a temp array, which was of size n by 2. In fact, let's look at total space allocation, right? So this n by 2 will make a call to n by 4, 8, etc., etc. So this is a log n stack memory space. Plus, in each of these, so imagine I was sorting this array of size n. This will end up calling for n by 2. This will end up calling for n by 4, n by 8, and so forth. In each of this, I would have a temp array allocated, which will be freed as long as, I fill it back, right? So this temp array here is of size n by 4. As soon as I am done, then this will be freed. Then I come back here. Here it will be of size, additional size of n by 2. As soon as I'm done, it will be freed. And then I'll come back here and I'll have a temp array additional size n. So maximum space that I end up using additional is I have log n stack of recursion. Plus I have this additional order n size array that I might have used, which is my temp array. So order n extra space is what we end up using apart from the array space. So space complexity becomes order n. Time complexity becomes order of n log n. There's one more way to, by the way, calculate time complexity. If you assume that the time taken for sorting an array of size n is tn, then tn is nothing but, I'm saying first sort array, first half of the array, then sort second half of the array, which is also of size n by 2, and then merge them, which is it takes you some n time. Let's say it takes you n time. This is basically saying 2 times t n by 2 plus n, right? If you break it down further, your n by 2 is 2 times t n by 4 plus n by 2, which is the same as 4 times t n by 4 plus 2n. which you'll see will finally come to 2 to the power I t times n by 2 to the power I plus n into I. I mean, this is just a little mathematical. Therefore, I explain the intuitive way first. Which, I mean, if you want this to become equal to 1, I becomes log n. So you have n into t times 1 plus n into log n, which is n log n. This is how Master's theorem actually works. I'm just elaborating that, expanding that equation. Even if you don't know about Master's theorem, that is fine. As long as you understand the intuition of why it is n log n. Because in the recursion tree, there are log n levels. On every level, I'm using order n time. So time complexity becomes order of n log n. Space complexity becomes order of n. Is there any way without using the extra space? So actually merging two sorted arrays without using extra space in order n is not possible. That becomes the blocker, right? So if you can merge the array in place without using extra memory, then your problem would have been sorted. But the problem is like merging without extra memory is the issue. All right, does this make sense? Merge, sort, space complexity, time complexity, all of that. All right. Today we'll be talking about quicksort, and today we'll be solving a lot more problems actually. By the way, I just wanted to maybe also share one news with all of you. Today was the first case when one of the fellow students at Scalar has gotten an offer as a CTO at one of the energy companies, which is a fairly big company now, right? And that the reason why I'm sharing this with all of you is to show you that, look, I mean, learning matters. I mean, and like, again, I can't disclose the exact salary of the person, but it is in a few CRs. We're not talking about lakhs, right? So the thing that matters at the end of, I mean, that is basically the North Star for all of us. He's 30 something, but like we all should focus on the learning aspect. As long as we do that, eventually all of us will succeed. We'll go and build really, really great things in the future. He is part of Scalar Academy and not Scalar Plus. And I can't disclose the name of the company. And I'm sure like that news will come out later on. It will be shared with all of the community as well. Once he joins, it's still sort of confidential. But just letting you guys know, I mean, look, it is important that all of us focus on learning. As long as we do that, I mean, obviously, like what you find later on is going to be a function of what you know at present, plus like some bit of experience. I mean, so again, just to also elaborate, this person is not somebody who is very young. As I said, like he's 30 plus, already has more than 7-8 years of experience, actually has more than 10 years of experience. But as long as you keep learning the right things, you'll keep moving forward, right? And that is, all of us should just aspire to become 1% better every day. That being said, back to what is the agenda for today. Today, we're going to actually talk about one sorting algorithm, which is actually used in most libraries that you use, be it in Java or Python or C++. The sort function that you use, they all use a different algorithm, which we will talk about today. But instead of talking about the algorithm, which is, I believe, not the right way to introduce a concept, what I'm going to do is I'm going to give you a problem, a real life problem that you may take an attempt at solving. And then we'll use that to maybe introduce the approach. So imagine this. Imagine you have a bunch of nuts and bolts. You have nuts and bolt, right? So nuts basically look something like this. And then you have bolt that is basically a circle that fits into the nut. The nuts and bolt, and usually like they're created in pairs, right? So you have a nut of a size and then the bolt actually clearly fits. If the nut and bolt are of the same size, then they fit. Now imagine you have a lot of nuts and lots of bolts. And you are given that every single nut is of unique size. It is every single nut and bolt are of different sizes. So none of them have the same size. And you're also given that every nut has a corresponding bolt. One fact that is given is every nut has corresponding bolt, which means they both fit each other. 2 is no two nuts have same size. So they're all different sizes. However, it is very hard for you to just visually differentiate which one is bigger or which one is smaller. So what do you do? What do you do is, like, if you pick a nut and you pick 2 bolts, if the bolt is loose, then you know that the bolt is bigger. If the bolt is not going in, then you know that the bolt is actually smaller. Now the problem is, given that info, can you sort all of the nuts and bolts in increasing order of their size with the right nut and bolt paired up? Currently, they are all just in this array. You have a table full of nuts and bolts. You don't know which one is paired up with which one, right? One is how can you arrange that? And 2 is how can you do it as fast as possible? Let me explain again, right? So imagine this. Let's say I had only 2 nuts. Imagine I had this nut, another nut, and I had another bolt and then another bolt, right? Now, what I can do is I can pick, let's say, this particular one, and I pick this one, and let's say I try to match them. There are following things that can happen. One is these guys clearly fit. In that case, I know that this nut is to be paired with, let's just call it bolt 1, bolt 2. This is nut 1, nut 2. If they fit, then I know these guys are in the pair. They belong together. And then I can just compare the other bolt. If it is smaller than this particular nut, then it goes before this nut, right? If it is smaller, otherwise if it is bigger, it goes after. And then I definitely know that the pair for this bolt is this nut, right? So I just put these two guys together, either after or before, depending on how it compares with this current nut. So if I have to define the problem formally, you can pick a random nut, an X, and you can pick a random bolt. If you pick these two guys, you will get either of the following result. Either you will get nx is equal to by, which means both of these guys belong together, or you will get to know that, by the way, this nut is smaller than bolt, or you will get to know that nut is bigger than bolt. These are the 3 results you can get. You cannot compare nut with nut. So for example, I cannot get nx and ny and compare these guys. I can't. Similarly, I can't compare bolt with bolt. This I can't do. This I can't do. However, I can take a random nut and a random bolt and I can compare them. Does that make sense now? It does, right? Now, I mean, the question is, how do I sort these guys? How do I sort these guys? When I can't really compare a nut with a nut and a bolt with a bolt. The bolt size is not given to you. I mean, think of it like this, right? You have a table which is full of these nuts and bolts, and there's only minor variation in the size. What you should end up with, for example, in this case, imagine that these guys were equal. N1 and B2 was equal. So I would put N1 and B2 together and assume that B1 was smaller than N1. So I would put N2 and B1 before this. And I will return this list. N2, B1 as the first entry, N1, B2 as the second entry, right? So if you just compare with a bolt with a nut, you do get the relation, whether a nut is bigger than a bolt or not. So imagine if this nut was paired with another bolt, BZ, then you know that BZ is actually smaller than BY. So you can compare the pairs by picking nut from one pair, bolt from another pair. There is no size given. The only way is you just pick a random nut and bolt and then compare whether one is smaller than the other or not. Let's actually look at how do we do that, right? So one is, if I pick any random nut, let's say if you're given, let's say n different nuts, let's say I pick some random nut. Let's call that nut N1, right? What I can do is, now I have a bunch of bolts. I have B1, B2, B3, B4, B5 till Bn. I can compare each of those bolts with this N1. And I'll basically get 3 kinds of bolts. There will be one heap of bolts which are lesser, right? So there's one heap of bolts which are smaller than N1. There is one heap of bolt that we will get. Let's call this bolt bigger, which is bigger than N1. And there is exactly one bolt that I will get, which will be equal to this nut, correct? If I compare all of the bolts with this nut, I'll get 3 sets, one bolt which is equal, and then a set of bolts that are smaller and set of bolts that are bigger. How these guys compare amongst each other, that I don't know. But essentially, I do know which bolts are smaller than this nut, which bolts are bigger than this nut. That you guys all agree with? So if I pick any random nut, I can distribute all of these bolts this way. And very similarly, now that I know that this bolt is the same as this nut, so I can pick all of the nuts, which were N2, N3, N4, N5, N6, N7, N8 till N. And I can say, let me compare all of these nuts with this bolt, right? I'll get some nuts that are smaller. So I'll basically have some of these guys. If I compare with this bolt, I'll get some nuts here. Let me take a different color. Some nuts here, which are smaller. Some nuts, which are bigger. The equal one is already here. So you'll not find anybody who's equal. So what we have done is, we first started with one nut, right? And then we use that to break all of the bolts in 3 parts. One bolt which is equal, a lot of bolts that are smaller, a lot of bolts that are bigger. And then once we found the equal bolt, we use that bolt to actually split the remaining nuts into 2 parts, smaller nuts and bigger nuts. Now what I know is, all of the bolts, smaller bolts, will have their corresponding nut somewhere here. I mean, basically now I have 3 sets, right? I have a set of nuts and bolt which are smaller, and they are guaranteed to be present in pairs here. Same guarantees holds here. Then I have one pair which is N1, B1. And then I have set of nuts and bolt that are bigger. Now I can actually recursively sort this set separately, and I can sort this set separately. But my problem has now reduced to sorting smaller set of nuts and bolts. And if obviously if the set only had one element, then I know that they are already sorted. I don't need to touch them. This is exactly how quicksort works. I'll introduce it very, very shortly. But let me take a few examples just to show how is this working. And that will give you a sense of or sort of some intuition behind how quicksort works. So imagine I was given some random, let's say N1, N2, N3, N4, N5 nuts. And let's say I had random 5 bolts as well. What I'm going to do is I'm going to mark, let's say hypothetically, what the process is going to be like. So what I'll do is in step 1, I'll pick this nut and I'll say, let's compare it with all of these 5 bolts. And we'll find some bolts that are bigger, some bolts that are equal. Imagine, hypothetically, let's say N1 was equal to B3. And imagine that B2 and B4 were smaller bolts. And we found out, let's say that B1 and B5 are bigger bolts. Very similarly, then what I did was that I picked B3 and I started comparing B3 with all of these guys, N2, N3, N4, and N5. And I would come to know whether they are bigger than B3 or smaller than B3. All of the bolts, again, let's say hypothetically N2 and N3 were smaller, and let's say N4 and N5 were bigger. Now the problem becomes that I know that N1, B3, whenever I sort, is going to be the third element in the set. I have 2 elements before. I don't know their order, but those 2 elements have basically B2, B4, N2, N4 as 2 pairs. And I have 2 elements after, which is B1, B5, N4, N5 that are yet to be sorted. That is after, right? However, this portion is fixed. I don't need to change this portion. It is in the right position. It is where it should be. I do not need to change this position. This is already in its correct position. So then what I do is I recursively sort the first half. And then once this is sorted, then I'll go to the second half. How do I sort the first half? I again do the same thing. I say, let's pick a random nut. Let's say I pick N2 as the random nut. And I compare B2 and B4 with it. Oh, sorry, this should be N3. So B2, B4, N2, N3, B1, B5, N4, N5. Right. Okay. So then let's say pick N2 as the one nut, right? And I compare B2 and B4 with it. I know that I don't need to compare B1 and B5. They're definitely bigger. I'll deal with them separately. I'm only concerned with sorting these 2 pairs. So I compare B2 and B4. And hypothetically, let's say I find that N2 is the same as B4. So I find these guys are equal. And hypothetically, let's say I find that B2 was bigger. I know that B2 will be paired up with N3. So I put it as it is. These guys are sorted now. Then I have N1, B3. And I do a very similar process here as well. I pick any one of these guys. Let's say I pick N4. And hypothetically, let's say N4 pairs up with B1. And I find that B5 is smaller. So therefore, B5 will come here. The pair of B5 is N5. That will come here. So this becomes your sorted array totally. Now this process where I actually picked one element and I started comparing all of the remaining elements with it is called choosing a pivot. So while this is a more complicated case, let me take an example of sorting an array of integers. And I'll show you with that. Imagine, let's say my array was 5, 2, 1, 8, 6. N1 of B3 is largest. That means this set does not exist. The set is empty. But the remaining set is still smaller set than what you began with. It has now n-1 bolt and n-1 nuts. So you still have a smaller problem to solve. So in every step, you're reducing the size of the problem. So that is actually your worst case where you will end up taking n square time. But still, I mean, that still gets you to your answer. So at each step, one of the pair comes at its right place. Let me just elaborate that with this array as well. So in the quicksort process, what you do is you pick one element, any random element, to be the pivot. For example, I say that I want to pick 5 as the pivot. So what you do is, the first part is you count how many numbers are smaller than 5, right? So you basically, let's say, have 2 is smaller, 1 is smaller, 8 and 6 are not smaller. That means the right position of 5 is the third position because there are 2 numbers smaller. So what you do is you put 5 here. 1 probably comes here. So your array is basically 1, 2, 5, 8, 6. And then once you have put 5 in the right position, then you compare all of the remaining elements. What you want is all of the smaller elements are on the left side, all of the bigger elements are on the right side, which in this case has automatically happened. But in case it wasn't, what you would do is you would start from here and you would start another pointer from here. The first number that you find on the right side, which is actually smaller than 5, you'll stop there. You'll try to find the first number from on the left side, which is actually bigger than 5. You'll stop there and then you swap those two guys. So in order n, you'll be able to get to a place where all smaller numbers are on the left side, all bigger numbers are on the right side. And then the problem becomes that 5 is in the right position. Now, as long as I can sort the left side of the array and right side of the array separately, my entire array will be sorted. And that I can again do recursively. So in every step, when I choose a pivot, one number will come at the right position and it will divide the remaining array into two parts, two smaller subsets that need to be sorted. Do we have to take pivot as the middle to make the swap easier? I mean, so if the thing is when you're choosing the pivot, you don't know which one is the middle element. I mean, you basically start with choosing a random number as the pivot in the array that you have to sort. If you are unlucky, then it would turn out to be one of the numbers, which is either the highest number in the array or the smallest number in the array. If you are, I mean, if it is just very, very random, chances are you'll find a pivot somewhere towards the middle. I mean, let me actually go step by step. Does the nuts and bolt approach make some sense? Basically picking one nut, comparing all of the bolts with it to divide them into smaller heap, bigger heap, equal to, and using the equal to bolt to divide the remaining nuts into a smaller heap, bigger heap, equal to. And I know that the equal to part is in the right position. Now I need to sort the smaller heap of nuts and bolts separately, bigger heap of nuts and bolts separately. Let me take another example of this. Actually, here there was a swap. Let's see what kind of thing we can do where we would need a swap. Imagine I still have 5 as the first element. Let's say there is 6, 8, 1, and 2. Hypothetically, let's say this was the array. And again, we chose 5 to be the pivot. If 5 is the pivot, the first step, let's count the number of numbers smaller than 5, 1 and 2. So that means 5 should come at position number 3 in the array. So 5 should come here. So what do? The quickest way is I just swap, right? So I just bring 5 here, I bring back 8 here. So 5 comes here, 8 comes here, I remove the circle. Now I know 5 is the pivot. What I want is all smaller numbers should be on the left, all bigger numbers should be on the right. Right now it is the opposite. So what do? I say that I'll start with a pointer on the left side. Let's call it start pointer. I'll also start with a pointer on the right side. Let's call it the end pointer. Or maybe we can just call it left and right. Both are also okay. Left and right. I compare the first number and I see whether it is in the right half or not, in the correct half or not, right? So 2 is smaller than 5. It should have been in the left half. So it is not in the correct half. So I make my right pointer wait here. My right pointer is currently pointing at 2. Very similarly, I start a loop on left to find the first number, which is not in the correct half. In this case, the first number that I find, which is 8, is not in the correct half because 8 is bigger than 5. It should have been on the right half. And then the first place wherever left and right is, I just swap them. So essentially 2 comes here, 8 comes here, and I now know that these two guys are in the right half. So then I again start moving my left till I find the next number which is not in the right half, which is 6. So my left will wait at 6. Very similarly, I start moving right to find the next number which is not in the right half, which would be 1, and I'll just wait at 1. And I end up swapping 1 and 6. So 1 comes here, 6 comes here. So your right pointer will move from this position to this position, and your left pointer will move from this position to this position. If you add these guys up, you'll get total sum as n minus 1, n being the size of the array. This will help you shift all smaller elements to the left of the array, bigger elements to the right of the array. So if I have to write the steps of quicksort, one is choose any number randomly as pivot. And then once you have chosen a pivot, put pivot in the right position. For calculating the right position, you'll have to count numbers smaller than pivot. So this is one order n iteration. Third thing that you do is using left and right pointer, shift smaller numbers in left half, bigger numbers in right. So the fourth step is sort left part and right part separately. can be optimized by choosing the correct pivot. The most optimal pivot is your median, basically a number which can divide the array into two equal parts. That is the best pivot, right? Because then you're left with smaller arrays to sort. It is obviously faster to sort smaller arrays. However, the problem is it is very hard to know what is the median of the array. Why would you want to spend a lot of time finding out the median? So what quicksort says is, as long as your pivot choice is completely random, if it is completely random, then you're still fine. Average time complexity will still become n log n. All right. What is the approach behind quicksort? Quicksort is essentially choose a pivot, divide the array into smaller numbers, bigger numbers, sort the smaller number separately, sort the bigger number separately. Your array will automatically be sorted. Divide and conquer. Most of the library functions that you use, they use quicksort and they choose pivot randomly. I'll explain why randomly still works here. The one thing which you will notice is in this entire process, we have not used any additional memory. We did the swapping, etc. in place. So we have not created a duplicate array. All of this is happening inside the same array. That is important because while merge sort also is order of n log n, which we will see with quicksort, merge sort uses additional space, or it requires this separate array where you merge the two arrays, which is additional memory required. So one of the reasons why merge sort is not used extensively, but quicksort is used extensively, is because quicksort does not use additional space. The worst case of quicksort is still really bad. Collections, you also use quicksort. Now, since we don't have random access, how does it work? For example, if you use, what you're saying is, let's say if we have implemented the list with a linked list, then how would the quicksort sort of work there? Because here, if you see in the quicksort, you're not really doing random access. All of your access is still sequential, right? For example, let us go step by step. We say, let's choose any number randomly as pivot. I can take a loop till the number because I'll still anyhow have to take an order n loop throughout the entire list to count the number of numbers smaller so that I know what is the right position. I'll have to do that anyway. So I take a linear loop to get to the number. That's fine. I take a linear loop to find out the right position. And again, I do the same thing. I anyhow have to split the numbers into left and right pointer. I can take a linear loop for that. So in all of this case, if you see, I'm not doing any random access. I'm actually going step by step in a linear loop. Let's do, what is the time complexity analysis? Let's do, what is best case? What is worst case? And what is average case? What is the best case with quicksort? What is the best pivot you can choose? Assuming that the array is not already sorted, what is the best pivot you can choose? Median. Let's say you were very lucky and you were choosing the middle element all of the time. What would happen is, if you were given an array of size n, you would put the median in the right place. So median would be in the right place. And then you'll have an n by 2 size array here, n by 2 size array here. You'll need to sort these separately. So what happens is exactly like merge sort. You start with an array of size n. This reduces to sorting array of size n by 2 twice. One on the left side, one on the right side. That becomes, basically time to sort an array of size n is the same as 2 times tn by 2 plus order of n for merging. And this basically comes to order of n log n. So if you are choosing the median as the pivot all of the time, then you end up sorting it in order of n log n. If you are choosing the median as the pivot every time. And by the way, this is probably not the best case. Best case is in the array is already sorted. Best case meaning that if you're given an array and then your median is the best, right? So you end up sorting in order of n log n. What is the worst case? What is the worst kind of pivot you can choose? One end, when your pivot is actually on one of the ends. So what happens is, in one step, in order of n, what you would do is you'll end up choosing a pivot that is on one end. So your pivot is here, and you'll find all of the other remaining n minus 1 elements are on one side, which means that in one order n loop, you have only fixed the position of one element and you still have n minus 1 numbers to be sorted. And if you keep doing that again and again, if you're extremely unlucky, your time to sort will become n plus n minus 1 plus n minus 2 plus n minus 3 plus n minus 4, which is order of n square. So your worst case becomes order of n square. If you're very, very unlucky that you're choosing the extremes as your median all of the time. Does this make sense? Why is the best case order of n log n? Why is the worst case order of n square? Just in terms of how we choose the pivot. If we are really, really good with choosing the pivot, then we end up choosing the median as the pivot. That means it divides the array into 2 equal halves, which is exactly the kind of thing that we did in merge sort, right? Like you start with an array of size n, you end up with two equal halves of size n by 2 each, which you have to sort, which again will split further into n by 4 if you again choose median. This tree will have log n number of levels. On every level, you're doing order n operation. So your becomes the best case. If you're choosing the best pivot, then it becomes n into log n. If you are choosing the median as a pivot, then you'll have order of n log n complexity. That is clear to everybody, right? Okay. What is the worst case? Worst case is when you're choosing one of the pivot. Your time to solve or sort n sized array is in order n, you were able to fix the position of one element. The other n minus 1 still need to be sorted. And if I just expand on what Tn minus 1 would look like, it would be n minus 1 plus Tn minus 2, which is what? N plus n minus 1 plus, what is Tn minus 2? N minus 2 plus Tn minus 3, which if you keep adding up will become n square. I was not talking about the best case really. I was talking about given an array. If let's say I had flexibility on what I choose as the median. So what kind of pivot will give me the best complexity? What kind of pivot will give me the worst complexity? That was what I was looking at. Right. So what is the average case complexity? One algorithm that I wanted to address, which is called bucket sort. If you guys remember, we did something called a count sort, right? Which is when the elements were in limited range. We would just count the frequency of elements and that would help us sort. Bucket sort is a slight variant of that. Variant being that if I can categorize numbers into buckets where I know the buckets are sorted in some fashion, then the sorting problem becomes easier for me. Radix sort is exactly bucket sort. For example, hypothetically, let's say you had a lot of numbers. So let's say I had 456, 923, let's say I had 150, let's say I had 268, and let's say I had 12. And maybe I also have 950. Now imagine I was to create 10 buckets. Bucket 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is for the most significant digit of the number. Let's say the 100th place of the number, assuming that all of the numbers are smaller than 1000. They can be 1 million, 10 million as well. So then we'll choose the most significant bit and we'll keep it the same position for all numbers. If I do that, then I know that 423 will go in the fourth bucket. Most significant digit is 4. Most significant digit here. Assuming for all of them, the most significant digit that we're looking at is the third digit from the back. So 923 will go in the 9 bucket. 150 will go in the 1 bucket. 268 will go in the 2 bucket. 012 will go in 0 bucket. 950 will go in the 9 bucket. What I know is now if I start going bucket by bucket and I have sorted the numbers within a bucket, and if I just start picking numbers from here and appending them, then I end up getting the entire array sorted. Why? Because I definitely know that any number that is starting with 0 is definitely going to be smaller than any number starting with 1. So dividing them into buckets and then sorting the buckets within themselves, sorting the numbers within a single bucket, that helps me reduce the complexity to some extent. And I'll show you an example of that to a major degree, which is what is called as Radix sort. But the idea is if I can break them into buckets where buckets already have some ordering defined, then my job becomes just simply appending the numbers in the buckets, and that might give me a sorted array. And I'll give you a few examples to sort of talk about what bucket sorting is. And we'll do one problem on bucket sorting as well, which is a hard problem, but we'll do that. What kind of data structure can I use for buckets? Think of them as, for example, vector of int. So for example, your v of 0 is a vector of numbers. V of 1 is also a vector of numbers, and then so forth. So the concept of bucket sort is very simple. If you can split numbers into buckets where buckets themselves are ordered in some fashion, then I can sort numbers within the buckets and then I merge them. That gives me a sorted answer. If numbers are not on the same order, how do we put them in bucket? So even here, if you see like 12 was not of the same order, I just added another 0 to get it to the same order. So imagine I have numbers as 950, 1, 12, 923, 256. I'll just add 0 to make sure they're all of same length. How do we keep the value sorted in one bucket? Within the bucket, just use quick sort or whatever kind of sorting you want to use there. Insertion sort, quick sort, whatever you want to use. Let's take an example. Bucket sort alone isn't enough. Bucket sort paired up with a few observations is actually very powerful. So one observation that leads to sorting algorithm is called Radix sort. The way Radix sort works, imagine again you have a bunch of numbers to sort, right? Again, I'll pick the same thing, which is, let's say I have 923, 950. Let's say I have 12. Let's say I have the number 1. Let's say I have number 100. Let's say I have 150. Let's say I have 650 and 688. Hypothetically, let's say I have a bunch of these numbers. So what Radix sort says is, look, I mean, at the end, if I was at the end, let's make all of these guys equal length. So add zeros wherever applicable. If all of these numbers are of equal length, then at the end, most significant bit, this bit, is the most important bit. Obviously, if the most significant bit of one number is smaller than the other number, then the overall number is definitely smaller. It is only a problem when they both are equal. Then I will look at other digits. So I know that. So what I want to do is I want to start sorting digit by digit, with most significant digit being the last place where I sort, because I know this is the final step. So what Radix sort does is it says, let's start with the least significant digit. Let's first sort based on this. And what do? I basically create, again, 10 buckets corresponding to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I will first look at the last digit. Based on that, 923 goes here, 950 goes to 0, 012 goes to 2, 001 goes here, 100 goes to 0, 150 goes to 0, 650 also goes to 0, 688 goes here. And then I append these guys, right? What will happen once I have done this step? All of the numbers will be sorted by their last digit. So I get 950, 100, 150, 650, 001, 012, 923, and 688. I've sorted numbers based on their last digit. Now let's look at the next digit. I repeat the same process again, but with the next digit now. I'm going to erase all of these guys from here. We are now going to look at the second digit. I say that now let's look at these numbers again, one by one. But the second digit is what we are looking at. So 950 goes at 5. 100 goes at 0. 150 goes again at 5. 650 also goes at 5. 001 goes at 0. 012 goes at 1. 923 goes to 2. And 688 goes to 8. I'll again append these guys. What this would make sure is now everything is sorted based on the last two digits. So I append, and when I append, I basically get 100, 001, 012, 923, 950, 150, 650, and 688. And now the last step is the magic step, which is where I look at the most significant bit. So I erase all of this again. I look at the most significant bit and I bucketize these guys based on the most significant bit. So 100 comes here, 001 comes here, 012 comes here, 923, 950, 150, 650, and 688. Now once I append them, all of the numbers should be sorted, which you would see 001, 012, 100, 150, 650, 688, 923, 950. Now this final array that we have gotten, this is sorted. What has happened? We can take MSB directly. The only problem is then within the bucket, if you have multiple numbers, and think of like when you have a million numbers, right? You only have 10 buckets based on MSB. That means every bucket on average will have 100,000 numbers. And if you go to solve or sort of sort each of those buckets separately, it will take you a lot of time. But here, I can sort the entire array by doing this function, the number of digits, number of times. So imagine all of the numbers had 5 digits. I'll do this operation 5 number of times and my entire array would be sorted. For every single digit, I am putting them in buckets, 10 buckets, and then I'm appending them, which is an order n operation, right? So my total amount of time taken is order n into max number of digits. Space is assuming that we are taking a vector of vector. The total space taken by vector of vector combined across all of this is order of n. So I'm using an order on n extra space. Actually, order of 10 plus n, which is order n. Do we need to compare an element with the existing elements present in the bracket? No. Right now, because the moment you start doing that, then your complexity increases. Currently, it is just very dumb way of appending to existing numbers in the bucket. Why can't we take MSB to LSB? I mean, when we start with MSB, in the first step, we would definitely have put the bigger numbers to the first half of the array, the smaller numbers to the second half of the array. That I completely agree with. In fact, numbers would be sorted based on their first digit. But as you go to the second digit, within these numbers, if the sorting is happening in the right way or not, because you'll have, let's say you look at second digit as 0, right? Now, some of those 0 numbers will come from the numbers that had the first digit as 9. Some of those 0 numbers will come with some numbers where the first digit was 6. For example, let's look at this example itself, right? If I started from MSB, then what would have happened? Let me erase this. My first 2 numbers will go in the 9 bucket, 923, 950, 012, 001, 100, 150, 650, and 688, which is great. Now, if I append them, then I get this, which is almost sorted. The problem is when I move to the next digit, it's then that it becomes a problem, because 012 will come here, 001 will come here. Now 100 will also come here. However, I know that 100 should only come after 012. When I'll merge, then I wouldn't know how to maintain this ordering. I mean, I'm using digits here. You can do the same thing for bits. There you will only have 2 buckets, 0 and 1. Here I have 10 buckets. You'll only have 2 buckets when you're dealing with bits. When you go from LSB to MSB, that means MSB takes higher priority because it is the last deciding factor. When you go from MSB to LSB, then LSB starts taking higher priority. So time complexity is n into number of digits. If d is the number of digits, that is your time complexity. Usually, the number of digits is the same order as log n. It's actually log n to the base 10, n being the maximum number in the array. Number in array. So, I mean, usually Radix sort is good number to know and good approach to know because this can be applied at multiple places. That being said, again, like not very commonly used because n log n, you can just directly use your sort function. Why would you go and take the pain of implementing Radix sort when it has very similar time complexity? If all of what we have discussed till now, if that makes sense, I'll give you one problem which will actually make the bucket sort even clearer. The reason why we have bucket sort. Explain the time complexity again. So if you look here, what are we doing? We are taking digit by digit, right? So first we look at the last digit. And for that digit, what do? We put them in these 10 buckets, right? So basically what happens is, what is the last digit of any number? Let's say I do this, right? I say I goes from 0 to n and we calculate the last digit. Digit is equal to array of I mod 10. That is your last digit. And then you put it in the same bucket. So for example, let's say if you have bucket array, it's a bucket of digit dot add AI, right? You do that. All of this is order n process for the last digit, correct? And then eventually I'll basically look at numbers in every bucket and I'll keep appending them in another array. All of this is order n process. I'll have to do this for every digit, correct? So if all numbers have, let's say 5 digits, then my complexity would be n into 5 because for every digit, I'll do an order n operation. If every number has d digit, then it becomes order of n into d. How n log n is similar to n into d. So n into d makes sense, right? Order of the algorithm is n into d. That makes sense. Correct. Okay. Now what is d? What is given a number x, what is the number of digits that x would have? How do you find that? Basically, how do you find number of digits? You basically divide x by 10. You check if it is 0 yet. Then you again divide it by 10 further, which is 10 power 2. Then you divide x by 10 power 3, x by 10 power 4, 10 power 5, and so forth, right? When x by 10 to the power I is 0, which is like now 10 power I has become bigger, then that is where you have the number of digits, okay? If I just put it like this, I mean, basically, if x has I digits, then x is approximately equal to 10 raised per I. Approximately, which means if I take log 10 on both sides, then I basically get I is equal to log of x. That you agree? So if there is a number x, then x has basically log base 10 x number of digits. So therefore I'd say like whatever is the highest number in the array, then d is basically log of that highest number. So your d is almost the same as n log x, x being the highest number. So bucket sort is more generic. Right? Like bucket sort just says, hey, look, my fundamental is you can create any sort of bucket you want. You can create a bucket of all numbers from 1 to 100, all numbers from 100 to 1000, all numbers from 2000 to 3000. You could create any bucket that you want as long as it covers all range. You put numbers in the bucket where you know that every number in bucket 1 is going to be smaller than every number in bucket 2. So you just bucketize these numbers you sort them separately, and then you append. That becomes bucket sort. It is very generic. Radix sort is using bucket sort in one way. Why this type of bucketing works? Going for all positions instead of just MSB or LSB. Let's say if you just go for MSB, there wherever two numbers have different MSB, most significant digit, there, I mean, you probably can only do with most significant digit. The problem is there will be a few numbers that will have the same most significant digit. In fact, there are only 10 possible most significant digit, right? So if you have, let's say, 1,000 numbers, then on average, you'll have 100 numbers in every bucket, right? For example, here as well, I had 950 and 923. They'll all go to the 9 bucket. Now, how to actually decide the ordering between these? In fact, if you have a lot of numbers in the bucket, then how do you figure out the ordering between those? That is not clear. So therefore, you can't decide only based on most significant digit. You'll need to somehow sort these guys within the who have the most significant bit as 9 as well, right? Internally, you'll need to sort them. So there are two ways. One is like you just say, I'll bucketize based on the most significant digit and I will sort each bucket, right? So what happens is if I had n numbers, then on average, each of the buckets will have n by 10 numbers. To sort them, I'll take n by 10 log n by 10 and I'll have 10 such buckets. So I'll finally multiply by 10. This will give me n log n by 10, which is the same as n log n. So I end up reaching the same algorithm which I have anyhow done before. This does not seem to be an improvement. So therefore I said, like, can I improve further on it? And there we said, maybe if instead of saying that we'll sort the numbers in the same bucket, if we could do bucket sort multiple times in a way where at the end of it, all of them would have been sorted, then that would be nice. So I say, you know what, like for the sorting based on the most significant bit, one thing is if I can somehow reach a state where numbers with the same most significant bit, they are already sorted in some way, that would be awesome. But to sort the numbers with the same most significant bit, for example, if you remove the most significant bit, you'll need to sort them by the remaining bits. There also, if you just again break it down recursively, you'll reach the same state. Like you'll first have to sort based on the least significant bit, then the least significant and most significant together, and then the last 3 together, last 4 together, and so forth. In Radix, you have log base 10 of not the number of elements. I mean, so in n log n is number of elements. This is log base 10 x, which is the highest element in the array. This is not the number of elements. This is highest element in array. Two different things. But yeah, I mean, in cases of log n, if you have, let's say, 1 million entries, 10 power 6 entries or 10 power 7 entries, the log n is typically 20, 22, 24. In the case of numbers, the number of digit is probably still 8 or 9. So it can perform twice as faster. If max is less than n, go for Radix sort. That I wouldn't say. If your log of 10 max is less than, in fact, significantly less than log n, then go for Radix sort. Okay. In case of integer, we could use Radix. That's why I said, like, if your log of max is less than log of n, you could use Radix. That might run just slightly faster. Even if you go with bits, yes, you will eventually end up sorting. Just that the number of iterations will be more. All right, let's move to the next problem. Imagine you're given a bunch of numbers, which are not sorted, by the way. So let's say you have 5, 8, 3, 1, 6, some numbers, right? And you've been given this array that you cannot modify. So this is a constant array. Cannot be modified. Now what you need is that if this array was sorted, let's say if this array was sorted, the numbers would be 1, 3, 5, 6, 8. Actually, let me change the numbers a little bit. Let's say this number was 7, right? If this number was 7, then the numbers would be 1, 3, 6, 7, 8. And then in the sorted array, if you were to look at adjacent difference, the difference here is 2, difference here is 3, difference here is 1, and difference here is 1. There you have to find out what is the maximum gap between the numbers when the array is sorted. In this case, the maximum gap is 3. So you say the answer is 3. So given an array, how do you find this maximum gap if the given array is constant? And obviously, like, one answer is you make a copy of this array, you sort the array, and you look at the adjacent differences and you take the maximum of that, which becomes time complexity order of n log n, space complexity order of n. Can you do something better than this? I'll repeat the question once more. You're given an unsorted array. The array is not sorted. What you have to find is if the array was sorted, and if you looked at the adjacent numbers differences, what is the maximum difference you can find? What is the max gap you can find?
So let's get started with our today's lecture on linked list. Linked list is also a very important topic from the interview point of view. So to get comfortable with linked list, you have to attempt multiple questions because it's tricky to deal with all the pointers. Sometimes it's confusing, but once you start with it and you practice with it, it's great. Okay, you will get comfortable. So let's get started. Now, why linked list? Why have we come to linked list? So it's like we started with arrays. Let's talk about arrays. So why not we continue with arrays? So the problem with arrays was that its size is fixed, right? Size fixed, that's a problem. So if I want to insert more elements, I have to create a new array with a greater size. So that's problematic, right? What else can I do? I can basically create a dynamic array instead of that. A dynamic array, right? So in dynamic array, what happens? So if I have an array of size, let's suppose 5, now all of this is filled. And if I want to enter one more element, what happens is an array gets created double the size of this array. So an array of size 10 will get created and all of this will get copied into this newly created array, and then we can insert the element that we would want to insert, right? Now the problem with this is that, let's suppose now I don't want to enter any more elements, so this space will get wasted, right? This space will get wasted, and that's a problem, right? Wastage of space is also one of the major problems. So now we cannot do anything. The dynamic array will anyway get twice the bigger of the previous array. So that's a problem with dynamic array. So here comes the linked list now. Here comes the linked list. Okay. In linked list, what happens is we don't have to reserve any space. Okay. We don't have to reserve any space. Rather, so what happens? Let's see the logical view. So this is I am taking as the memory. These are the memory cells. Okay. So you will agree with me that in array, the elements are stored in contiguous blocks of memory, right? Elements are stored in contiguous blocks of memory. So now in case of a linked list, this is not the case. This is not the case. If let's suppose one element is stored over here, another can be stored over here. The next could have been here. Then the next could have been here. So now if I want to connect to one node with the other node, so how to do that? So for that case, the structure of linked list looks like this, that we have a data part and we have an address part. Okay. So this address part will help us to connect one node with the other node. Okay. One node with the other node. So let's look at its structure. So here I have this node, let's say the data is 5. Then I have this node, let's say the data is 3. Then I have this node, the data is, let's suppose, -2. Then I have this node, let's suppose the data is 1. So I can connect this address part of this node with the next node. Then the address part of this node with the next node. Likewise over here, and this is empty because no node is after this. Now in a linked list, so basically I want a point from where I can, start. So basically I need something to, traverse the linked list or at least have the linked list. So in that case, we should have the pointer to this very first node. Okay. So that's pointed out by head. We can have a head pointer which can store the address of the very first node. Let's suppose its address is 100. Then the address of this node is 250. Let's say it's lying at 300. Let's say it's at 500. So head will store the address of 100. And what do we mean by pointing this pointer out? It means that here the address is stored like 250. Then here, so basically it's like we have address 250 over here. Then we have 300 over here. Then we are storing 500 over here, and there it's nothing, empty. So this was pretty basic about linked list. Now let us see how can we declare a linked list. So in C++, we can use a structure or a class as well. So a structure can be defined as struct, then node, then so we have this data field as well as this address field. So let's suppose I want to store integer type. So I'm declaring it as int, then int data. Then we have, so we will also have a pointer, that is this next pointer, right? So that's how I can declare structure of the linked list like this. And in Java, how can I do that? So I can have a class. Let's say the class name is node, then int val, node next. Okay, so that's how we can do that. So now linked list is a linear data structure. Linked list is a linear data structure. That means we can only traverse the linked list in this fashion. We cannot go to any node from in between. Okay, is it clear that why a linked list is known as a linear data structure? By this we mean that next is a pointer of type struct node, because this pointer is going to point to a node, right, of type this. Therefore the type of this pointer is struct node. So that's how the structure of this the data, that's how the structure of the node look like. Okay, the first entry is of data and the second is of next pointer that points to the next node of the list. Okay, cool. Now let's talk about the advantages and disadvantages of using linked list. So the advantage of linked list is that it has a dynamic size, isn't it? Dynamic size. So if I want to insert a node, I can simply create it and attach to this node, right? Attach to the last node of the linked list like this, right? So it has a dynamic size. Then second point is that there is an ease of insertion and deletion. So if I talk about an arrays, if let's suppose I want to delete an element from here, then all of these elements I have to shift one step left, isn't it? I have to shift them one step left. So that's an extra overhead. So in linked list, we don't have to do any such thing. We just have to manipulate the pointers. We will come to that part. We will see that dry run in a while. Okay, so now let's talk about disadvantages. So first disadvantage is that there is no random access. I cannot access any node from in between. Okay, any node from in between. The second disadvantage is that we need extra memory for pointers. So whenever you already know the size of your data, you already know, okay, I am going to store 10 elements and that's all I need, always go for arrays. But if you are not sure that how many elements you are going to store, how much data you have, so go for linked list. The third point is that linked lists are not cache friendly. Okay, linked lists are not cache friendly. I would suggest that give it a read. And this is basically quite a big disadvantage of using linked list, due to which we prefer arrays. Okay, due to which we prefer arrays. Okay, now let's talk about that. How can we, insert, print, delete a node in the linked list? So let's come to a little bit of code part. So as I told you that this is how in C++ we can make a structure of the linked list. Right, let's make functions. Let's say, so void insert, that I would want to insert the node in the linked list. So I'm making this function. Then also let's make another function, void print. So how to insert a node in a linked list? So for that, first of all, we should have a global head pointer. Okay, we should have a head pointer. So let me create that. So we just need to write this for that. Now, what do we have to do? So for inserting a node, first we have to create a node of type this. So how to do that? We will write node star temp is equal to new node, and then we have to set this data part. So temp data is equal to x, okay, this x, whatever the user has supplied. Then also they have to set this next pointer. So temp ka next is equal to what? Let's set it for now as null. Okay, let's set it for now as null. Now what do? We have to check if if let's suppose head is pointing to a null, so head is null, okay, it's pointing to nothing. So if head is null, let it be like that. If head is not null, this is the case when there already exists a node. Head is pointing to this node. So now what we'll do, if head is not null, we will set temp ka next is equal to head, right? So we have created a new node. This is our temp node. Let's say the data is 5 over here. So what we are doing, we are setting it next to the head node because head is pointing to this right now. Okay, and we also have to set head to the new head. So head is equal to temp. So basically now head will start pointing over this node. So this is how it will look like now. 5, then 4 is there, and head is pointing to this node. So this is the case when head is not null. But if head is null, so in that case, we will set head is equal to temp directly, right? So now there's this thing that since this is getting repeated in both the cases, so what we can do, we can simply remove this from here, and this is how our final code looks. Okay, so this is how we can insert a node in a linked list. Now if suppose I want to insert one more node, I can create it. Okay, I can create it. Let this be temp. So the data is 1. Now I will set it next to head, current head, and then I will set head to this newly created node. So this is how it will look like. That we have this 1, then we have 5, then we have 4, and head is pointing to here now. So I am inserting at head. So this function is for insertion at head. Okay, this function is for insertion at head. So if you have got the logic of this, that how you are manipulating the pointers, you can very well insert any node, let's say at end or in between as well. So if you, let's say, want to insert a node at end, you can go till end. And so basically this is, let's suppose, your linked list, and you want to insert a node. At end. So you can set a temp pointer over here and iterate the linked list till the next of a node is not null. So here, as you can see, the next of a node is null. So we will stop over here. Now we will make this point to the new node. Does that make sense? That how we can insert a node at end? Likewise, you can insert a node at, so how can you insert a node at somewhere, let's say at position 3rd. So this is a linked list, and you want to insert a node at, let's suppose, this position. So this is a new node that you want to insert over here. What you will do, you will start traversing from here. You will go, so k is equal to 3, that means you want to insert a node at 3rd position. You will go till 2nd position and you will manipulate the pointers. Okay, so you are over here, then you move to the next element, and now you are at k minus 2 position. So you will simply stop. What you will do, you will make this point over this. So this will point to this now, and this will point to this now. So this link will break. Does that make sense? That how we can insert a node at any position in between? So now let's talk about that how to implement this print function. So what we'll do, we will create a temporary node. So as to iterate the entire linked list. We will set this to head. We will set this to head. Okay, now we will simply iterate the linked list like this. So while this temp is not equal to null, we can simply see out the data. We can simply print the data of this temp node. We can print the data of this temp node and make the temp point to the next of temp. Okay, next of temp. And this will go on and print the entire linked list. So temp will simply start from the beginning, and so temp is here first, let's suppose. So it will print its data, then it will move forward, it will print its data, then it will move forward, it will print its data, then it will move forward. And now you can see that we will simply come out of this while loop because now the temp is null. Okay, language should not be a constraint. You should get the logic. Okay, you should get the logic that how we are doing it. That's why I'm also taking examples that how pointers will be moved. So don't really go with the language. You can check that how these things are implemented in Java. But here, please try to understand the logic. Okay. Okay, now what do we do? So here is our main function. So I can simply call insert x, insert let's say 5, then I call insert let's say 4, then insert -1, then print. So this all will do the trick, right? Now all these functions can be called and our linked list will look like this. So since we are inserting at the head, so this will be 5, then this will be 4, then here we will have -1 and likewise. Okay, so guys, now let's do the final, this delete function. So let me write a pseudo code of it. Okay, I am not writing the C code for that because that's creating confusion. Let me write simple pseudo code of it. So we have this delete function. Okay, and it's taking the head. Okay, so head is already declared as a global variable, so we need not do that, right? We need not do that. So what we can do for deleting an element, we can create a node of type, whatever class or structure you are declaring. So we can set this node and make it point to head. Okay. So basically, you can see it in this diagram that how we are going to delete a head. So we will mark. So this is head. Temp is also pointing over here. So basically, we can do head is equal to head ka next. So head will come over here and then we can free this temp. So basically we will do head is equal to head ka next and free temp. Does that make sense? Okay, so now let's quickly move on to the questions. Let's do the questions now. Okay, I would like to discuss some conditions where, you know, even if people very well know linked list, but sometimes they fail at implementing it. Okay, so the manipulation of the pointers and, you know, while handling the linked list, it becomes tricky. So therefore, a lot of coders stumbles on that. So let us see what we can do about it. So some conditions are there that we can definitely check after writing our code, that the head, so we should check if head is null or not. Okay, as in we should check if that have we handled the case when head is null. Okay, so don't worry, as you will proceed through the questions, you will get clear of these things as well. Okay, then you should definitely check your code for a single node. What if only a single node is present in the linked list? Then you should definitely check for 2-3 nodes. Okay, so let's say only 2-3 nodes are present in your linked list. You should check if your code is working fine in that case or not. And always try to think aloud. Like, that's the suggestion for all the questions that you attempt. Think aloud, write on pen and paper, and think about all the edge cases that can be handled or that needs to be handled. So that will help you a lot. Okay, now let's discuss some questions. So here we are discussing some questions. Now we discussed about printing a linked list from the very start till the very end in iterative manner, right? In iterative manner. This is an iterative manner, isn't it? Can we do it using recursion? So basically, let's say, so this is our print function. This is our head pointer. Now, what we can do, as you can see over here, this is a linked list and I want to print it using recursion. So basically, I can simply print the data of this node, and now with all the rest of the nodes, I just have to do the same thing with them. So why not using the same function for them? So what I can do is I can simply print the data of this head node. So then what I can do, I can simply call this function again with the next node as the head node. So print func. Now I am basically calling the head dot next. So this is this dot representation, then this arrow representation. It's how you reference, it's how you refer to these variables. So in Java, you use this dot. So basically for in classes while you implement it, you basically use this dot, and like in structures I told you, you use this arrow function, okay? So will this do the trick? Is it sufficient? Is it sufficient, or are we missing something out? So if your head is equal to null, then you simply have to return, right? You cannot do anything about that. So simply return from there. This is the base condition. So let me actually first state the question. The next question is that you have to print the linked list in reverse order. So this is your linked list. This is your head pointer. Now you have to print it like this, 2, 1, 6, 4. How can you do it? Do you have to go at the end or something? Is it like that? Or like, can you do something about it in a better way? So you can have a stack. Okay. So basically you can put this node into this stack, or you can also simply put the data of this node onto the stack. So you can have a stack like this, stack in S. Then you can traverse the this linked list using a temporary pointer, let's say T. So you are here, you put this data onto this stack. Then you move ahead, put this data on top of stack, put this data on top of stack, put this data on top of stack, and now the linked list is empty. So you can simply pop everything off, right? So you'll get 2, 1, 6, 4. Simple, right? What's the time complexity of this? It's just order of n, and the space complexity is also order of n, right? It's also order of n. So you can also do this using recursion, right? So as you see over here, most people have pointed out as well that we can simply reverse their order, and that will do the trick. That now I don't have to print this node immediately. I have to go till the last and then start printing. Okay, and then start printing. So what I can do? So basically, let me simply copy this. So what I can do? I can simply bring this over here. What's the time complexity of this approach? Again, it's order of n, and the space complexity is order of n as well, because here also we will be using the call stack. Recursion uses stack. So that's ideally what we are doing here as well. So both are same basically, right? The next question is to print kth node. So what you need to do? Again, so as I told you before, that you just need to go till the, so just go till kth node and print it. That's it, right? And print it. So it's pretty simple. Let's move forward. Okay, let's move forward. Now let's say I ask you to print the kth node, from end. So what we can do, we can actually see that what's this kth node from start. So we have this node. Let's say I want to delete this third node. Okay, I want to delete this third node from end. So what's the value of this? What's this node from very start? It's nothing but n minus k. This will give us these rest of the nodes, right? This will give us these rest of the nodes, and plus 1 will give us this node. So that is, from start it's nothing but 4th node. But to delete it, you will have to reach till this node so that you can connect this pointer over here and remove this. Does that make sense? So you can, if you simply have to print it, you can simply go till this position. But if you, let's say, have to delete it, so you have to go till k minus 1th position and connect this. Okay, so let's find the middle of the linked list now. Middle of the linked list. These are the basic questions, and if you get hold of them, you'll get pretty comfortable with linked list. So try attempting them on your own, okay? Okay, how to find the middle element of the linked list? Okay, first, the basic approach we can use is that we can find the number of nodes in the linked list and simply do the count by 2. So we can traverse till count by 2 and return the node. Does that make sense? That's how we can do it. And the second is, let's see. So we have this head pointer, then we have this mid node, and we have this end. Okay. Let's say I have 2 pointers. So this is a slow pointer and this is a fast pointer. This is moving with the speed of 2 twice, so 2 into x, and this is moving with the speed of just x. So if with this pointer, if with this fast pointer starting from the very head, I reach till end, then this pointer will reach where? Remember that it's twice the speed of this pointer. So if I am reaching with this pointer till the very end, this pointer will reach over this place and we will find the mid. Does that make sense, that why the slow and fast pointer work? So let's quickly write the code for it. So mid of linked list. So we have this head. We will set slow pointer to head. We will set fast pointer to head. Then I'll come to these conditions in afterwards. Let's write this, that the fast pointer, you know that it will go 2 steps forward. So next ka next, and slow pointer will go only 1 step forward. So slow ka next. Then after coming out of this while loop, we can simply return slow ka data, let's say. So in this condition, this fast pointer is reaching till end. So we will be moving till fast is not equal to null. But this is incomplete. This is incomplete because here we are jumping 2 steps forward. So we have to make sure this exists. This node exists. So we have to check if fast ka next is also not null. Okay. So what's the time complexity of this? So time complexity is just order of n and space complexity is just order of 1. Now let's talk about another question, which is to reverse the linked list. So how to reverse the linked list? So we can use stack. So like I'm not going into depth of it. Let's say the nodes are 1, 2, 3, 4. Now you can basically make a stack like this, stack of node pointers. Okay, stack of node pointers. Now you have to, return what? You have to return this 4, then 3, then 2, then 1. You actually have to reverse the entire linked list. Okay. So you have to take node pointers so that you can push them. So you keep pushing them. This is 1, then 2, then 3, then 4. Now you can simply connect them. Now you can simply remove them one by one and simply connect them. Okay, so this is one way. The time complexity of this approach is order of n and space is order of n as well. Now how can we do it using recursion? We can do it using recursion, right? In which it will look like this. So we will have a function reverse, then head, then we will call, so we have to reverse it, right? So we will call itself with the next node. Now here we will perform some operations, and here we have to write the base case. Let's see what to do about that. What are the operations first of all? So we have this operation to perform. Now what do we need? So let's see it over here. This is 1, 2, 3, 4. So I am here, this is my head, and if I'm back to here after recursing, that means this is done, they all are reversed, and I am back to this after recursion. Now what do I need to do? I have to set 2 next to 1, isn't it? So in place of 2, can I write head next, and in place of 1, can I simply write head? Will this be the case after returning from recursion? So I can simply write it over here that head ka, so you can write head ka next is equal to head. And then also what you need to do, you have to make this null. You can make this null. So head ka next is equal to null. But this isn't over, right? So we have something like this now. So, but we also need the head of this. Now this is the head basically. So this will actually return us that. So what we can write over here, let's call it last is equal to. So this function will return us that. I will come to that. I will show you the dry run of this. So we will simply return last at the end. But first let us talk about the base case. So do you guys agree that first we have to check the condition for null? So if head is equal to null, and also if there is one node, so we don't have to do anything. So if head ka next is null, in that case we can simply return head, isn't it? Return head. So this is it. That's all the code. Now let us look through the dry run. So recursion uses stack. So here I have that, and I am using 2 variables, that is head and last. So I'll maintain them. Now first, so this is my linked list. So I am here right now. So head is at 1, and so last is what? Whatever we will get from here. So Abhi, right now I don't have anything. Okay, right now I don't have anything. So I have called this function. Now basically this is my head. So next head is equal to 2, and last is still nothing, because again we are calling this reverse function. Okay? So since we are calling it, now head becomes this. So next head is equal to 3, and last is still nothing. Then moving ahead, head is equal to 4, and last is nothing. But here, as you can see, we will actually not go over here, since there is only, you can see that head is not null, but head ka next is null. That means we don't have to go over here. We can simply return the head. So now this will return, and what's the head at this? It's 4. So 4 will get returned. Okay, 4 will get returned. Now basically we are returned from this. Now we are back at 3 as the head. So answer to 3 has been returned, right? So once we have returned from here, now we will do this. So head ka next. Head is at 3. So we will set this basically. Head ka next is this. So we will set this over here. And we will make head ka next as null. Now we will get back from this, and 3 will, so again last from here is, it's 4 only. Now again we will do head ka next, that is 3 ka next point to head. Okay, and head ka next is null. So now we are done with both of them. Basically, we are done with both of them. So 4 will basically return, so this will basically return 4 over here, and this is also gone. Now we are back at 1, and we will make head connects point to it, point to head, and we will mark head connects as null. So what do we have? This is also done. So last has had what? Last had 4, this node as the new head. Does that make sense, guys? Let me again do it quickly, okay? Let me go through it quickly. So this is my linked list. My head is here, okay? Head is here. So I am at this if condition and my head is not null. Also, the head connects is also not null. So I will not go into this if block. I am here. So I am calling this reverse head again. This should be head connects. And now basically I am calling reverse and passing 2 in that. Okay? So I have to store this on stack. So head is equal to 1 and last is equal to whatever this will give me as the answer. Okay? Now so now basically I am here. Now head is not null and also head connects is not null. So we will go to this block. Now here head is equal to 2. Last is I don't know, right? Last I don't know. So basically we are calling reverse head connects, that is 3. We are calling this and we are on this now. So head is equal to 3. Last is equal to, we don't know, because now whatever we'll get from reverse of head connects, that is 4, will be coming over here. So we are calling head connects, that is 4. So head connects is 4 now. We are over here. Now as you see that last is not null, but head connects is null. It's null. So we will simply return this head. What is head? Head is 4. Return 4. Where to return it? Where are we returning it? We are returning to this last variable. So here will come the 4. Okay, here will come 4. This is done. We are done with that. So basically this we are done. Now we are back from recursion at this place. Okay. So since we are back, now it has this value of last. It will return this value over here. Okay. Now this is also done. But before that, also what it will do, it will set this. That is head connects will point over here and head ka next will become null. Now we are done with this and back over here. Now we have got the answer for last. Okay, over here. First of all, what we'll do, we will set head connects over here, right over here, and we will make head connects as null. So this will return 4 over here and this is also done. This is also done. Now we are back from recursion over here. We will set head connects, that is 2 connects to 1 and mark head connects as null. So we are back from here as well. So this will return 4 to us. So in last variable what we'll have? Finally in last variable what we'll have? So we will have the address of this node, the head node now. Okay, we will have the address of this head node now. Okay. The time complexity of this approach is order of n and the space complexity is order of n. Can we do it in order of n time and space as order of 1? Using pointers, okay, using pointers approach, iterative approach. So we have these nodes. Let's see the intuition first. Let's suppose I am at this node. Now what I can do? I can break this link and make this point over here. But now I will lose the connection from here. So I need 2 pointers at least. So that is 2 here and here. But I'll also need a third pointer that is over here, because this is a one-way linked list, right? How will I set this to this node? There is no way. So I need 3 pointers over here. So let this be current, next, and previous. So let's see a dry run of that. Let's see how we can do this. So initially, previous and next can be null. Both previous and next are null. Initially, they are empty. And current can be set to this node. Then we can set. So if current is not empty, if current connects is not empty, so we can set this next node over this node, so that we do not lose this contact. Now, since we have set this up, we can set this link to here. Now what we need to do? Now this is actually previous will now move here. Current will move to next. Okay? Current will move to next. Basically got this link. Now current connects is not null. Therefore, next will now come over here. And we will set current connects as point 2. This link was set up. This link was not set up yet. Okay? This link was set up. And now we will set current connects to over here. Okay? Now we will set current connects to over here. Then again, previous will come over here and current will come over here. Now again, current connects is not null. So we will set next pointer over here and current connects as over previous. Okay? Now again, what do we need to do? Set previous over here, current over here. Now current connects is not null. So we will set next over here so that we don't lose the next node. So we are setting this. Now make current connect point over here. Now previous will come over here. Next will current will come over here. Now current connects is null, right? It's null. We will be checking that current is not null. Okay. So since current is not null, so we will set the next over here, and mark current connects as over here. And then just like that, previous will come over here, current will come over here. And now current is null. So we don't have anything to, we don't have any node now. So this previous node is our head now. This is our head. Is the intuition clear that why we are doing this? Let's quickly write the pseudocode now. So you will set current to head and previous next will be null. Then while current is not equal to null, what we did? Next will go to current connects. Current connects will go to previous. Previous will become current and current will become next. Finally, we can simply return previous as the head pointer. So the time complexity of this approach is nothing but order of n and spaces order of 1, right? So this is reversing a linked list is a very important problem in the interview. With stacks, it's easy, right? With stacks is easy, but with these pointers approach, and here we have a recursive approach, it's little tricky to understand. Okay, this was it, guys, from my side for today. I hope you guys attempt the questions provided in today's contest. So thank you very much.
So we will start with the very first bucket. So what I have decided that from each bucket, I will be doing one question. Okay. Let us do the very first question from each of the buckets. Okay. Let us start with the palindrome list. So the question says that we are given a singly linked list and we have to determine if it is a palindrome or not. If it is a palindrome, return 1, or basically if you do Boolean, it is true for 1. And if it is not a palindrome, we return a 0. So I mean, like in Boolean, false represents 0 and true represents 1. So basically we have to return true or false if we talk in parallel sense of a Boolean variable rather than an integer. Okay. And the solution that is expected is linear in time and constant in space. Okay. Let us assume that, hey, this time we are given a linked list. Okay. So suppose you were given an array 1, 2, 3, 4, 3, 2, 1. This is a palindrome, right? How can we find if it is a palindrome? We can start a pointer from the left side and similarly a pointer from the right side going towards left and a pointer from left side going towards right. At each index, we check. So for example, at the very first stage, left will be this, wait a moment, and right will be this. Is the pointer at left equals to the pointer at right? Yes, it is equal. So now that means it satisfies the property. We increment left and we decrement r. Is the new left and right equal? Yes, they also are equal. So we again increment L and we again decrement R. They are also equal. Then we increment L and we decrement R. This time L will be equal to R. So I mean, like L and R both will be together. Okay. So at this stage we can stop because this is a central point. Okay. So if it had been an array, we could have done something like this. Int L equals to 0 and R equals to n minus 1 while L less than R. If AL not equal to AR, return false. Else we do plus plus L minus minus R. And when we are out of the loop, we can just return true. That means that the array was sorted. But this thing doesn't work well for a linked list. Why doesn't this work well for a linked list? Because in a linked list, we don't have random access. We can't directly access this number and this number. Similarly, a singly linked list doesn't allow you to go backward side. It only allows you to go the next side. Okay, so this is why we can't use exact same approach for the linked list. Okay, but now let us see this. Let us say this was a linked list. Okay, also reverse this linked list. What will happen if we reverse this linked list as well? Then the reverse of this linked list will also be 1, 2, 3, 4, 3, 2, 1, right? So we can see that for a palindrome, the linked list and the reverse of the linked list is equal. Okay, so I mean, like if we are somehow able to reverse a linked list, we can find if a linked list is palindrome or not. Okay, now the question comes, how will we reverse a linked list? Okay, let us see how we can reverse a linked list. Okay, so linked list is something like this. 1 is pointing to 2, 2 is pointing to 3, 3 is pointing to 4, which is pointing to 3, which is pointing to 2, and finally this is pointing to 1. Okay, now suppose at every iteration we are maintaining 3 pointers. This is the previous pointer. Wait a moment. This is the previous pointer. This is the now pointer, and this is the next pointer. Now, what we see that in the reverse of the linked list, now next will be what was previous element and next. So basically now next will be the previous element. Okay. Okay. Now let us do exact same thing. Let us try to use this approach to reverse the linked list. Okay. So now if we somehow are able to reverse the linked list, and how to reverse the linked list we already know, then we will be able to, then we will be able to find if a linked list is palindrome or not. Okay. Now, from what index should we reverse? Actually, we should reverse only this part of the linked list, right? Because if we reverse this part of the linked list, this will change to 1, 2, 3, and whatever that comes after this doesn't matter to us. We will keep on comparing each element. So 1 is equal to 1, okay, 2 is equal to 2, and 3 is equal to 3, and we are done, okay? So we will reverse the part of the linked list that comes after the middle element, okay? Let us do that. So the first question comes out is, first we have to find the middle element, okay? Then the second thing is reverse the list after the middle element, okay? And then we have to compare corresponding elements in the first half and reverse of second half, okay? Now let us do this step one by one. So how will we find the middle element? So I mean, like, if you have not heard of this approach, this is known as hare and tortoise approach. Okay, what a hare and tortoise approach is that we maintain 2 pointers on the linked list. Initially, the first pointer is here as well as the second pointer is here. One pointer moves faster, actually at the double speed of the second pointer. Okay, so at the next step, the first pointer will go here, the second pointer will be here. Then in the third step, first pointer will be here, second pointer will be here. Then first pointer will be here and second pointer will be here. So as soon as one of the pointers reaches the end of the linked list, that means the other pointer will be at the halved position of the linked list. Okay. So I mean, like, you can read about this after this session if you are hearing this approach for the very first time. But let us do that. So we say list node value at tortoise. I mean, you should actually not take these variable names. You should say slow, which is initially A. Then you should also say fast, which is equal to A. Okay. So while fast not equals to null and fast next not equal to null. So we move the slow pointer by one step. Slow is equal to slow next. But we move fast pointer by 2 steps. Fast is equal to fast next. Okay. Now, when the fast will be null, so when the fast will be null, that will be a situation like this. Let us say this is a linked list. So in this case, initially slow will be here and fast will be here. Then fast will go here and slow will go here. Then fast will go here and slow will be here. So when the fast is null, at that time, slow is pointing to the first element of the second half of the linked list, right? Okay. But let us take a case when the linked list is of odd size, 1, 2, 3, 4, 5. In this case, initially slow is here, fast is here, then fast goes here, slow goes here, then fast goes here, and slow is here. At this point, slow is pointing to the exactly middle element, okay? And we have to reverse the second part, I mean, like, just after the middle element, okay? So we will say if fast not equal to null, slow is equal to slow next. Now we are sure that the element slow is pointing to the very first element of the link, at the very first element of the second half of the linked list. Okay, awesome. But anyways, we will have to do, wait a second. So if first not equal to null, second is equal to second next. Okay, that's it. And always we have to set this slow next equals to null. Now we reverse the linked list that starts at second. Okay, how will we do that? We say list not So this is also a very good technique that you should use whenever you are solving a linked list problem. While solving a linked list problem, you maintain a dummy head, okay, which is node that contains only 0. So initially, the previous will be dummy. The current will be the very first node, which is A, and next will be nothing. So we will say while now not equal to null, next is equal to now ka next, okay. Then now ka next is what? Now ka next is the node that was the just previous node, okay. So actually we can actually initially take previous as null. So that will also work for this, okay. Now ka next is equal to previous, and now what is the previous? Now previous is equal to now. Clear? Okay. So now we have done this. At the end, the previous node will represent the head of the new list, because at the end, previous will point to the node 4, which is the new start of the list that comes at the second half. Okay. So now we know this. So we will say while your first pointer is at A and the second pointer is at previous, we will say while first pointer not equal to null and second pointer not equal to null, if first pointer key value is not equal to second pointer key value, return false, and we say pointer equals to first pointer ka next and second pointer equals to second pointer ka next. Finally, if we are out, that means we can return true. That means the whole list was a palindrome. Does this seem correct? Let us test it. Okay, so actually we did a time limit exceeded. So basically we entered in some kind of a loop, right? Let us see where we did wrong. Okay, so we should do this here. Otherwise, always something like this, right? Let us see if we can test it. So we are saying while if fast not equals to null, second is equal to second ka next, okay? And we are setting the slow ka next to null. Slow is the previous element here. So in this case, in the very first case, we saw that when fast was null, slow was pointed to the first element. So we also need to know actually the previous. So we also need to know the previous slow. Slow, which will be initially null. And we will say previous slow is equal to slow, okay? So, okay, in this case, when the array size is given, initially slow will be here and fast will be here, okay? Then slow goes here, fast goes here, slow goes here, fast goes here. In this case, previous slow ka next should be null, okay? Else previous slow ka next should be equal to null and second is nothing but slow, okay? Great. But in the case of odd, slow will point to the very first element. So second is equal to slow ka next. Okay, second is equal to slow ka next. And we set slow ka next equals to null. Okay, now does this look cool? This looks good. And so here we are breaking the list basically into two parts. And then let us see that if we can actually test it. First, let us test in custom input. Okay, we are not changing now to next, right? Previous is now, but now is also next. So we have to do this. Okay, and now this will work. Yep. So, but this case it should return 1, right? So in the case of 1 to 1, slow will be here and fast will be here. Then fast goes here and slow comes here. So in this case, what is the start of the next? This is 1. So we will say that we have to reverse the list that starts at second. So we have to reverse this thing, right? While now is not equal to null. Now is actually not A. We are reversing the first list. Now is second. Yep. Now this is working. Yes, and it is submitted. Are we missing an edge case? I think yes, we probably are missing the edge case where all the elements are null. One advice for any kind of linked list question, make sure that you never end up assessing a null element. That is actually a very big mistake that many people do. Okay, always ensure that the pointer that you are assessing in a linked list is not null. So that is one of the biggest mistakes I've seen many people doing that in linked list questions. Okay, cool. So we're done with the very first question. So here we learned two techniques. The one was the hare and tortoise approach, and the second thing was how to reverse a linked list. So basically this is a combination of two questions. Let us do a question in this pointer now. So let us say that we are doing swap list nodes in pairs, okay? Because K reverse linked list is just same as a normal linked list question, normal reverse the list question, okay? Let us say that we are solving this question that is swap list nodes in pair. Okay, so we are given a basically linked list and we have to swap 1 and 2. Then we have to swap 3 and 4. So basically 1 and 2 will become 2 and 1. Then we are done with this particular part. Now we are taking the care of the part 3 and 4. We again swap it, which becomes 4 and 3. Okay, and we are asked that, hey, we have to use only constant extra space. So basically we can't create a new linked list. But what is meant by a constant extra space question is normally that what we mean by a constant extra space in linked list is that you don't have to create a duplicate node. You have to use the nodes that were given in the initial question itself. Okay. Okay. Anyways, let us try to see how we can do this. So basically linked list is nothing but a game of pointers. How you are able to mingle pointers is how you will win the game. So let us say that we have 1, 2, 3, and 4. Okay. So now suppose I have to reverse this linked list. I told that in the previous question as well that dummy head is a very common and helpful technique in solving any kind of linked list question. Okay. So for example, here what I will say, I will assume that there is a dummy node here, after which it is 1, after which it is 2, and 3, and 4. Okay. So now see, suppose I'm reversing the pair of 4 and 3. I at least need the pointer to 4 and also the pointer to 3. Okay. But I also need the pointer to 2. Why? Because when I have reversed these two, I have to make sure that 2 ka next points to 4. Okay. So we at least need 3 pointers. Okay. So let me first create a dummy node. Let me name this pointer. Let us say that when we were swapping 3 and 4, let me name the variable 2, the variable that stores the node 2 as the previous pair end. Okay. So let me say list node value at previous pair end. Initially, it will be dummy, right? Because this is the end of the first pair. This is our assumption. Okay. So this will be dummy. Okay. This will be equal to the current pair start. Okay. So this is current pair start. Okay. Which is in the case of in the first case, this will be the node A itself. Okay. Awesome. Okay. So while I will say that while the start of current pair is not null, start not equal to null. Okay. So I will say current pair second is equal to, okay, I let me also assume that current pair start ka next is also not equal to null. Is not equal to null. Okay. So current pair start ka next. So basically both the nodes of the current pair exist. Okay. If there is only one node, we don't need to do any swap, right? So I will say current pair second is equal to current pair start ka next. Okay. I also know the previous pair end. At the end of the current iteration, what will be the previous pair end? Previous pair end at the end of current iteration will be the starting node of the current pair. because at this time, let us say this was the start and this was the end. Okay, so after this will change to 4 and 3. So basically this will be the previous pair end, so which is the current start node. Okay, and we also have to make sure that current pair ka second, so basically previous pair end ka next is equal to current pair second, now has to point to 4. Okay, and current pair second ka next is current pair. So now we have made sure that 2 points to 4, 4 points to 3. Okay, and finally we have to make sure that 3 points to this. Okay, current point start, current pair start ka next should be equal to what is currently the current pair second ka next. Okay, finally the current pair second next, and this is previous pair end. Okay, and finally I can just return dummy ka next. Okay, because dummy was just a node that we assumed. Okay, so now in this case dummy ka next will become, so the pointers will change like this, right? And 1 will now point to 3 and dummy ka next will point to 2. So dummy ka next will actually be 2, which is the start of the next list. Let us see if that is correct or not. We might have done some errors, but let us see, hopefully not. What did I do? Oh, I didn't comment here. What are we doing here? So we are saying that initially we actually made sure that dummy ka next should be equal to A. Okay, because dummy is going to point to 1, right? That I told earlier. I will like initially dummy should point to 1 and 1 should point to 2. So I didn't point the dummy to first one. Now let us test this. You lost 0. Okay, and I say first pointer previous pair end is dummy. Okay, and current pair start is A. Okay, while current pair start is not equal to null and current pair start next is not equal to null. Okay, both are not equal to null. So then current pair second is current pair start next. Okay, we change the previous pair end next to current pair second. Okay, so now dummy node is starting to point to 2. Then we make sure we point 1 ka next equals to 3. Okay, so now dummy node is pointing to 2 and 1 is pointing to 3. Okay, now we should point 2 to 1. So current pair second ka next, that is 2, is now going to point to 1. Okay, and previous pair end will be equal to 1. That is fine. So this thing is fine. And what will be current pair start? Okay, so now we have not changed current pair start. If previous pointer end not equal to null, current pair start is equal to previous pointer next, else current pair start is equal to null. Similarly, if current pair start is not equal to null, then okay, so we don't have to do that. So we only need current pair start and we are done. So now 2834 is changed to 3428. 4874 is changed to 7448. Similarly, 4249 is changed to 4942, and we are doing well. Let us see if we have any issues. Seems fine. Great. So we got this as well. So one thing we learned from this thing, the takeaway should be that, hey, for any linked list question, first try to find what are the pointers that you need to know to reorder the list in any way. Suppose it is swapping pair. What are the elements you need to know so that you can change their pointers to something else? That is the very first thing you need to know. And the second thing is, again, I tell you to know, is this dummy thing. This is very important in a lot of linked list questions. I will do one more question after this that will use this thing. And the third thing is, make sure that you are never assessing null. Okay, so here also I do a check of null. Make sure you are never assessing something that is null. Okay, cool. Let us do one more question. So the question is, we are given a singly linked list L0, L1, Ln minus 1 to Ln. Okay, and we have to reorder this to L0, Ln. Okay, so the very first node from the start and the very first node from the end, then the very second node from the start and the second node from the end, third node from the start, third node from the end, and so on. Okay, and we must do this in place without altering the nodes values. So what in place means is that you don't have to change their values. I mean, like, you can dangle some pointers, but that will work. Okay, you just don't have to change the node values or create a duplicate of those nodes. That is the only requirement. Okay, so one thing that I find from here is that, hey, if we somehow, let us say that this was our list. Okay, our list was 1, 2, 3, 4, 5, and 6. We have to change this to 1, 6, 2, 5, 3, and 4, right? Suppose I know the first half of the list. I also know the second half of the list, which is 4, 5, 6. Okay, now I reverse the second part of the list. This is 6, 5, 4. Now what I do, I keep on merging this. First, this is 1, so I will put this 1. Then I put this 6. Then I put this 2. Then I put 5, and so on, right? Okay, so how can we do that is, first split the list in 2 halves. Okay, then reverse the second half. Okay, and finally merge 2 lists. This is something that you do. This is something very similar to that you do in a question like merge sort, right? In merge sort, the merge step is something like this. Okay, okay, let us do these steps one by one. In the previous question, we had discussed an approach to split the list in 2 halves and reverse the second half, right? We had discussed that in the very first question for the day. Okay, so let us do that. So how did we do that? We do this question by using 2 pointers, the slow and the start. Okay, so initially the slow pointer is equal to A and the fast pointer is also equal to. Then we do while fast not equal to null and fast next not equal to null. Slow is equal to slow next and fast is equal to fast next. So now there were 2 cases. The first case was if fast not equal to null. When did that case happen? Let me redraw it again. That case happened when the linked list was of odd size, 1, 2, 3, 4, 5. So in this case, slow will be here and fast will be here. Slow changes to this, fast changes to this, slow changes to this, fast changes to this. In this case, fast is not equal to null, right? Okay. In this case, we can reverse this whole linked list. So this will change to 1, 2 will remain as it is, and this will change to 5, 4, 3. Suppose we are able to do that, then we can do the merging, right? Or not? Yes, you can do that. So it will be equal, yes. Okay. Okay. If the size of the linked list is even, then it will be 1, 2, 3, and 4. Then slow will be here and fast will be here. Then slow goes this, fast goes this, slow goes this, and fast goes this. Then also we can reverse the linked list that starts at start. So that we could do even in the previous question. I missed this thing. So we can reverse the linked list that just starts at the slow pointer. Okay. So suppose we reverse this part of the linked list, then we are cool. Let us see how we will do that. So we have to make sure that the pointer of 2 is now the next of 2 is null, so that these two lists break off, right? Else anything can happen. So we will say list node value at previous low is equal to null, and previous low will be equal to slow. So finally, we can say previous low next is null. So at this point, we have broken the list into 2 halves such that slow points to head of second half. Okay. Great. Okay. So now let us reverse the linked list that starts at the slow pointer. Okay. So basically reverse this 345 to 543. So we will say list node value at previous is null. List node value at current is equal to slow, and list node value at next, this variable we will need. We will say that while current is not equal to null, that means there is still a node there. Okay. So while current is not equal to null, I will say next is equal to current ka next. Then I set current ka next is equal to previous. Finally, I change previous equals to current. And what is the next current? The next current is the node that was currently stored in the variable next. Okay, great. So now this has reversed the linked list at 345 to 543. At the end, the node 5 will be the previous node. So we can say that list node value at second head is equal to previous. Now we do have to just merge both the linked list, right? So we will say while a not equal to null, sorry, yes, for this also we will need a dummy node. Then we will need a pointer to the current index in the answer. So list node value at dummy pointer. Initially, it will be equal to dummy. Okay. We also need a pointer, which will be initially a. And we also need the pointer to the second half, right? So this will be second head. So we say that while a pointer not equal to null and second pointer not equal to null, okay. So while both of these are not null, we first append the second thing to this. I mean, like then we append, but we say we have to first append the node at a pointer, right? So we say dummy pointer ka next is equal to a pointer, okay? Then dummy pointer equals to dummy pointer ka next. Finally, dummy pointer ka next, okay, and a pointer is also equal to a pointer ka next. Then dummy pointer also moves to one step ahead. We change dummy pointer ka next is equal to b pointer, or the node that b pointer points to, okay? And then we say b pointer is equal to b pointer ka next. Okay, great. So now what will we be having is, suppose for a linked list of odd size, we will be having something like this: 1, 5, 2, 4. Okay, but at this time, the pointer to the second pointer will not be null, but the first pointer will be null. So we say if pointer is not equal to null, that meant that the total number of nodes were odd. So we will say dp, again we have to make sure, okay, dp next is equal to what we say, the second pointer. Okay, Okay, so dp connects is the second pointer, and finally we have reached the end, so we don't need to do anything. We can so yep, we are done. Now, but where is the answer? The answer is the dummy head ka next, right? Because dummy head ka next is storing the very first node in the answer. So we can just do return dummy pointer ka next. Sorry, dummy head ka next. Like this. Dummy ka next. Let us see if this works. What is this happening? This is returning dummy pointer ka next. What is the dummy pointer ka next? Initially, this is the first pointer, but the first pointer is null. Initially, the second pointer is also a. So the second pointer will still point to this. So second pointer will not be equal to null. So this should be correct, right? So let us see why this particular case is having issues. Okay. So in this case, we won't ever go here. So if we don't ever go here, that means that there was only one node, right? That will happen only if there was less than two nodes. So we can say if previous low is equal to null, we can just return the original linked list. Why? Because this thing will happen. I mean, like previous low will be equal to null only if there are 0 nodes or 1 node. In that case, we don't need to do anything and we can just return the original linked list itself. So now this should work. Yep. Are there any other cases that you are missing? No. Yes, and let us submit it. Great. So yes, in this thing we missed checking for null one time and we again ended up with an issue. So that is why I was saying that never get to a situation where you are not checking for nulls. Okay. And also again, you saw that what is the use of dummy pointer. Dummy pointer allows us to improve the code quality by not checking for nulls in the initial previous. Okay. So use this technique as well. Let us do one more question and then we will end. Let us do this list cycle question because this also requires knowing a technique that many people might not know. So let us do this. Okay. So we are saying is told that we are given a linked list. We have to return the node where the cycle begins. Okay. The linked list might or might not have a cycle, but if there is a cycle, we have to return the node, the first node from the start where the cycle actually started. So for example, if we start traversing this linked list like this, the node 3 is the very first node where the cycle began, right? So we have to return the node 3. Okay, great. So let us see how we will do that. So see, we once found a middle of the linked list, right? We were once able to find the middle of a linked list using the previous approach, right? If you see the hash approach has a space complexity of order of n, right? So we have to do something that has space complexity of order of 1, but time complexity of order of n. Let us do that. So we remember that, hey, we were able to find the middle of a linked list using the hare and tortoise approach. But if the linked list has a cycle, will we ever be able to find the middle? No, right? Because fast will never be equal to null. So if we start growing from 1, 2, 3, 4, then we will keep on coming back to 3, 4, 3, 4. So if we were supposed finding this thing, value at slow is A. Fast is also A. We say while fast is not equal to null and fast next not equal to null. Fast is equal to fast connects and slow is equal to slow connects. Okay, but when there is a cycle in the linked list, this loop will never end. Okay, because it will again going on circle around. So let us say what will happen. Okay, suppose the loop is circling around and currently, let us say this is the case. So this is a linked list 1, 2, 3, 4. Okay. Okay, and suppose all these nodes are in a cycle. Suppose all these nodes are in a cycle. Okay, it might happen that currently fast is here and slow is here. Okay, that means in the next iteration, fast will go, what we say, at this place, and where will slow go? Slow will also come at this place. Okay, so okay, that is the case one. The case two is, let us say fast and slow are very much behind. Okay, let us say initially the fast was here and slow was here. Okay, then what is going to happen in the next iteration is, in the next iteration, fast is going to come here and slow is going to go here. Now this condition is again same as this condition, right? The condition that we had here. So we can say that if fast and slow pointers are in a cycle, that means they are definitely going to meet at some time. Okay, so we can say while fast not equal to null and fast connects not equal to null, okay, if fast is equal to null, this means that there is a cycle, right? This means there is a cycle, so we can break. So here we can say that if fast is not equal to null, or and fast connects not equal to null, or fast connects not equal to null. So let me say that I pool cycle is equal to false. If we enter in this loop, we say that cycle is equal to true. That means there is a cycle in this current thing. Okay, so if there is a cycle, now the question comes, how will we find the start of the cycle? But let us solve the case if there is no cycle. If there is a no cycle, we can just return null, right? Now let us see how we will find the start of the cycle. Okay, so let us say our cycle is like this. So there are nodes 1, 2, 3, 4, 5, 6, 7, and this 7 is pointing to, let us say, 4. Okay, so 7 is pointing to 4. Something like this. So suppose 7 is pointing to 4. Okay, that means this is a cycle. Okay, great. So now how will we find that 4 is the start of the cycle? How will we be able to do that? Let us see. Suppose, assume that this size, the size of the linked list before the start of cycle was A. Okay, and currently both the slow and fast pointers will be traversing 4, 5, 6, 7, again 4, 5, 6, 7, and so on, right? Is that clear? Okay, so now we know that this is, so now somewhere inside this linked list will both these nodes meet. Suppose both the fast and slow meet at this particular place. Okay, and let us assume that from the node start, this distance was B. Okay, so A was the distance of start of cycle from head, and B was the distance of meeting from the current node. Distance of meeting from the start of cycle. Okay, okay. And let us say we also have a variable C, which is the start of cycle, which is the size of cycle. Okay. Okay. Now, can there be any formula between A, B, and C? Fast will not become null when there is a cycle, that we have assumed. So basically, that is why at this particular position, if fast is equal to slow, we are saying that there is a cycle. Okay. So now let us try to see of one more thing. We say that, hey, this size was A. Okay. This size, suppose the nodes met at node 5. This size was B, and this size is C. Can there be a relationship between A, B, and C? Let us see in this way. Suppose the fast and slow pointer had traveled this node X times, this cycle X times, when they were inside the cycle, because they will keep on circling around, right? Okay, suppose they had traveled X times. So the total distance traveled by slow will be equal to this, which is A, plus the number of times they travels this cycle. What will be the number of times? Let us say they travel this n times. And what is the size of this they traveled? The size of cycle is C. So plus n times C. And they met at this. Okay. So what is this distance? This is B. So this will be the distance covered by the slow node. Correct? Okay. And what will be the distance covered by fast node? The distance covered by fast node is nothing but 2 times the distance covered by slow node. But how many iterations would it have done? How many iterations would the fast pointer would have done? Suppose fast pointer did y iterations. Okay. Slow pointer had done x iterations, and let us say fast pointer had done y iterations. So the distance covered by the fast pointer is going to be A. So this is n, let us say this is m. Okay. So A plus m into C plus B, right? That means A plus m into C plus B is equal to 2 times A plus n into C plus B. Is that clear? Okay. From these two equations, we can find that we'll be able to find that what will be the equation that will come out to be? The equation will come out to be that, hey, what is the distance from A plus B? Okay. Okay. So if we try to expand this equation, this will become A plus m into C. So let us try to expand the right hand side first. This is equal to 2 into A plus 2 into n into C plus 2 into B. Okay. If we take B to the left side, so this will become A minus 2 into B, and also bring this A to minus 2 into A plus B, right? So, okay. So this is going to be equal to 2 into n into C minus m into C, right? Okay. So what we get from this is that this is nothing but equal to minus of, this is equal to minus A minus B, and the right hand side is equal to C into 2 into n minus m, right? Okay. But what we find from this, this means A plus B, a negative, is equal to C times something. But what is C? We see that C is the size of cycle. So basically, we find that, hey, the distance from A to B. So basically, this distance is actually going to be a multiple of the size of cycle, right? So if we again start a pointer from this particular position, and we again, so basically till this time, this goes till here, the pointer that will be at this place will actually come to 4 again. Why? Because it will go from 5 to 6 to 7 to again 4. And by the time another pointer, if we start from 1, will also reach to 4. And 4 is going to be the start of cycle. Okay? So what we can do is, we can again put slow is equal to what we say A. And we say while slow is not equal to fast, this time we will move both the pointers by only one movement. Okay. So we will say slow is equal to slow next, and fast is equal to fast next. Okay. Now that means, okay, that means now where they have met, that is nothing but the start of the linked list, start of the cycle. So we can just return slow. So in this thing should work. What happened? Okay. So we will actually have to start with, okay, so this thing will be actually initially true, because at least we have to move fast and slow ones, because they will otherwise always be true. Right? Yes. And let us submit. Great. So we did one more question, and today our streak points are equal to 1685. Cool. So that's all for today. Make sure to complete your streak as well. Okay.
Okay, so today we are going to cover stacks. So let me give you first a little introduction about stack. So first of all, the stack is very much important. It's the most favorite topic of the interviewers. Be well versed with this topic. Like first go through the basics, understand it because they are very straightforward, and then attempt as many questions as you can. There are some, standard problems that you should definitely attempt. That was the gist about stacks. Now let's get started. Cool. So stack is very much similar to the stack of objects you see around yourself. So be it stack of plates, stack of books. So stack of plates, stack of books, then stack of, let's say, bowls. So you see it and use it every day, right? So let me draw the stack of plates. So this is how a stack of plates look like. Now from the stack of plate, you can insert a plate only from this end, that is top, right? You can only insert a plate on top, and you can only remove a plate from top. You cannot insert or remove a plate from in between, because that will disturb all the plates, right? So you cannot do that. You can only remove and insert a plate only from top. So that's essentially the idea behind stack, that we can only insert an item from top and we can only remove an item from top. Okay. So conceptually or logically, you can think of a stack like this, where one end is open and three ends are closed. So from only this end, we are going to perform operations, that is to remove an item and to insert an item. As I was saying, that we can only insert an element from one end and remove an element from that end only, and therefore stack is known as LIFO data structure. That is the last, as you can see the stack of plates over here. So this plate which was inserted at the very end will be the first one to come out. That is last in, first out. Okay, cool. So first what we are going to do, we are going to understand stack as an abstract data structure. That is ADT, abstract data structure. What do we mean by abstract data structure? In which the implementation details are hidden, but the operations are given to us. Okay, so let me write it over here, that implementation hidden. Okay, it's not there, it's not given, but only the operations are there. Only the operations are there with which, using which we can use the stack. Okay, so for example, you can see the fan on top of you, right? So you don't know how it's working internally. All you care about its operation, as in you put down the switch and it turns on, and you put off the switch and it turns off. That's what you care about. So that's an abstract. Cool. So we are given, let us understand the basic operations that are available with stack. Okay, so there are 4 basic operations. The first one, I am sure you guys, if you know about stack, you must know about all these operations. So that is push function, and then second is pop, the third is top, and the fourth is empty. Okay, so the push operation actually helps us to push an element on the top of stack. So this pushes an element on top of stack. Then here we have pop. So pop removes an element from top of stack. Then we have top. So it returns the element present on top of stack. So whatever element is present on top of stack, it just simply returns it. Okay, so don't worry, we are going to see an example over here. Is empty is the function that tells us if the stack is empty. So if the stack is empty, it returns true, else it returns false. Okay, so these are the 4 operations, that is push, pop, top and is empty. Push pushes an element on top of stack, pop removes an element from top of stack, top tells what is on top of stack, and is empty returns true if stack is empty, else it returns false. Remember that pop simply removes an element and top does not remove an element. It simply tells what is present on top of stack. Is it clear now? Okay. So basically, while performing a question, you will have to use in C++, let's say you can use STL, right? In STL you have stack. So in C++, you declare a stack like this. You can use a stack like this, and on this object basically you can call all these functions. So push x, then s.pop and so on. Likewise in Java, you have collections using which you can use stack. So while attempting a question, you don't have to implement a stack of your own until and unless told. Okay, so but in a while we are also going to see how to implement a stack. We are going to actually implement these operations. Okay, cool. Okay, so let's actually see a dry run of these functions. So here this is a stack, and these are the operations that I would want to perform: push 2, push 1, push -1, push 5, then pop, pop is empty, top. So let's perform these functions, okay? So it's push 2. So what we'll do, from where we'll put it? We'll put it from here. So basically 2 will come over here. Then it's push 1. So 1 will come over here. Then -1, -1 will come over here. Then there is 5, 5 will come over here. Then we are popping. So 5 will be gone, right? 5 will be gone. So we have removed 5. Now again pop is there. So -1 will be gone. So we have removed -1. Okay. Then we are checking, is the stack empty? What will it return? What will this return? It will return false because the stack is not empty, right? The stack is not empty. Okay, so now there is top. So what will be the top function return? It will return whatever is present on top of stack. So basically top is pointing over here. So whatever is on top of stack, it will return that. So it will return 1, right? It will return 1. So that was a simple dry run of how can we use these operations. Okay, how these operations work. Now let us come to the applications of stack, which are very important. Applications of stack. So some of the applications are undo, redo. Then we have arithmetic expression, evaluation, right? Then we have recursion. So these are some of the, then we have string reversal and so on. So these are some of the applications of stack which are very important and you must know. So try to figure out that how a stack can be used in these operations. You know, that's an activity for you, that do try to search that how we can perform an undo, redo. So this is actually present in your browser, right? So whenever you go to any page, from any page and want to come back, so basically you store, for example, let me give you an example. So you are at link, let's say 1, then you go to link 2, then you go to link 3 and you want to come back to link 2. So what you can do, you can actually maintain a stack of them. So like first you are on link 1, you can put it on a stack, link 1. Then you are going to link 2. So put it on top of stack. Then you are going to link 3. Then put it on top of stack. Now you want to come back to link 2. So what you can do, you can simply remove this. And now you are back to link 2. Does that make sense? So likewise, you can also have a redo stack. Okay, so that's an activity for you, that how you can perform a redo operation. Okay, so likewise try to figure out. And we have arithmetic expression evaluation. So I think you all must be very much familiar with this. That is, converting to infix to prefix or postfix, then evaluating the postfix notation. So that's where you can use stacks. Okay, and then you have recursion. Stack is a core of recursion. So you make function calls, and when you come back, so that basically those function calls get stored on top of stack. Okay, likewise string reversal. Okay, so there's another application that you may be using in your daily life. You must have seen this Insertion app, right? So what happens in this, you are on this screen, okay, and so here I am actually at my feed. I am at my feed, okay, and I am watching this news. So I can only see another news if I remove it, if I remove this. So can you see that how this is an implementation of stack, right guys? Now let's talk about the implementation of stack. So could you guys tell me how can we implement a stack? So using arrays, second is using linked list. Okay, so how can we implement a stack using arrays? So basically, let's see. So we can have an array. So size of the array is, so array is A, and size of the array is 7. Okay, so what we can do, so let's say I want to push 2, push 3, push -1, pop, push 7, pop. Let's see how can we implement these operations using stack. Okay, so what we can do, basically we can actually enforce that one end of the stack will be there to perform all the operation. So you can imagine it like we are pushing the elements from here and removing the elements from here. So let's say I want to push 2, so 2 comes over here. Now you can also maintain a top variable which is right now pointing over here. That means what is on top of stack? 2 is on top of stack. Then we have push 3. So what we can do, we can simply increment this top variable and push 3 in here. Then push -1. So we can simply increment this top variable and push -1. Now how to pop it? How can we pop it? Top minus minus. So basically we are now at index 1 and we have, so basically -1 is gone. Okay. Then we are at, so this was done, then we are at 7. So again we can increment the value of top and 7 comes over here. Now again pop's coming, so we can come over here and this is gone. So basically that's how we can operate a stack using arrays. Okay, and now can someone tell me the problem of stacks? So problems of stack are, which are very important if let's say an interviewer asks you to implement a stack using arrays or linked list. So if I talk about arrays, then we have problems, overflow and underflow. Let's say I want to push 1, 4, 0, 5, 6. These are the items that I would want to push. So 1 comes over here, then 4 comes over here, then 0 comes, then 5 comes, then 6 comes, and now I would also want to insert, let's say, -1. So as you can see, as I move my pointer forward, there is no space because array has a fixed space, right? So I cannot insert any more element, and that leads to the condition of overflow. Okay, and it's very important. So if interviewer has asked you, he's basically maybe judging you that will you cover these cases or not. Okay, so this is the thing. So how can you handle it? So basically here you have mentioned a size, right? You can keep a check that if size, so if top is equal to the size -1, so in that case, that's an overflow. You cannot insert any more elements. So that's a drawback of arrays. And to overcome that, basically you can use something known as dynamic arrays. Okay, you can use something known as dynamic arrays. Okay, now let's say I want to pop, I'm calling pop 7 times. Okay, so basically this is gone, third time, fourth time, fifth time, sixth time, and seventh time. And now I am again calling. So now what will happen? Will I be able to pop any more element? No, I will not be able to pop any more element because the stack is empty. So if I attempt to do so, that will lead to underflow condition. That will lead to underflow condition. So how can you make it all right? Basically, you can put a check that if top, so if top is equal to, let's say, -1, then print underflow, okay, and simply return. So that's how you can manage underflow and overflow condition. Does that make sense, guys? Underflow is when you are trying to pop an element when there doesn't exist. When you are popping an element when there is no element. So how will you be able to pop? Will you be able to pop? No, right? So that's the case of underflow. So you can manage the case of underflow by checking that if top is equal to -1, that means you have no element. So you simply print underflow and return. Cool. So let's talk about linked list. So in linked list, what you can do is, so you have nodes in linked list where this is the data part and this is the address part. So basically, the nodes of the linked list can be present anywhere in the memory, right? Like array, you don't have everything in a contiguous manner. Everything is scattered. Every node is scattered in linked list. Basically, if you have this as a memory, so if let's say one node is present over here, another node can be present over here. Okay, third node can be present over here. So basically, this address field actually links node. So basically, this will be linked to, let's say, this, then this is getting linked to this, and so on. That's how we store data in linked list. So basically, let's say you have 2 and 1 right now. Then you want to insert, you want to push, let's say, 7. So how you can do? Right now, top is here. So at what position, if you, so you are actually, remember, you are actually implementing stack using linked list. Where would you want to insert this node? This is your linked list. This is what you are building. This is the temp node, current node, that you new node that you want to insert into your linked list. So where will you insert it? That we can actually put it on top of head. So now we can actually make this its next pointer point over here. So this is how our stack would look like. Now top will be over here. Okay? So you can, in case of a linked list, you can imagine a stack like this. Like this, it's growing, right? Like this is it's growing. And when you want to pop an element, so basically you can actually shift this top to the next position, and this will be, so basically you can free up this space. Okay? So that's how you can implement a stack using linked list. Now with linked list, the concept of space. A lot of space is used in linked list. Okay? So basically you are storing pointers as well. That will take a lot of space. And pros of both stack and cons is that you will be able to perform push and pop operation in just order of 1 time complexity. Okay, in just order of 1 time complexity. Okay, cool. Let's get to the question. Okay, so the first question that we have is of very much famous question and very much asked question. It's of valid parenthesis. Okay, valid parenthesis. So the question says that you are given brackets, the round brackets, okay, and you have to tell whether the parentheses are balanced or not. Let's say you are, building this compiler in which you will be writing your code, right? So basically you will be, you want your compiler to check, verify your code. So in that case, you will definitely want how can we check if the bracket are valid or not. So how can we do that? Let's see. First of all, let me give you some examples. Let me write down the examples. Okay. So what do you say about the very first parenthesis? What do you say about the very first parenthesis? Are these set balanced? Is it balanced? Yes, it is balanced because a corresponding opening bracket has a corresponding closing bracket. So yes, it's balanced. Then if I talk about this, is it balanced? No, it's not, because this is complete, they are balanced, but here this opening parenthesis is lacking a closing parenthesis, or you can also say that this parenthesis is lacking a closing parenthesis. So this is not balanced. This is not balanced. Likewise for this, so this is lacking an opening bracket, or you can also say that this is lacking an opening bracket. So this is also not balanced. Okay, so you have to basically tell, are the parentheses balanced or not? Let's say we want to attempt this question without star. Can anyone think of something? Okay, so let me first actually put some observations. Let's do the question step by step. Okay, let's do the question step by step. So observations are, the first observation is that, can an opening bracket make a string invalid? As in, let's say I'm traversing the string and I find an opening bracket. So can that opening bracket make the string invalid? Well, it depends upon the future. It depends upon the future, that if I have this opening bracket, maybe in future I'll find a closing bracket and that will be valid. Or let's say I don't find a corresponding closing bracket, in that case it will be invalid. So it totally depends. It totally depends if I get an opening bracket. Okay. Now if I talk about a closing bracket, so what about a closing bracket? Can a closing bracket be a problem to us if we encounter it? Well, so if till now for a closing bracket there was no opening bracket, in that case, yes, it is a problem, because even if we move any further, the string that is given to us will not be valid in any case, right? In any case. So basically, let's actually let's take look at it like this. So I have something like this. So what will happen? Let it be like this. So I am at here. I will maintain, what I can do, I can maintain a left and right count, which can be initialized to 0. Now I am at an opening bracket. So that means left actually tells a opening bracket and right tells the count of a closing bracket. So I found an opening bracket. This becomes 1. And so let this be the thing. Let this be the bracket. Now I am here. So what I can do? I can simply decrement the value of this, and that will tell us that we actually found a match for an opening bracket. So we can actually set this to 0. Right. Now let's say I have a string like this. What will happen? That I am here, left and right. So basically I have left 1, then I have a closing bracket. So initially both are 0. So now this is a closing bracket. So is left greater than 0? Yes, it is. That means there is an opening bracket. So we can simply decrement it, telling that we have found a match. Now next we go to the next character. This is a closing bracket. Okay. So what's the value of left? It's 0. That means there's no opening bracket. In that case, we will simply return that it's invalid, because at this point there is no use to move any forward, because this closing bracket does not have a matching opening bracket. So we can simply return from here. Does that make sense to everyone? Okay, so whosoever is saying that, can we count the number of opening bracket and the closing bracket? Guys, we cannot simply count the number of closing bracket or opening bracket. Okay, let's take an example of that. Let's say I have this as a string. So now left is equal to 2, right is equal to 2. But are they valid? No, they are not valid, because they are not placed in the correct order. Therefore, this is not a right approach. Is that cool? The time complexity of the approach is what? What's the time complexity of the approach? So if we have this case, here the number of closing brackets are 2, number of opening brackets are 2. So are they valid? No, they are not valid. So this is wrong. This way is wrong. So what's the time complexity, guys? time complexity is just order of length of the string, because we are iterating the string just once. And what's the space complexity? Just order of 1. We have not used any space. Okay, we have not used any space. Now let me make a question little trickier. Now let's say I have brackets these and these. So this is an extension of the question. Extension hai ye question ka. Now I am saying that I have these 3 sets of parentheses. Now I have to tell, basically my string can contain these set. So I have to tell if those are valid or not. Let's take an example. Examples can be this, then we have this. So this will be given to you. Now you have to tell, are they valid or not? Now how can you do it? How can you do it? So whenever in the interview you're telling the interviewer that okay, we can use tag for this, but she or he already knows, right? You have to get to it, like how, what's the intuition? So that's is very important. Okay, some of you are saying that we can use 3 variables, so that will be wrong, because then you won't be able to actually find the order. You cannot judge the order by taking that many variables. So first of all, I am sure that you guys understand that it cannot happen by taking just the left count and the right count, because if okay, so first of all, let's take the example of this. Now here left is 1, okay, and now I find a closing bracket, but here they are not same, right? So this will not work. Having left and right is a bad idea. Now taking 3 variables. So here I have this string. So if I take 3 variables, let's say round, or let me write first bracket, second bracket, third bracket. Now here the first type. So this is type 1, type 2, type 3. First bracket ka left, right, iska left, right, then iska left, right. First ka left is 1, okay. Third ka left is 1, okay. First ka right, so we have found a right bracket and this manages to be 0. Then we have third ka right, so this becomes 0. But is this valid? No, it's not valid, because the order is different. Order doesn't match. So therefore, that's a bad choice. Does that make sense? You should have a clear idea that why your approach is wrong. You should take as many, like if you are stuck, you are not able to think, take examples and try to generalize it. You guys are clear with it? Cool. So let's move forward. Now let's actually build some intuition of this. So one thing is that, let's consider these brackets. One thing is that if, so since, okay, so this is invalid, right? This is invalid. This is also invalid, right? This is also invalid. This is valid. This is valid. They have right set of pairs. Now this is also, this is what? This is what? This is also valid. Okay. This is also, as you can see, that this is also valid. So if I talk about this string, then it's a property of the valid parenthesis that if the complete parentheses are balanced, then their sub parentheses will also be balanced. As you can see that this is balanced, this is also balanced, this is also balanced. So we are not considering all the substrings, right? We cannot consider anything like this or something. We have to choose the right set. But what it means is that whatever the parentheses are inside it, they will be balanced anyhow. So this is its corresponding pair. Then we have this, it's correct, then it's correct, then this is there. So does that make sense? That inside of it parentheses are balanced? Now, so an opening bracket does not bother us, right? An opening bracket does not bother us because in future we may find a closing bracket for it, right? But let's suppose I am at this closing bracket. Let's suppose I am done with everything and I am at this closing bracket. Now for this closing bracket, this is an opening bracket, this is an opening bracket. Does these brackets are of any use to me? No, they are not. Can I get rid of them? then that will be great, right? So if I can get rid of them, because they are valid in itself, right? As I told you by this property. So since they are valid, if I can get rid of them, then I can actually find out if this bracket has a matching opening bracket. Okay, so let's actually see a dry run of this using stack, because stack is the data structure that helps us find. Just look at just the past. Okay, just the past. So how and what we can do? We are at this bracket. This is an opening bracket. We'll see about it in future. So push it onto the stack. Then this is an opening bracket. We'll see about it in future. Put it on top of stack. Again an opening bracket. Put it on top of stack. This is a closing bracket. Was there an opening bracket for this? Yes. Where can I see? I can see it on top of stack. If there is a corresponding match for this closing bracket, then I can simply pop it off. Next time here. This is a closing bracket. Does this have a match? And see how nicely we have removed between whatever was presented. That is here. We have removed it. We have removed it. And now we are actually comparing this. Where can we find it? On top of stack. So yes, it has a match. Remove it. So now we are here. Now we are here. Put it. So this is our closing bracket. Yes, match found. So remove it. Remove it from top of stack. Then we have an opening bracket. Push it on top of stack. Okay. Then we have a closing bracket. Is the corresponding opening bracket present? Yes, it is present. Remove it from top of stack. Now we are at the last bracket. Is the corresponding opening bracket present? See here how we have gotten rid of all of this, right? So basically, yes, it's present. From where we can find? On top of stack. Just remove it. What's the condition we have to check for validity? And if the stack is empty, then return true, right? If the stack is empty, return true. But if the stack is not empty, so we have to return false. That tells, even after iterating the string, let's say we have completely iterated the string, even if the stack is not empty, so we will have to return false, right? Because there are still left some unmatched opening brackets. So at any time, let's say you have something like this. So at any time you don't find, so okay, let's do a dry run of this as well. So this is an opening bracket, move ahead, opening bracket, move ahead, closing bracket, but no corresponding match. Simply return from here. Simply return from here. Okay, so now let's move on to the next question. But before that, let's talk about the time complexity. The time complexity of this approach is just order of n, because we are going to each and every bracket not more than twice. How? Once while pushing it and another time while popping it. So that's only 2 into n, which makes it order of n, right? That makes it order of n. And the space complexity is order of n, because in the worst case, we may end up pushing all the brackets in the stack when, let's say, the string was something like this. In that case, you will end up pushing all the brackets in the stack. So the space complexity is order of n. Okay, so I hope that's clear, and we'll quickly move on to our next question. So intuition is that how can we, previously clear up something to get just the, so here as I talked about that, step by step we made the intuition, like, sorry, I just removed it. So as I was talking about that, inside of it will also be, balance. So if we can remove it, I will just be able to look at here. That's what I want to do. So we can simply remove it, and that is possible using stack. Okay, so let's move forward quickly. Cool. So question 2, and this is very, very famous question, which is of next greater element. Okay, so question is that, let's suppose you are given an element, you are given the elements in an array. Let's suppose 10, 13, 22, 7. For each of these elements, you have to tell that what is the next greater element to its right. Just the next greater element to its right. So what's the next greater element to the right of 10? It's 13. Okay, it's 13. The next greater element for 13, it's 22. The next, is there any next greater element for 22? No, it's not. So we can put -1 over here. We can put -1 over here. Then we have 7. So next greater of 7 to right of it, it's -1. Nothing is there. Nothing is there. Okay, so let me take, this was example 1. Let me take another example as well. So we have 10, 7, 4, 2, 9, 10, 11, 3, 2. Okay, so what's the next right to the right of 10? It's 11, right? Just greater element on the right of 10. It's 11. Just greater element on the right of 7. It's 9. It's 9. Just greater element to the right of 4. 9 again. To the right of 2. 9. Just to the right of 9. It's 10. Just to the right of 10. 11. Just to the right of 11. Nothing. To the right of 3. Nothing. To the right of 2. Nothing. Okay? Okay, cool. See, if you are implementing any question, you can use STL in C++ or collections in Java. You don't have to implement push pop functions on your own. That's just for the sake of if let's say your interviewer asks you. That's it. Okay, that's it. Cool. So if the question is clear, please tell me that how can we attempt it. At least give me the brute force approach. At least give me the brute force approach. So you will agree with me that brute force is nothing. So brute force is using 2 loops. So you can basically, let me actually write the code for it as well. So the brute force look like that. You can have an answer variable, answer array. Then you can iterate through all the elements from 0 to n-1. Then for those elements, you can again iterate from. So, okay, first you can initialize your result to -1 if let's say you don't find any element. So you can do for j that goes from I plus 1 to n-1. You can check if a of I is, so a of I is less than a of j, then simply put answer I is equal to aj, okay, and break from here. Take a break from here because you just have to find just the larger element. You don't have to iterate any further. Okay. Now what you have to do? Actually, this should be result, and out of this for loop, you can set answer I is equal to result. Does that make sense? This is just the brute force approach. Okay, cool. Let's go ahead. So the time complexity of this approach is order of n square, since there are 2 nested for loops, and the space complexity would be order of n, which we can ignore because that will be just to store the, so basically this is just so we can actually make it order of 1 only, because we anyway have to take an answer array. Answer array we anyway have to take because that's how we are going to return the answer. So the space complexity for this we can assume to be order of 1, right? Cool. Now let's talk about the optimized approach and let's build some intuition for that. Let's see some observation. The first observation is that let's suppose the array elements are 12, 10, 9, 8, 7. Okay? 0, 1, 2, 3, 4. If let's suppose these were the elements, what is going to be the answer for them? What's going to be the answer for 12? -1. Nothing is on right. For this, -1. For this, -1. -1. -1. Does that make sense? The answer for all of them will be -1. Now let's talk about another example. Let's say we have 5, 4, 3, 2 and 10. Now can someone tell me what is going to be the answer for 5 now? For 5 it's going to be 10. For 4 it's going to be 10. 3, 10, 2, 10, 10 minus 1. Does that make sense, guys? Cool. So the thing is that as you can see, when the sequence was in decreasing order, we got -1 for them. And here we also had a sequence in decreasing order. But once we got an element which was greater than them, so this element was greater than these elements, So the answer for them became 10. The answer for them became 10. Look at it like this. So let's suppose I have a 5, 4, 3, 2, 10. So I start from here. This is 5, then this is 4, this is 3, this is 2. Now 10 came. So once the number came which was out of order and greater than them, so answer for them became 10. Okay, answer for them became 10. Let's look at one more example. We have 9, 6, 5, 4, 8. So this is 9, this is 6, this is 5, 4, then 8 came. So 8 is 8 to whichever element it is greater, it will become the answer to them. That is here. So this is 9, this is 6, this is 5, this is 4, this is 8. So 8 will become the answer for 6, 5 and 4. Okay? So basically now once we have got the answer for them, can I just ignore this and start by finding the answer for these now? Does that make sense? Does that make sense? Okay, giving you some intuition that here we are also ignoring whatever was redundant from the past. The idea here is that we have a monotonic sequence. We have a monotonic sequence over here. Monotonic sequence is when we have a decreasing or increasing sequence. So my point is that I had a decreasing sequence. Once I find an element out of order, so all the elements which are smaller to this will be the answer for them. This will be the answer for them. Okay? Now, so basically, let's say I have elements 11, 4, 3, 2, 10, 12. So I have 11, then I have 4, then I have 3, 2, 11, 4, 3, 2. Now 10 comes. Now 10 comes. So 10 is greater than these numbers. So answer for these will be 10. Answer for these will be 10. Now since we have got the answer for them, we can actually remove this. We can actually remove this, and now it will become such a sequence. It will become such a sequence. Now 12 comes. So this will come over here. Now whatever is smaller than answer to them, 12 will become the answer. So 12 will come over here and 12 will come over here. Now only. So we have got the answer for them. So we will remove it. And now we are just left with 12. We have completely iterated the array, and whatever we are left with, to them the answer will be minus 1. Minus 1. Okay. So since we are ignoring whatever is redundant to us previously, and since this is a monotonic sequence, therefore stack will help us over here. So let's see the dry run using stack. So intuition was that we had to look at the just past, removing this just past. So whatever answer we had got, we will just ignore them, and now we'll start again from some monotonic sequence like we did over here, over above, right? Okay, so now let us go through the dry run using stack. Then again, if you guys will have some doubt, we will come to those. Okay, so I have 11, put it onto the stack. So 11 has been put onto the stack. Then we have 4, put it onto the stack. Then we have 3, put it on top of stack. Then we have 2, put it on top of stack. Then we have 10. Now this, you can see that this is a decreasing order. This is a decreasing order. Now we found an element out of order. So to whatever elements 10 is greater, the answer for them will become 10. So is 10 greater than 2? Yes. So we found the answer for 2. Answer for 2 is 10. Remove it. Is 10 greater than 3? Yes. We found the answer for 3. The answer for 3 becomes 10. Remove it. Now is 10 greater than 4? Yes. So we found the answer for 4. The answer for 4 becomes 10 and simply remove it. Now is 10 greater than 11? No. So simply push 10 onto the top of stack and move ahead. Now we are at 12. So on top of stack there is 10. 10 is lesser than 12. So answer for 10 will become 12, right? Answer for 10 will become 12. Now, so we are at 12. Is 12 greater than 11? Yes. So answer for 11 becomes 12. Okay? So now nothing is there. Simply insert 12 on top of stack. Now move ahead. So we are done. We are left with no more elements. So whatever is present on top of stack, the answer for them will become -1. So in this case, answer for 12 is -1. Guys, does that make sense? So Anshul says that then in this solution, we need to also store index and stack. Anshul, that's what we are going to do. We actually need to store indexes on top of stack because we actually are trying to find the answer for the previous elements that we are done with. So let me quickly show you a dry run of how we can do this using indexes. Okay. So we are having the stack. We will place 0 over here. Then we will place 1, right? Then we will place 2. Then we will place 3. So basically still the array is in decreasing order. Now we found 10. So this 10 is greater than what is present on top of stack. So basically answer for this. So we will write it like this. We will write it like this, s dot top. Okay? Because this is the index. So a of 3 is nothing but 2. So 10 is greater than 2. Answer for this has become 10. Then likewise, answer for this will become 10. Element at index 1 is 4, which is lesser than 10. Answer for this becomes 10. Now 11 is not smaller than 10. So we will simply push the index of 10, which is 4. Then we are here. Now this is 12. 12 is greater than a of s dot top. So we will simply mark the answer of a of 4 as 12. So this is 12. Again, so as we remove it, then a of 0 is lesser than 12. Answer for a of 0, that is 11, will be 12. And now whatever is present on stack, whatever is present in stack, you will simply mark their answer as -1. So you will put -1 here. And the time complexity of this approach is order of n. Since we are putting an element and removing an element just twice, so again order of 2 into n, which is nothing but n. And space complexity in the worst case can be, when let's say the complete array is in decreasing order, it will be order of n. So does that make sense to everyone? Okay guys, so we have actually placed the link to the questions for the next questions. Okay, so hope you guys try it. And guys, this was it. I hope you enjoyed it. And if you enjoyed it, please like and subscribe and share this with your friends as well. Okay, cool. Please try them.
Okay, so today we are going to study a very important data structure. This is going to be very handy, which can reduce the time complexities of many problems significantly just by adding a little bit on the space side. Okay, and this is called a hash map or a hash table. Okay, and the whole process is called hashing. In today's class, we are going to study some basics of hashing, how a hash table functions, and we'll also discuss some problems which have been asked in the interviews, and we'll see how you can solve these problems optimally using a hash map or hash table. Okay, I have a question for you guys. Have you ever encountered hashing in your real life? Hashing, have you ever faced any practical scenario where you have used hashing? Let's talk about those days when there was no corona, or let's call it the pre-COVID era. Let's talk about the pre-COVID era. So during the pre-COVID era, we used to go out on holidays, right? We used to go for trekking. We used to go to visit different places, right? And whenever you go to a different place, you need to stay in a hotel, right? So let's say that if you go to a hotel and if you want to look for a room, right? You go to the receptionist and ask whether a room is free or not. Now the job of the receptionist is that he will take all your preferences. He will ask you what type of room you want. And then based on your preferences, he will just check whether a room of those preferences is free or not, right? So you go to a hotel, and in this hotel, you have a receptionist, right? And you go to the receptionist and you ask for a room. Give me a room which, let's say, is a single bedded room, has a AC, has a balcony and all, right? And this guy will just check whether a room is free or not. Now, this guy has got two ways to check the room. First is that he can actually go and he can visit all the rooms of the hotel and check whether such a room is present or not, right? He will go, he will knock each and every door, he will check whether the door is closed or whether the door is open, whether the key is with him or whether the key is with the person who has taken the room, right? So this is one way. Now, as all of you can see, that this is a very, very unoptimized way of finding a room, right? Because if there are let's say 200 rooms in this hotel, if this is a very big hotel, then he is going to check each and every room for each and every customer, right? So if there are n customers and if there are m rooms, then how many checks is he going to make? This unoptimized receptionist is going to make n into m checks. This is not going to be profitable for the hotel business. Whoever is the owner of the hotel, he will fire him the next day, right? The other way that this guy can use is he can maintain a map, right? He can just against each and every room, right? Let's say room number 101, 102. He can maintain whether this room is occupied or whether this room is empty, right? Or he can also have the keys in the key holder itself. He can also have the room number written, right? So now whether he has the key or not, that is also visible here. Whether the room is empty or not, that is also visible here. He can also have the type of the room written here. So he can have that 101 is a single bedroom which is empty. 102 is a single bedroom which is non-empty. Let's say 202 is a double bedroom which is empty, right? So he can have each and every information regarding the room stored against the room number. Okay, is this going to be a better choice? Yes, right? That is why each and every receptionist actually does this. You must not have seen any receptionist who actually go and check all the rooms, right? But this is something which you all must have seen, correct? Let's talk about another example. Okay, so let's say that in those days we also used to go to shopping malls, right? So this was an example when we want to stay on a hotel. Another example would be that if I want to go to a shopping mall, okay? Now, if I want to go to a specific shop in the shopping mall, again, there are two ways that either I go and check each and every shop in that mall, right? So there are going to be multiple floors in that mall, right? Each floor will have different shops, right? And let's say I'm looking for a specific shop, okay? Let's say I want to buy the magical drug Coronil, okay? I have a perception, I have read on WhatsApp that if I take Coronil, then Corona is not going to catch me, right? So what I would want is, I would want to search this shop which is selling this drug Coronil, right? Now again, I have got two ways to do this. First is that I go to each and every floor and I check each and every shop one by one, right? Or some of the malls who have a logical owner or who have a logical management, what they do is they put a board or a map of the mall, right? So what they do is they put shop number, they give the complete address of the shop, floor wise. They will say that in the first floor, these are the shops which are there in this order, right? And in the second floor, these are the shops. So what I can do is I can use this map and I can find the exact location of that shop, and then I can go to that shop, buy this drug, and then I can make sure that Corona is not affecting me. But since this was a knowledge that I gained from WhatsApp, this might not be true, right? But this way of searching the shop, this definitely is a better approach, right? Instead of visiting each and every shop, what I'm going to do is I'm going to check this map and then find the exact location of the shop. Okay, does this make sense to everyone? These are two examples which all of you must have used, like these or something like this in your real life, right? Where you have to keep track of things and you just create a table or you create some entries and you just mark true false, or you just the attendance register that we have that we used to have in our school classes, right? That was also an example of hashing. If let's say a teacher wants to know whether a student is present in the class or not, right, what he will do is he will just do a linear scan on all the students. And doing this linear scan while taking the attendance, he also marks the attendance, right? So if there are students, let's say in our class, we have Aman, then we have Monica, then we have Anmol, right? So if I have to check whether all of these guys are present in the class or not, what I can do is just before beginning the class, I can just mark their attendance, right? Now, if let's say after some time I want to know who all were present in the class, I will not do another scan. I will just check whether Monica is present, whether Aman was present or not, right? So this again is another example of hashing which we have been seeing from the school days, right? Okay. Is Oyo also used concept of hashing? Yes, Oyo must also have used this same concept, right? Okay, so this is the general idea of hashing. Now let us see how it actually functions in the world of computer science. Okay, so let's try to understand this whole process using an example. So let's say that we are given an array, and this is just to understand how hashing is going to function. Okay, this is going to be a very easy example to understand the working of hash maps and hash tables. Okay, so let's say that you are given an array. And in this array, you have all the numbers from range 1 to 1000. So you know that any number in this array is going to be from, or let's say from 0 to 1000. Okay. So you're given an array of size n, and each and every number of this array ranges from 0 to 1000. Okay. You have to return the frequency of every number. Let's say you have got queries about the numbers. Okay, so you have this array and now you are getting multiple queries. You have to answer these queries, and each query asks you the frequency of a number. Okay, so for example, if the array is something like this, okay, if this is the array, after getting this array, you will get multiple queries, and you have to answer what is the frequency of the given number in that query. So for example, if your query has 58, you will return 1 because 58 occurs only single time. Then if let's say you get 3 in the query, then you will be returning 2 because 3 is occurring twice in this array. If you get 2, you will again be returning 2 because 2 again occurs twice in the array. Okay, is this scenario, is the problem clear? How can we solve each and every query in the most optimal time? Okay, let us start from the brute force. Okay, what is the brute force way to solve each and every query? The brute force way to solve each and every query is that whenever you get a number in the query, you iterate over this complete array and you count the occurrences of that number, right? So if I get 58, I will do an iteration over the complete array, which is going to be an order n operation, and then I will return 1. If I get 3, I will again do another order n operation over the complete array, and I will return 2. Okay. So what is the total time complexity of, if I go by this approach? Let's say there are q queries. Solving each query takes order n time. So the total time complexity is going to be q into n. Right? Now this q can be very, very large. Okay. So this is something which is not optimal, right? Any other approach that we can use in this case that you might have studied in the previous classes? Can we optimize this order n factor here? Let us say if I do some pre-processing, okay? If I sort the array, what happens to the order? Now the order is, the array sorted in ascending order, right? Now can I find the frequency in a more optimal time? Can I reduce this factor of n? Yes. Now how can we count the frequencies? Now we can use binary search. You must have studied this, you must have learned it in the previous sessions, that given a sorted array, you can count the number of occurrences of any element using binary search, right? You can just find what is the first occurrence of that number using the binary search. Then you can also find what is the last occurrence of the number, and then you can get the length of this subarray, right? So if you use binary search after sorting, then each and every query is going to take how much time? Only log n time, right? So now what is the total time complexity of finding all the frequencies? So if you have q queries, then solving all the queries is going to take you q into log base 2 n time. This much is the time that you will invest in resolving each and every query. But before this, you have also sorted the array, right? So that amount will also be counted. Now, whichever is the greater of these two will be the overall time complexity, right? This still is a lot because again, n can be very large, q can also be very large, right? So can we further optimize this? Right, so as many of you have already suggested, what if I have another array, right? So I can see here, if I focus on the constant of the problem says that any array value is going to be in this range strictly, right? Any array value cannot be more than 1000 and it cannot be less than 0, right? What if I just have another array where each and every index of the array represent the numbers and the value in the array represents the frequency of a number in this original array? So what if I have another array and just call it a frequency array, right? And store and count the frequency of each and every original array element in this array, right? So I can have another, let's say, frequency array of size. What should be the size of this array? What should be the optimal size of my frequency array? If I know that all the numbers are going to be in the range from 0 to 1000, I know that the maximum number that I can have is 1000. To have 1000 as an index, I need an array of size 1001, right? 1001. This array is going to be, this array can accommodate all the numbers from 0 to 1000 in index, right? So now what I will do is, whenever I am iterating over this array, so initially I initialize this complete 1000 sized array by 0. So in this array, initially I have 1000 zeros in every index, right? And then whenever I visit a number, I will just loop over this array. And whenever I visit a number, I will increase the value here, right? Because this denotes the frequency. So initially I am assuming that frequency of each and every number is 0. Whenever I encounter a number, I will increase the frequency, right? So I will just loop over this array. I will say for I equals to 0, I less than n, which is the size of the given array, I plus plus. And I will say frequency of a of I plus plus, right? If I just do this, what will I get? In this array, frequency of 1 will be increased to 1, right? And then frequency of 2 will also be increased and it will be 2. Frequency of 3 will also be 2, and so on, right? So now, after I have built this array, if I have to return what is the frequency of any given number, right? What is the operation that I have to do? After I have built this array, for any number I, for any given number I, if I have to return what is the frequency is nothing but frequency of I. So if I have to return what is the frequency of 58, I will quickly do frequency 58. If I have to return what is the frequency of 2, that is going to be frequency of 2. And that's it, right? So what is the time complexity of this operation? Time complexity of this operation is constant, right? This is a constant time operation. I'm just retrieving a value from the array, right? So this is going to take order 1 time, correct? Now I have q queries and each query is being solved in order 1 time, correct? So what is the overall time complexity of solving all these queries? Overall time complexity becomes order q, because each and every query is taking how much time? Only order 1 time, right? So this is the time to resolve each and every query. And then we have also built this array, right? So we have iterated over the given original array, and then we have also built that array. So this takes order n time, order n plus q, whichever is greater will be the final time complexity. Okay, does this make sense to everyone? How we have solved this, like optimize the time complexity from n square to n log n plus q log n to order n plus q. Okay, now one of you just asked what happens when array elements range from 1 to 1 raised to power 10 raised to power 18. Okay, what if, so in this problem, it was given to us that the numbers are going to range from 0 to 1000. That is the reason why we are able to create an array, right? I can create an array because I know that indexes can be in this range, correct? Now, what if the numbers are going to be very large? Okay, A of I, as asked by Lucky Movies, what if the range is this? Can I use the exact same approach? So now I cannot use the exact same technique because I cannot have an array, I cannot create a frequency array which has a size 10 raised to power 18, right? Because this is going to cost me a lot of memory, right? How much memory is it going to cost? If this is an array of integers, one integer takes how much memory? 4 bytes, right? So if you want to create an array of size 10 raised to power 18, this is going to cost how much time? How much memory? 4 into 10 raised to power 18 bytes. Can anyone quickly tell me how much is this in GBs? 4 into 10 raised to power 18 bytes. How much is it in GBs? So if you want to create an array of that size, you need to have this much of memory. You need to have this much of memory in the RAM, right? So this much of memory in the RAM is definitely not going to be possible for an ordinary computer, right? So what we are going to do is, now we'll have to be a little more logical and we'll have to apply a little more mind, right? Unlike Mumbai police. So let us be a little more logical and let us try to see if we have an upper limit on the memory, right? If let us take a smaller example, and let's say that the numbers are ranging from, just to understand, let's take the smaller example that the numbers are again ranging from 1 to 1000, but the largest array that I can have a size of 100. This is the upper limit on the size of array. Okay, similar example. So what we are doing is, numbers are ranging from 1 to 1000, but the maximum size of the array can only be 100. Right? Now again, I cannot use the exact same method. Why? Because having an array of size 1000 is not possible, right? So if I want to store the numbers as an index in the array, then I can only store till 100. Is there a way using which I can map all these numbers from in this range from 0 to 99, because the maximum size that I can have is 100. So can I map all these numbers in this range? Is there a way? Have we seen any way? Or let's say that all these numbers are ranging from 0 to 1000, right? Yes, what can we do? We can simply take modulo, right? Is everyone familiar about what is a modulo operator? This gives you the remainder, right? So if I take modulo of any number ai with 100, which is the maximum size of the array that I can have, can I say that this number, which is ai modulo 100, will always lie in the range from 0 to 99? Can I say this? Yes, correct. So I have got one way to map these numbers which are in this range from 0 to 1000 to a range which is very, very small, right? This range has a length 1000, 1001, and now the resulting length is only 100. So I'm mapping these 1000 numbers to 100 numbers. Okay. If this is the case, how am I going to store the numbers? Let's have an example. Let's say I have 492, 5, 8, 23, 15, 142, and some random numbers. Okay. And now if I can only afford an array of size 100, right? How can I map these numbers? I will first take the modulo of these numbers with 100. And then whatever number I get by doing this operation, I will store these numbers in that index. So I get the index by taking modulo of these numbers by 100. So first number will be stored against index 92. This will be stored against index 5. This will be against 23, 15, 42, 54, and 64, right? So if I have these as the array index, 54 and so on till 99, Then at 0 is going to be empty, 1 is empty, 2 is empty. At 5, I am going to have 5. At 23, I will be having 823. At 42, I will be having 142, and then 654, 764, and so on, right? So now, is this going to work? Is this going to work correctly? If these are the indices and these are, and I keep the values in array element mod 100 index. Okay, now some of you are saying that this is going to work, but there can be collisions, right? What are collisions? Okay, so let us say that in the array, in the original array, I have these numbers 100, 201, then I have 302, then maybe 300, 401, 200, right? If I have these numbers, right? So in which index should a number belong? In index 0, how many numbers am I going to have? In index 0, I am going to have 100. Then I am also going to have 300, and I am also going to have 200, right? All these numbers will try to get inserted against a single index, right? These are called collisions when there are multiple prospects candidates for a single index, right? So index 1 will try to accommodate 201, then 401. Index 2 is going to have 302, and then 2 also, right? So there is no one-to-one mapping, right? A one-to-one mapping does not exist, correct? If a one-to-one mapping does not exist, is this even possible to use this technique? Are we going in the wrong direction? Is this a correct way? Is this the correct path that we are taking? Maybe, right? We have also studied a data structure called linked list, right? If you know about a linked list, what if we have an array of linked lists? If I keep an array of the linked list nodes, right? Can I say that this can work in that case, right? So currently, if you are only storing a single element, if you are only trying to store a single element against one index, then since there is no 1:1 mapping, this will definitely fail. We are going to lose some data, right? Because every time you have a collision, the previous number will be overwritten. But what if I use a linked list? So instead of having these integers, right? If at index 0, I have this complete linked list stored. So if I have to create an array of linked list, what do I need? I only need the pointer to the head stored in that correct index, right? Only if I have an array like this where I have this head pointer, then using this head pointer, we can have the complete linked list, right? So we don't need to actually store this complete linked list in the array. We only need to store the head pointer, right? Similarly, at index 1, we can have the head pointer of 201. At index 2, we can have the head pointer to 302. Does this make sense to everyone? So we can still manage doing hashing in this case. Even though the range which we have to store is very large, the size of the array is very small, but we are making sure using the modulus operation that we are mapping these numbers to the available size. And then using a linked list, we can also make sure that we are not losing out any data, and we are storing all these numbers using the chaining. Okay. Now, if I'm storing the values like this, now if I have to find what is the number of frequency, or let us say if I just want to check whether a number is present or not, right? What is the worst case time complexity of this case? If I'm going by this approach, if I'm storing linked list, if I'm having an array of linked list nodes, what is the worst case time complexity of finding whether a number is present in the array or not? Worst case is going to be if all the numbers are mapping to a single index, right? So if let us say that the numbers are these 1, then you have 401, then you have 101, then you have 601, right? 701 and 501, correct? If I take mod of all these numbers with 100, all of them are going to take the exact same key. So all of them are going to map against 1. So what will happen now? If I have to search whether a specific number is present in this array or not, I will be traversing this complete linked list, right? So first, let us say I get a query. I get a query of, let's say, 801. I have to check whether this number is present or not. So first of all, I will try to see in which index is this number is stored. So I will just do 801 mod 100, which is going to be 1. So I go to index 1 of my array. And now I have a linked list of size n. I will iterate over this linked list, and since this is also not in sorted order, right, I will have to check each and every element, and I will then figure out whether I have 801 or not, right? So this is going to be a order n time complexity operation. Does this make sense to everyone? This is the worst case time complexity of checking whether the number is present in this list or not, right? Okay, so this is the worst case. What could have been an ideal case? When can I say that this is the best thing that I want? What is the ideal case in this scenario? The ideal case would be that if all the numbers are mapping to different index, if all the numbers, if I have a data and like if I have the data in such a way that all the numbers are distributed evenly amongst all the index, right? So if I, let's say, have 401 against 1, then I have 2. So let's say I have 702, and then I have 23, so I have 823, and I have exactly one element for each and every index. This is going to be the ideal case. And what is going to be the time complexity in this case of just finding whether a number is present or not? Since the list size in each and every case is exactly 1, the time complexity is going to be constant, right? So this is the best case time complexity, and this is the worst case time complexity. Is everyone clear about these two? Okay, great. So the aim is that the mapping function that we are using, right? Currently the mapping function is mod by the size of the array, right? So the aim should be that whichever mapping function we are using should try to evenly distribute the load amongst all the possible indices, right? So this function, the mapping function that we are using, this is called, what is it called? Anyone knows what is the name of this function? This is called the hash function. Okay, and hash function is a very, very big topic in itself. There is a lot of research going on. There has been a lot of research already done on what could be a better hash function or for what case, right? So you can just go and Google and read about hash functions. There are multiple publications on these. You can read, you can go through some of the publications if you're interested, right? But taking a mod, this is the most simple hash function that you can have, but not the most optimal. Right? This was just for the example. You have very complex, very optimally written hash functions which try to distribute the load evenly. Okay, so you can just go back and read about what are hash functions, and you can also read about some of the common hash functions. Okay, cool. Now, if I write one of the best hash function, even which is the best possible hash function currently present in this world, can I say that hash function will guarantee zero collision? Can there be any hash function which can guarantee zero collisions? No. Why? Why no? You have got a very big range of numbers, right? You have to map numbers from, let's say, 0 to 1000. You have got only 100 slots. Do you guys, are you aware about the pigeonhole principle? You have 100 slots and you have to put 1000 things. When you put the first 100 things, and if your hash function is guaranteeing zero collision, 100 slots are filled, right? Now when you pick the 101 index number, this is definitely going to collide with at least one of the pre-existing slots, right? So since you are mapping a bigger list of numbers to a smaller list, you will always have collision. So there cannot be any hash function which can guarantee zero collisions. Okay. However, there are hash functions which try to distribute the load evenly. That is possible. There has been a lot of research done on that. You can Google and read. Okay. Cool. So this is the basics of hashing. Right? You can read about hash functions. You can also read about hash tables. Hash table is nothing but key and value. right? So you must have seen what is a dictionary. If you use Python, you must have used hash maps. So hash maps or hash tables, they are nothing but a key value pair. This key is the result that you get from the hash function. This is a hash code of any value, and in the value you can store anything, right? So the key, as you all now should understand, these keys in this case are the index from 0 to 100, right? So keys are always and always going to be unique. Values can repeat. You can store the values in list or maybe in some other data structure, but keys are always going to be unique. Okay. Now there was a question that if you are using a list, is there any specific reason of using a list, or can we have any other data structure here? What do you guys think? Can we have any other data structure in place of list? So Surit is asking why we use linked list. Is there any specific criteria? Correct. So Komal has got a good solution to that. If I'm using a list, what is the worst case time complexity of searching a list in if you have a list which is not sorted and which is a linear linked list, what is the worst case time complexity of searching in this list? Worst case time complexity of searching in list is order n. Okay. Now, do we know any data structure which provides a better searching time complexity? Is there any data structure which can store the numbers maybe in some order and then can give us a better time complexity? Do you guys know about binary search trees? In a binary search tree, all the values on the left subtree are going to be less than or equal to the value of the root. All the values of the right subtree are going to be greater than the value of the root, right? So just by using a technique like binary search, it can always discard, while searching for a number, it can always discard half of the search space, right? So what is going to be the time complexity to search a number? It's going to be log base 2n. If you are using Java 8, if anyone of you who is using Java 8 must know this, that in Java 8, they optimize this worst case time complexity of retrieving from a hash map using a balanced binary search tree. In a normal binary search tree, in worst case, you can also have a time complexity of n if the tree is skewed. But if the tree is always balanced, then you are always going to have a searching time complexity of log base 2n. So in Java 8, what the hash map does it, if the size of the list is till a threshold number, which I don't remember correctly, I guess it's 5 or 6, till then it maintains a list. If the size exceeds the threshold value, then it converts the list to a balanced binary search tree. So the worst case time complexity that we have seen to be order n will reduce to order log n. Okay, cool. So guys, this is in brief about hash maps and how they work. Okay, let us quickly solve a problem also. Okay, in which type of questions can we blindly use hash functions? Okay, in any question where it talks about the frequency or counting the numbers or maybe checking whether a number is present or not, or checking the presence of anything, then you can use hash function, or then you can use hashing. Okay, let's quickly solve a problem and then you will get a better idea of when to use hashing. Okay, so the problem says that you are given an array and you have to check whether there exists a subarray which has sum equals to 0. Okay, so for example, if your array is this, in this case, does there exist such a subarray? Yes, right? If you see the sum of this subarray, what is the sum of this subarray? Is exactly 0. So you can return true. If there exists a subarray which has a sum equal to 0, the subarray can start from any index, it can end at any index, it can have any length which is possible. But if there exists any type of subarray which has sum equals to 0, then you can return true, else false. Okay, modify cadence algorithm. Okay, how will you do that? Remember that the subarray can start from any point. This subarray is starting from this point. There might be an input where your subarray which is causing a zero sum can be present, let's say here, or the subarray can be present here, or maybe the complete array can also be the subarray. What is the brute force way? If you are not getting any solution, can you quickly write down what is the brute force way? Okay, the brute force way is going to be that you actually try to calculate the sum of each and every possible subarray, right? So you first check all the subarrays of size 1, then you can check all the subarrays of size 2, then you can check all the subarrays of size 3, and so on, right? How many subarrays are possible? N square subarrays are possible. To calculate the sum, what is going to be the time complexity? For every subarray, you will also run another loop to calculate the sum. So it's going to be an n cubed solution, right? Which is highly unoptimized. How can we come up with an optimized approach? And we have also studied hashing. Hashing doesn't seem to contribute in this question, right? Okay, let us assume that there exists a subarray. Okay, there exists a subarray which has got sum equals to 0. Okay, so let us say this is the initial array that we have, and there is a subarray, let's say this part, which has a sum equals to 0. How do we define a subarray? We always define a subarray using a range of indices, right? Because as I said, the subarray can start at any point, it can end at any point, right? Let us say it starts at a point L and ends at an index R. And I'm saying that we are just assuming that the sum of this subarray starting from L to R is 0. Okay. Now, if this subarray has got sum equals to 0, right? If I also have the sum of all the subarrays starting from 0 stored with me, okay, what can we say about this part? This part which is in the blue dotted line. What is going to be the sum of this part? The sum of this part is nothing but sum from 0 to R, right? And this sum from 0 to R can be broken down as sum from the range 0 to L minus 1, right? Plus sum of the range from L to R. Does this make sense to everyone? Right? So sum of any subarray can actually be written in terms of this prefix sum, right? I can write sum from L to R is equal to sum from 0 to R minus sum from 0 to L minus 1 index. I can write the sum of any subarray which starts at index L, ends at index R in the form of the sum of subarray starting from 0, which is nothing but the prefix sum. Everyone here understands what is a prefix sum, right? So if I have a prefix sum array P, then I can say that the sum of the subarray starting from and ending at R is nothing but P of R minus P of L minus 1. Does this make sense to everyone? Prefix sum is nothing but, prefix sum is the sum of all the indices till that index. So if I have an array, right, prefix sum at any index I is nothing but, it is the sum of all the elements including the I and all the elements before the I. Okay. So if let's say I have an array 1, 2, 3, 4, the prefix sum array would be 1, and then this will store the sum of these 2, is 3, then this will store the sum of all of them, which is 6, and then this will store the sum of all of them, which is 10. So this is the prefix sum array for this array. If I have all these numbers stored with me already in this array prefix, now I can represent the sum of any subarray in the form of prefix sums, right? And if I'm saying that this sum is equal to 0, if this sum is equal to 0, can I make any comment about these two values? If this sum is equal to 0, this means that prefix sum of R should definitely be equal to prefix sum of L minus 1, right? Let us visualize this in this diagram and then it will be more clear. So I have these two parts, right? Now I am saying that this blue box represent the prefix sum of R. This is the sum of all these elements from 0 to R. Okay, this green, this yellow box, this represents the sum of all the numbers in the range L to R. Correct? And what about this green box? This green shaded box represents the prefix sum of the index L minus 1, the sum of all these numbers. Can I say that if this is going to be 0, right? If I'm adding the sum of all the index from left to right, and if this part is equal to 0, then whatever sum I get at this point, the exact same sum will also be present after this, because the contribution of this is 0. Does this make sense to everyone? Right? So if I have an array, right, and if I'm just calculating the sum of all the array elements till that index, and then there is a part which is contributing exactly 0 amount, right? So this will give some sum, right? Let's say S, this gives S dash, and then if I add this as well, this gives S double dash, this gives S triple dash, and then this gives something. After I'm here, I will again get S triple dash, because the overall sum of this part is 0. Does this make sense to everyone? Let us take the example as well, and then this will be crystal clear. So I will just copy this thing. So if I just calculate the prefix sum of this array, I will be getting 4, right? 6 minus 3 again is 3, then 4, and then 10. Okay. Now what I was explaining is, since the sum of this part is exactly 0, this part, the contribution of this part in the sum of all these numbers is going to remain 0, right? That is why whatever number I am getting here will also be repeated here, right? So whatever sum I am getting at this point, which is, this point is L minus 1, right? Because I am assuming that this subarray starts from L. So the previous is L minus 1. And this is the R. These two have to be equal. If these two are equal, this means that this subarray, the contribution of this subarray was exactly 0. All the values cancelled out each other, and we are remaining with whatever we had before starting this subarray, right? So how can we now solve this problem? If we calculate the prefix sum of the array, and then if we observe that there is a number repeating in the prefix sum, can I say that the contribution of all the elements between these two numbers is going to be 0, which means that this subarray is adding to 0. Okay, is the idea clear to everyone? Guys, is the idea clear? Right, let's take another example. Let's say I have 4, 2, 0, 1, 6. Okay, now if I take the prefix sums, I will be getting 4, 6, then again 6, and then 7 and 12. So again I can see that a number is repeating in the prefix sum, which means that whatever comes in between these two, this is, if I said that first number should be L minus 1, this is L minus 1, right? And this number is R. So whatever is from L to R is going to give me a sum equal to 0. L to R here has exactly one element, which is 0. Now one of you asked, what if same number is repeating twice, right? That can also be possible. You will have to understand what is the physical significance of this thing, right? So even in this case, if I just modify this array, here I got 4, then I have 0, then let's say again 0, then I get 2, and then minus 2, and then something, right? Now what will be the prefix sum here? Again 4, 4, 6, again 4, and then 5, right? So this means that all these numbers which are repeating, they all are forming a subarray which is going to give a 0 sum. If these two are repeating, this means that we have a sum 0 here. If these two are repeating, this means we have a sum 0 here from this plus 1 to this, right? Because this has to be the L minus 1 index. So even if you have multiple repetition, that points to only one thing, that the subarray between them is giving a 0 sum. Okay. Now, how do we solve this problem? So one thing should be clear to everyone, that the first step is that you create the prefix sum array. How can we create the prefix sum array? This is very easy task. You can have P0 equals to A of 0, because the first number is going to be exactly the same. And then for building the rest of the array, you can just keep calculating. You can just keep adding the current value to the previous prefix sum, right? Prefix sum of I is nothing but the previous prefix sum, whatever is the sum till now, plus whatever is the sum of the current element. So now we can run a loop from I equals to 1, I less than n, I plus plus, and then you can say P of I is equals to P of I minus 1 plus A of I. This gives you your complete prefix sum. Now in this prefix sum, you just have to check whether there are two numbers which are repeating or not. Is there any data structure that we know which can solve this problem very optimally? You just have to check whether there are two numbers which are repeating or not. How do you check for a repetition of a number? You can have a hash map, right? Maybe you can have an integer here and a boolean, right? When you get 4, you store true. When you get 6, you store true. When you get another 6, you know that 6 has already occurred. If 6 has already occurred, this means that there is a subarray which is giving a zero sum. If you also want to find what is the length of the subarray, instead of having the boolean, you can try to store the index here. This also becomes integer, and now you can say that 4 occurs at index 0, 6 occurs at index 1, then 6 again occurs at index 2. This means that from this index, this plus 1 to 2, we have got a subarray which is giving us sum equals to 0. Okay, let's take this example which we initially had, this one, right? You can have your key and value. Key is the sum, value is the index in the hash map. You get 4 sum at index 0, then you get 6 sum at index 1, 3 at 2, and then you again get 4 at index 3, right? Now we had discussed, right, that keys are going to be unique. So once you get another same key, you can just check that this key is already present in the hash map and the starting index was 0. This means from 1 to 3, I have an array which is giving sum equals to 0. Okay, does this make sense to everyone? What is the time complexity of this complete problem, of this complete algorithm? First of all, we have calculated the prefix sum. This costs us order n. While calculating the prefix sum only, you can just also enter in the hash map, right? Here only, what you can do is you can do your map dot put, or first maybe you can check if map dot contains pi. This means that you have found a subarray, you can directly return true, right? Else you can say map dot put pi and comma whatever you are storing, whether it is index or whether it is your true or false, right? And this is going to solve the problem. Overall time complexity here is order n. Okay, so guys, I will now end the session. Please do solve all the problems. Thank you guys.
Hello everyone. So today we have the topic as hashing, and I am Paridhi. I am a software developer at InterviewBit. So today I have selected two questions basically that I'm going to discuss here, and it's basically how important they are from interview point of view. So I have selected them, and so today we are going to do first question is anagram. So let's quickly dive into that. Okay, so today we are going to do our first question, and that problem is anagram. This is a very famous problem. This has been asked in Amazon, Microsoft, Goldman, as you guys can see. Very important from the interview point of view. Let's quickly see what it says. Okay, so given an array of strings, return all groups of strings that are anagrams. Okay. So represent a group by a list of integers representing the index in the original list. Fine. So we are given a group of anagrams, and basically we have to group the anagrams together. Okay, so let's see the example for clarification. First of all, what is an anagram? So it's a word, a phrase or name formed by rearranging the letters of another, such as spar is there, formed from rasp. Okay. So basically, anagram is a word in which two strings can be said as anagrams if they have same characters, right? And the frequency of the characters is also same, but their order is different. Okay. So here, as we can see, that S is present in spar and S is also present in rasp. Then P is present in spar and P is present in rasp. Likewise, A is present in spar and A is present in rasp, and R is present in spar and R is present in rasp. Fine. And these are the only characters. So these characters are basically jumbled, right? So these are known as anagrams. Now, given the example, we have cat, dog, god, and TCA. Fine. So these are the anagrams, and we have to group the anagrams together, right? Okay, fine. So we have cat, and I can see that 1 and 4 are anagrams. That means cat and TC are anagrams. Okay, fine. They have same set of characters and frequency is also same. Makes sense. And dog is there and god is there. They both are anagrams. Fine, makes sense. So they have same basically characters and frequency is also same. Fine. Okay. So what do you think we can do? What is the first thing that comes to your mind? So what I can think of is that from these two anagrams as given in the example over here, the spar and rasp, right? They have same characters and also the frequency same. So maybe if I like sort them, they should give the same result, right? So if I sort spar, I should get the same result as if I sort rasp, right? Does that make sense? Exactly. So you guys have started to reply and you are on the right track that we can sort them. And after sorting, what is the thing that we are going to get? Let's see. So let me share my screen first of all, the notepad screen. So here we have, so in the example, we have, fine. So let me just copy it down. So we have cat, dog, and god and TCA. So I'm just copying it down on here. So, okay. So if I sort them, this will become ACT, right? And if I sort, so if I sort dog, I will get DGO, right? If I sort god, I will again get DGO. And if I sort TCA, I will, okay, so wait a minute, it just got auto-corrected. DGA, sorry, DGO, and this will also be BGO, and this will be ACT, right? So that means here we know that CAT, as in the example, CAT and TCA are anagrams, and when we sort them out, then ACT and ACT we have got the same string, right? Okay, that means anagrams will have the same string, makes sense. And likewise in dog and god, DGO and DGO, they have the same string. Now, what can we do to group them up? So as someone of you has have said that we can hash them up correctly. That perfectly makes sense that basically here the sorted string can act as a, so here the sorted string can act as the key, right? The key is the sorted string and the value are going to be the indices of the anagrams. Does that make sense? So here let's actually number them up. So we have 1, this is 1, this is 2, this is 3, this is 4, and we want the indices only, right? So indices are starting from 1 in this case. So basically the key here for CAT is going to be ACT, and here we are going to have the value will be a we can say a vector where we can store the indices of the anagrams. So ACT is a string and CAT is an anagram for that. So that means we can have in a vector we can have 1, and also this TCA is also, if we sort it up, we will get ACT, right? So that means the same string, and so the value is going to be 4 over here, right? So that means we have actually paired up the anagrams, the main task, right? Now the second string is DBO, right? And we can pair the strings that are forming the anagram. So that means 2 and 3. Does that make sense? So, right. We can do it in various ways. We can even hash them up in various ways. We can use frequency arrays as well. So you can do it in any way, right? So let's just code it up. So I think most of you are ready for this. Let's code it up. So here we have the screen and let's quickly code it out. Right, okay. So basically we will be keeping, first of all, we need a vector of vector for the answer thing, for storing the answer, right? So vector of int, and also we need the map, we need a map, unordered map. So we'll basically do int, comma, okay, no, sorry, not int, we need string, right? We need string and we need a vector of int. Let's call it maybe group, right? These are the groups. And now the task is that we have to basically iterate through the vector of strings that is given to us. So let's iterate through it. So I will go from 0 to a dot size, right? And I plus plus. Now, okay. So we will take the first string. Let's take it in. Let's say we will actually have to generate the copy of the string because we have to sort them up, and also we need the original string, right? So therefore we are maintaining a copy. So let's take it in here and this will create a copy. Now let's sort the string. So let's sort the copy string. So cpy dot begin, then cpy dot end, right? So we have sorted, and now the task is that we can actually hash it. So that's what we are doing. So let's hash it. So the groups is the map that we have taken, and this is copy, right? So string is copy that we have sorted. Okay, so we have sorted it, and let me see if there are some comments. Okay, so now what shall I do? May I get it in the comments? What shall I write? So basically I can push, if that copy is present, I can push the index value, right? So after sorting this copy string, the string at AI, if after sorting we get a string which is there in the hash, right, which is present in the key, we can actually push I plus 1 to that. It's exactly what we have done in our notepad, right? So we will do it for all the strings, and finally after doing it, we actually have to iterate through the map. Does that make sense? That we have to iterate through the map. So let's do it. Groups is the map. Iterator, let's say, is IT. Now we will simply move through it. So that means IT equal to, that is groups dot begin. Then IT is not equal to groups dot end and IT plus plus, right? So we have to just take the value, right? So here we have actually maintained an answer variable, answer array, and we have to basically push the entire vector that we have created in our answer, in the main answer, right? So basically we will be pushing back IT, that means the iterator dot second, and here we can simply return the answer array, right? So does this look fine? Please check, everyone. Are you guys coding with me? Yes. So basically for that, we are actually storing the indices only, right? So Nilesh, we are storing the indices only. We actually have taken the string in the copy string, that means the extra string. Then we have actually sorted this copy string, and here we need not maintain the main string. Basically we just want the index of that, right? So here we are pushing the index, right, just as we have seen in the notepad. So that's what we are doing. Let's try it now. Let's see if it passes. Oh, sorry. So this should be pushed back. Great. Let's see if it gets submitted. Cool. So we have done a good job, and we have scored 338 out of 350. Not bad. Okay, so have you guys got it? Have you guys got it? Are you guys with me? Is it clear? Shall we move to the next question, guys? Cool. Do submit it with me, right? Be here with me. Okay, so now let's do the next question of the day. And the next question is, so here I am taking the longest substring without repeating characters. So here is our question. Let's proceed to it. This question has been asked in Amazon, and not only Amazon, I have heard previously as in recently that it has been asked in various other companies as well. Can't remember the name right now, but yes, this is a very important question. So let's get to it. Okay, so Ashish says he has a question. In interview, are we allowed to use inbuilt function? Okay, so basically it's like when you are asked to implement something, which is, let's say you are asked to implement a substring function. In that case, you cannot use it. Or let's say you are asked to sort the array. So the trivial question is that, so the main question here is that you have asked to sort it. So how can you use a given the inbuilt function, right? In that case, you have to actually perform the sorting with the various algorithms you have. You can't use inbuilt function in that case, right? So here the question is different. You can use the inbuilt function in this case if it's not mentioned. If it's mentioned that you cannot use, then you cannot use, right? So it actually depends. You can actually ask your interviewer about it, that if you can use it or not. Make sense? Cool. Okay, great. So guys, let's move on to the next question. And the next question is longest substring without repeat. Okay, so let's see. So the question says that given a string, find the length of the longest substring without repeating characters. Okay, so here we are given a string. This is the string, let's say, and here it says that ABC is the longest string and the length is 3. That means ABC is the longest such substring in which there are no repeating characters. As you can see that, okay, ABC has unique characters. Okay, so basically we want a substring out of a long string which has only the unique characters, right? Which doesn't have a repeating character basically. In the second example, as you see that we have so many B's over here. And that means here the substring is just a B. That means of length 1, that has a unique character. If we try to extend this up, that means if we try to make the length 2, then definitely we will get BB, and length of 2 doesn't have unique characters. Does the question make sense to everyone? Okay. Could you elaborate more? That what would you do? Guys, please at least come up with the brute force approach. I would like to discuss it with you all, that what do you have in your minds? Can you guys think of the brute force approach for this question? Is the question clear to you all? Okay. So guys, please think on this question, okay? And then in a minute, we are going to proceed with the solution. Okay. So Garima says that please explain the question again. Sure, Garima? So here it says that you are given a string. Okay, you are given a string and you have to find the length of the longest substring without repeating characters. Now, first of all, do you guys understand what a substring is? So a substring is that when you take, so here if I say that this is a string, right? So what are the substrings of this string? So let me actually show you my screen. Cool. So here is my notepad screen, and let's remove this. So here we are discussing the longest substring without repeating characters. Okay, so let's say I have a string A, B, C, D, and or B, C. Okay, A, B, C, B, D. Now, first of all, what are the substrings of this string? So A is a substring, then AB is a substring, then ABC is a substring, ABC B is a substring, then ABC B is a substring. Okay, then starting from B, we have just B, then BC, then BCB, then we have BCBB, right? Then starting from C, we have C, then CB, then CB, C, B, D. And starting from B, we have just B, then BD. And then starting from D, we just have D. Does that make sense that these are the substrings of this string, the consecutive characters? Garima, is the question, so the question says that once. So basically you have to find the longest length of the substring that has unique characters. Here, such a longest length is just ABC, because if we consider any length which is beyond 3, then that has a repeating character. So if we have, let's say ABCB, right? So in this case also we have 2 repeating characters, as in 1 repeating character, that is B, right? So B occurs 2 times, which we don't want. So the question says that you have to find the longest substring without repeating characters. Am I clear with the question, guys? Am I clear with the question? Okay, great. Okay, so let me clear this up, right? Okay, so let me actually build your solution, then you will be more clear. Okay, so the brute force approach that comes to my mind is that we can generate all the substrings, right? We can generate all these substrings and we can check if these substring consists of unique characters or not, right? So how to check if a substring consists of unique characters or not? So basically for that purpose, we can maintain a hash map. What's it? So we can maintain a hash map that will tell us that if some character is already present in our string or not. Does that make sense? That we can use a hash map because it tells us in just order of one time that, okay, if some character exists or not, already exists or not, right? So this is the brute force approach. So does anyone know that how many total substrings we can create out of a string? How many total substrings are there? Okay, so total substrings are n into n, wait a minute, n into n plus 1 by 2. Okay, these are the total number of substrings that we can create, and where n is the number of characters in the string. Okay, now, so once we generate all the substrings, and then if we check with the help of a hash map that if that particular substring has unique characters or not, then the time complexity for, first of all, for generating the substring is going to be order of n square. Okay, because total we have n into n plus 1 by 2 number of substring, therefore the time complexity of generating these many substrings is order of n square. Now we also have to check it with the help of a map if it consists of unique characters or not. So for that, it's again going to take order of n, because why? Because for maintaining the hash map, it's going to take again order of n. So the total number of time complexity, the total time complexity is going to be order of n. Does that make sense to everyone? Cool. So the time complexity is going to be n cube, but it can be further optimized if, while going through our second loop, we can actually check on that pace only if we are getting the unique characters or not. So what I'm saying is that while maintaining the second for loop, in the second for loop itself, we can check that substring from I till j has unique characters or not. And this we can do in our for loop only, the checking part. We don't have to do it separately for checking the unique string. Okay, so then the time complexity will reduce to order of n square, right? Because here we will be doing it in our second for loop only. We will be checking it in the second for loop only. Does that make sense, guys? Is it clear now that why n square? So n square is because while generating a string, let's say I am at A, so the string is, wait a minute. Let's say the string is A, B, C, D, D, right? This is our string. Now, I'll keep my I pointer here, and initially the J pointer will also be here. Okay. Now, we will also maintain a map side by side, and we will put the character in the map that if, so for checking if it's unique or not. Right now in our map, A is not there, right? So we will put that, okay, A is not there. That means A is unique. Let's put it in our map. So first we will check that if some character exists in the map or not. If it doesn't exist, that means that character is unique. Once we get to know if that character is unique, then we can add that character in the map. Okay. So okay, now we have done it. So we have checked for string A. Now we will move. So now we have AB. So we have in the map, we just have A till now, right? Now we will check that if the character at B is in our map or not. If it's not present, that means it's a unique, right? That means it's unique. But once we have checked that if it's unique, we will add it to our map because we have already taken it. So are you guys able to relate that how in the second loop only, that is while moving our J, we are able to check in the map. That's why the complexity is order of n square, okay? Do try to dry run it on your own, right? And then I am sure that you are going to get it. And if you are still confused, then you should definitely try to code that up. Now I would try to, so here we are now. So the time complexity of the brute force solution is order of n square, right? Or I would say a little optimized solution is order of n square. But here we are generating all the substrings. Do we really need to generate all the substrings? So let me make my point clear from here. So we have A, then AB, then ABC, ABCB, ABCBD, right? So here we are actually generating all the substrings. Here I am trying to make my point clear that we actually don't need it. So I can figure it out. Let's see if you are able to. This is our main substring basically, and here we have all the substrings. Okay. So if you see here in the third also we have to maintain the length as well, right? We have to return the length of the longest string. So when we had 1, the length is equal to 1, right? When we had AB has unique characters, length become 2, right? Then we have ABC, then length become 3, right? Because ABC has unique characters as well. Makes sense, right? Then we have ABCB. That means it doesn't have unique characters. Length is still 3, right? Then again ABCBD is there and length is equal to 3 again because it doesn't have unique characters, right? So that's how we will keep on going on, and the length will remain 3 entirely. Now the point that I'm trying to make over here is that if you carefully look, then here we have ABC, right? We have ABC, and once we got this fourth B, we come to know that okay, this string can have a length of 3. Then as soon as we are moving to B for length of 4, for checking for length of 4, the strings doesn't have unique characters. Now if you see, then in the second step we are generating ABCBD. Do we really need to do that, guys? Do we really need to check for ABCBD once we have checked for this? No, right? Why? Because here we have already checked that ABCB is non-unique. Then even if we add D, that doesn't make any sense because here till this point, this is not unique. So in any way, if we try to add more characters, that will still be non-unique, right? So that means this is redundant. So why are we doing something which is redundant, right? So we can ignore that. So this is the first point that I tried to make. Now we can actually, now the second point that here to be seen is that once we have got this B, right? Once we have got this B, so here from this A, I am sure that my substring having a unique characters starting from A more than of length 3 is not possible, right? Does that make sense? That starting from A, if I have already got the repeating character and if I had any more character, now it won't create a unique string at all because here I have a non-unique character. That means starting from A, I have just ABC as a length, right? Now here we have, the point here to be seen is that even from B if I start, I can get at most 2, I can get the length of 2, right? Where the string length is 2 of the unique characters, right? So that means from A, I can get the maximum length of 3. From B, I can get the maximum length of 2. But starting from C, starting from C, there is a chance that I get a length of unique characters, a substring of length, a substring of unique characters which is more than 3. Does that make sense? So now here comes the point to do what I can feel is we can do sliding window, right? As suggested by Nilesh in the comments, we can do sliding window. So let's see how can we do that. So let me just remove all of this. We have A, B, C, B, D. Now in my sliding window, I will keep a window. I will start the window from A, okay? In the sliding window, we have 2 pointers, okay? One is left pointer and one is right pointer. So I'll keep both the left and right pointer at 0th position, which is A, right? Okay, so A is unique and that we are going to see it from the, we are going to do it from the map, right? So we are also keeping a map. So let's keep a map. A has a, so we can maintain an index, okay? So we can maintain an index. Let's also put the indices 1, 2, 3, 4, right? We can put an index over here. That means A is at index 0 and A we have already taken. Now let's try to expand the window. Before that, we will also keep a length variable which will keep the track of length. Length right now is A. Now we will move our R. So now the window has become from A to B. B is also not present in the map. Let's make the length 2, right? And add B to the map. Index of B is 1, right? Now let's increase R. So R is at C. So C is not there in our map. Let's include C in the map with the index, right? Also the length has become 3. Now let's move R. Okay, as soon as we move R, we saw that now we don't have any unique characters. So that means length will remain same. And now we will move our left pointer so that we can actually remove the previous occurrence of B, right? We will move our L till the point the B, the occurrence of B becomes 1 only, right? Does that make sense? That we will move it till the point the occurrence of 1 becomes 1. Okay, so let's move our L now. So as I move my L moves to B, right? L moves to B and R is still at 3. Okay, L is at 1 and R is at 3. Now we will, so A has gone out of window. That means L to R is the window. A has gone out of the window. So remove A from map. Okay, we will be removing A from map. Now we will check that still is the element, is the character at R still present in the map? Well, yes, it's still present. It means that it's still the part of the window. And in that case, we will again move our L. So let's move the L and L comes over here and B will remain at 3. Now B will be gone. That means here. So we actually remove this B from the window. Let's remove it from here. Now we will check that, okay, is B present now? Is B present in the map? Well, yes, it's not present now, right? It's not present. That means we can include this B in our map now. We can include this B with its current index, which is 3. Okay, which is 3. Now we can start moving our R again. So let's move our R. Now R comes to 4 and B is not present in the map. Length will remain 3 only because L to R, the length is still 3. Let's include D in the map. Now D becomes, so D is at position 4. Okay, and now let's move our R, and now R, there are no more characters, therefore we will simply stop, and whatever will be the length, we will simply return it. So this is how we can process it using sliding window. The time complexity of this approach is going to be just order of n because we are iterating to each character not more than twice, because one with the left pointer and one with the right pointer, right? So as we are moving our left pointer and as we are moving our right pointer, so we are not coming to any character more than twice. Therefore, the time complexity is going to be 2 into n, which is nothing but order of n, right? We don't consider constants. And the space complexity is order of n again, because here we are using a hash map. Does that make sense? How we have beautifully come across a good just by building some, observations, we have come to this solution. Does that make sense, guys? Shall we code it? Great. Cool. So let's code it up. Here we are. Now let's quickly do this. Okay. So first of all, I have to maintain an answer which is, let's say, at present int min, right? We want the maximum value, so we will initialize it to int min, or we can initialize it to 0 as well. It doesn't matter, right? Okay, so we can, the left pointer we will keep, which is initialized to 0, and also we will keep a right pointer, right, which is initialized to 0. And also we will keep a length, right, which is again 0. Now we will be iterating through our string. We will be iterating it with the help of right pointer. Right pointer, so let's keep the right pointer in the loop. So let's initialize the right pointer here only to make it more readable for you guys. So right is less than a dot length, then right plus plus. Okay, and we will, okay, so we have to take a map as well, right? So we will take a map, and that will be map will be of char comma int, because we will be maintaining the index. Make sense? We will be maintaining the index with each character. Now, okay, so if the character at right is present in the, so it's not present in the map, right? So how we will check that? M dot find, right? M dot find is equal to M dot end. That's how we will be checking that if character is not present in the map. So if it's not present, we will simply do what? We will simply do M at A of right is equal to I. Sorry, right. Here we are actually assigning. So here we are doing nothing, but let's say we have A, B, C, B, D, right? So here we are doing nothing. In the map, we will be storing A mapped to 0. That means the index of A. Okay, that's how we will be storing it. Now, after storing it like this, what to do? Let's increment the length, right? Because we have actually found a new character we have included in our map. Let's increment the length. So after incrementing the length, we are done till this point. Now, what if the character is already present, right? So for that, we will use a else block, and in the else block, we will be actually moving a left pointer. We will be moving the left pointer till the point. So let me just write it, and then I'll make it clear maybe. Okay, so let me make it clear first. So here, what my point is that I have, let's say, L here, and my R is here, okay? And now A, so let me actually change the map. The map will be A, for A it's 0, for B it's 1, for C it's 2, and again B comes, right? So I will be moving my L till this point. That means the index of previous B plus 1, because we actually have to remove the first occurrence of B. So we will be moving our L till the index of this B, right, plus 1. So here, let me write it. So while left is less than equal to M at A at right, we will be moving our left pointer. And what more do we have to do? Moving our left pointer, and we have to erase the occurrence of whatever is left behind, right? So that means M dot erase A at right. Okay. And also we have to do one more thing. So we have to reset the length. Okay, we will be resetting the length. We have maintained a global variable. That means this is, let's say, this is the answer. But as our left and right shifts to this place, that means L comes over here and R comes over here. Again, the length. So we will also maintain a variable length. So now it will become 2. Okay, it will become 2. That means the current window size. And that is given by what? That is given by right minus left plus 1. Okay, and also we will be updating our answer to max of answer comma length. And finally, we will return the answer. Let's see if it works. Are we missing on something? Does this look fine? Okay. So we actually have to do one more thing over here, and that thing is that we actually have to write the new index, right? So here, let's say A was gone, and now the new index of B is equal to 3, right? So that means it's equal to nothing but M at A at right is equal to right, and that's all. Let's test it. I'm really sorry I didn't see that. Let me share it again. Don't worry, I will explain the code. Okay, so you guys want me to just explain it. Cool. It's good that you have understood the logic, and I'm sure that you will all will be able to code it. Let's see. So here I am maintaining the answer, which is initialized to int min. Okay. Then we have a left, that is the left window, and this length is basically the to keep track of the length we have, right? This length is actually from left to right. Okay. Now we also have a map that is from map to character to int, that character map to the index. Okay. Now we, with the help of this right pointer, we will actually be iterating through our string. Okay. And while iterating through the string, we will check that if the character is already present or not. So here we are actually checking if the character is not present. Okay. So the character is not present. So we will actually put the character with the index in the map. Okay. And also we will increment the length. So this is when character is not present. But if character is present, in that case, we will be moving the left pointer. Okay. We will be moving the left pointer till the point. So actually I have shown it to you in the editor. I think you have seen it there, right? You have seen it there. So we are actually moving our left pointer till the first occurrence of the repeating character in is gone. Okay, it's gone. So then we will do left plus plus, and we will erase the character that we have left behind. Okay, and then we will do it till the character at right pointer, which we found repeating in the current window. So till the repeating character is no more repeating, we will then add the new index of that character in our map. Make sense? We will add the new index of that character in the map. Does that make sense? So, okay, let me complete it, and then I'll get back to your questions. Okay. So here we have the character with its new index, and also now we will reset the length to the length of the current window, right? To the length of the current window, and then we will update our answer. We will update our answer. We will keep on doing this, right? So length will have the size of the current window, and this answer is the global answer that we have. So whichever is maximum, that will come in our answer, and we will return the answer. Okay, we will return the answer. Let me try to submit it. Let's see if it gets submitted. Okay, it failed. Where did it fail? Okay, sorry. We need to erase the left, not right. Okay, and let's see it now. It's still not passing. Let's see if this works. Yes, it worked. So first we have to basically erase, and then we have to do left plus plus, right? Okay, so there was just a little bug. Okay, so is everyone fine with this thing? Okay, so basically you should use set when you just have to keep track of that particular character only, or I would say that particular data only, as in when you don't have to map anything, right? So here we see that we actually map the character to the index, right? So that's why we used a map, because keeping the index also was necessary to move our left pointer, and therefore we preferred map over set, right? Does that make sense? Execute now that why do we need to keep map over here? Why not set? We actually made a streak today, right? So Pavandeep, I would say that yes, maths is important, but competitive programming is more than maths Olympiad, right? So it's more than maths Olympiad, that I would say. But yes, it will definitely help you, right? Because in competitive programming, we can see maths a lot. So yes, that's a good question, Pavandeep, that you brought up. So this was it from my side. These were the questions, and I hope that you enjoyed them, right? So see ya, bye-bye, take care, stay safe.
Yes, so we are back with another class, and today we are going to continue a little bit of hashing, and we are going to see hashing on strings. So today, once again, we are going to cover hashing, but we are looking at hashing specifically for strings. And there's one more thing that we are going to cover today, which is the Rabin-Karp algorithm, which is one way of hashing over a particular string. Right? This is for substring matching. Perfect. So let us begin. Let us start directly with a very simple question. The question goes something like this: that you have been given a string, let us say S. All right. Now you have to find whether it is possible to somehow permute or somehow rearrange the letters of the string B, somehow to permute or rearrange the letters of this given string so that it can be represented as a concatenations, so that it can be represented as a different concatenations of some substring, of some string, basically. So let us take an example perhaps. Suppose that I have the string AABB, right? So currently, if I look at this string, is this particular string a concatenation? So let us suppose that A equals to 2. Can I somehow break this string down into two parts such that both these parts are equal after rearranging the string? Yes, I can. Right? So if I currently this is not, currently this cannot be, these partitions are not equal. But what I can do is I can perhaps rearrange it like this: A, B, A, B. Right? This string is just a permutation of this previous string. And now if I see in this string, yes, there are two occurrences of the exact same string. Is that clear? So basically you will be given a string like this, and you will be given a number such as 2, and you have to tell me if it is possible to rearrange this original string such that it becomes a concatenation of A similar strings. I hope the question is clear. Right? So what approach can we come up for this particular question? Let us always begin whenever we solve a problem. We always try to begin with the absolute brute force approach, because as we know, being able to solve a problem is always the first step. Right? Let us forget about the optimizations. Let us do the optimizations later. Let us first solve the problem. So what will the entire brute force look like? Well, we know that we have a string, let us suppose S, and let us suppose the length of string S is n. So we can try all permutations. So let us suppose that we have some permutation of the string S. And we have the value of A. Let us suppose A is 4. So we can check, we can split this string into 4 parts, and we can check whether this is equal to this, is equal to this, is equal to this. Simple enough. That will be the brute force approach. What will be the time complexity of this approach? Well, first of all, how many permutations, how many solutions do we have to check through? How many permutations can be there in the worst case? If the length of the string is n, then the number of permutations will be n factorial. All right, and given a particular permutation, we will also have to check whether it satisfies this property. So that will take an extra order of n time per permutation. So the total time complexity will be order of n factorial times n, which is pretty bad, but at least we solved the question. Now, as most of you have already started pointing out, so Ashita is asking to repeat the question. So let me quickly repeat the question once again. So the question goes something like this: that we have been given a string S. And we have been also given a number A. Right? Now we have to check whether it is possible to permute or rearrange this original string such that it can be represented as a different concatenations of the same string. For example, if I have this string AABB, then currently I cannot represent this as two different concatenations of the same string. Right? Suppose that A has been given as 2. However, if I rearrange this string into ABAB, now I can say that, okay, because A is 2, I can represent this string as two different concatenations of the same string AB. Right? That is the question. And the brute force approach that we saw, that simply involved trying all the different permutations and checking each permutation separately, which was pretty slow, but at least it will give us the right answer. This is the brute force. Now let us talk about the optimized approach. And yes, so both Vaishnav and Parth have given the right approach over here. So has Akshat. Akshat has also given the right approach. Animesh, your approach is not quite correct. Right? So what the correct approach over here is? So what we can do over here is, we know that this string S, suppose that this string S can be represented. Suppose for now that it can be permuted and represented as A concatenations of the same string. Then what can we understand from that? What can we understand from that? Let us suppose we break this down into 8 different parts. Suppose we break this down into 8 different parts. After the permutation, we know that this particular substring has to be the same as this particular substring after the permutation, right? And so on, this also has to be the same as this, and this also has to be the same as this. So what do we know? Suppose a character comes over here, right? Suppose this character is A. So we know that this character must also be over here, must also be over here, and must also be over here. Right? Similarly, if there's a character B over here, this is how the permuted string should look like. Right? Suppose there's a A over here and X over here. So this is what the permuted string should look like. Yes or no? All right. So what can we basically say from this? We can see that whatever character comes, right, for any character, right, the frequency of that character or the number of times that character occurs in the original string, that has to be a multiple of A, right? It has to be a multiple of A. Why so? Because if it is not a multiple of A, then you will not be able to make A different copies of it. You have to make A different copies of that same character to repeat that string. So it has to be a multiple of it. The frequency has to be a multiple of it. So this is very simple now, right? This is very simple. All we have to do is we have to go through the string, and maintain a count of each character. Right? Count each character, right? And then check for each character. Check if the frequency is multiple of A. All right. So this we have to understand over here that this must go both ways, right? This implication must go both ways. So we have so far established that if S has the property, then every character occurs some constant times A times. Right? That is what we have established. But that is not sufficient, right? That is not sufficient. We have to establish that the other way is also possible. That if you have any such string, then you can always rearrange the string into A different subparts that match, right? And that is actually pretty simple to see. What we can do is, once we have, let us suppose that we have several characters, C1, C2, C3, C4, right? And all these characters occur in some constant, let us say alpha times A, right? This occurs beta times A, this occurs gamma times A, this occurs delta times A. Right? Now what we can simply do is we can start putting these characters in, right? So we can put C1 alpha times. So this will be alpha times. Then we can put C2 beta times. Then we can put C3 gamma times, followed by C4 delta times. Right? So this particular thing will give us one part of the string, and then we can simply repeat this A times. And that will give us these frequencies that we so desire. Right? So we see that yes, this implication goes both ways. So this is both necessary and sufficient to solve our problem. Right? So the solution now becomes very simple. Just go through the string, count each character, and at the end we just have to check for every character if its frequency is a multiple of E. Perfect. Let us see some other approaches that we have. Sai is saying we first check if length of string is multiple of A or not. If it is, then we go with the solution, else returns false right away. Yes. So Sai has a very nice optimization over here. Sai says that, hey, if the original string S, let us say the length of S is suppose 10, and let us suppose that A has been given to you as suppose 4. Now we know that no matter what you do, no matter how you commute or what substring you choose, if you have a string of length n, you cannot make 4 substrings out of it of the same length. Right? You cannot make 4 substrings out of it of the same length. Why? Because simply 10 is not divisible by 4. Right? 10 mod 4 is not 0. Right? So this is one check that we can very well do. At the start itself, we can check if the length of the string is a multiple of the value a, only then should we continue with the rest of the solution. Otherwise, we can very quickly return false. That's a nice optimization. Thank you, Sai. Perfect. So I hope that you guys will be able to code it. Yes. So how do you count the frequency of a particular character? Well, this is easy if I know what the underlying character set is. If I know that my string consists of only lowercase a to lowercase z, then it is simple, right? I just have a frequency array of size 26, right? One for each character. But what if I do not know? What if I do not know what the underlying character set is? Then I can use something like a hash map. And that hash map will take care of figuring out the underlying character set for me. It doesn't really matter what characters I see. So what will be the time complexity of this optimized approach? Let us suppose that we are using a hash map. And let us suppose that the amortized time complexity of checking or insert in a hash map is order of 1 amortized. Right? Or basically, let's not say amortized, let's say expected. So what will be the overall time complexity? Well, now we are just iterating through the string and counting the characters, right? And finally checking if each of the values is a multiple of a or not. So this is very simple, order of n plus, so n is the length of substring, plus order of delta, right? Delta is the size of character set. And we always know that size of character set has to be less than or equal to n, right? Because in the worst case, every character can be different. So I can just rewrite this as order of n. So that is the time complexity of the optimized approach. So what we see from here is that all these things are variants of hashing. Calculating a hash, so over here, our hash function was slightly different. Our hash function over here was just the frequency count of characters, right? And whenever we are solving problem related to hashing, we might have to choose our own hash function to make sure that it aligns with the problem that we are solving. So let us look at one more question perhaps. So suppose that we have been given an array. We have been given an array A of size n, and this array consists of n strings. So we have been given an array of n, and this array consists of n strings. We have to return the groups of all strings which are anagrams. Right? This is a very simple question again. So let us quickly understand the question. Suppose that I have an array that looks something like this. Right? So array is at, dog, god, right? At, and fan. Suppose that this is my particular array. So over here in this array, if I rearrange the values, I can see that cat and act, they are anagrams. Right? So first of all, does everyone understand what an anagram is? Two words are anagrams. A and B are anagrams. If and only if A can be rearranged to look like B. Right? For example, the words dog and the word God, they are both anagrams because there is one G, there is one O, there is one G. I can rearrange them to look the same. Right? Now the question is that we have been given an array and we have to return the groups of all anagrams. Okay, so over here, if this was given as the input, then our output will be what? So let us quickly number all these values. So suppose this is 1, this is 2, this is 3, this is 4, right? This is 5. So our output should be a list of lists. Right? Our output should be a list of lists. The first group is 1, 4. Right? 1 and 4, they are anagrams. The second group can be 2, 3 because they are anagrams as well. And in the last group, I have 5 separate because fan is not an anagram with any of the rest of the strings. Right? So given this as input, we have to give this as the output. Is the question clear? Perfect. So let us once again look at the brute force solution. Right. In the brute force solution, what we can do is we can start with the first string. Basically the A of 0, and we can compare it with the rest of the strings. A of 1, A of 2, A of 3, A of 4, A of 5, and so on. Right? We can check each string with each of the other strings. While checking this string, we have to check for anagram. How do we really check for anagram? Should we try all the possible permutations? to check for an anagram? Not really, right? Is there any better way? So given two strings, we have to check if they are anagrams or not. Is there any good way of checking if two strings are anagrams or not? So suppose that we have been given a string A and a string B, and I have to check if A and B are anagrams. I mean, the brute force approach will be to check all permutations and compare. Right? That is very, very bad. So what we can do is we can otherwise check the frequency of each character. The frequencies have to match. And once again, if the frequencies match, then they are guaranteed to be anagrams. Right? Cool. We have another approach over here. So Ankush is saying that what we can do is we can simply add. We can simply add the ASCII values. Now this might not always give us the right answer. For example, suppose we have the following strings. So we have A and B, and we have B and C. Right? So we know that the ASCII values of these are 65 and 69, and this is 66 and 67. Okay, so this is 68. Right? These are the ASCII values of these. And if we see, then yes, 65 plus 68, this is actually equal to 66 plus 67. Right? So if we were to compare these two strings by the ASCII values, by the sum of the ASCII values, then we will the solution will tell us that yes, these are anagrams, whereas these are not anagrams. All right. So something like this, something like a simple addition, is going to leave us astray. It is not going to give us the right answer. In many cases, it will give us the right answer, but you will always come up with edge cases. Right? So the correct way over here would be to count the frequency of each character, because that does not lose any information. Right? That saves all the information. Is there any other way? So yes, this is definitely a way. A simpler approach could be just to sort the strings. Sort the strings individually. Right? So for example, if I have the string God and if I have the string dog, if I sort God, then what string will I get? I will get D, G, O. Similarly, if I sort dog, I will get D, G, O. And the sorting strings, they have to match character by character. If I have two strings, and if I sort both of them, then the sorted value should be the same for the strings to be anagrams. All right. So what we can do is we can compare the string A0 with each of the other strings and check if it is anagram. If it is anagram, we will put it in the same group. But we are still comparing every string. We are still comparing A of 0 with all the other strings, right? Simply we are comparing A of A1 with all the different strings. So the time complexity of this is perhaps not that great. What will be the time complexity of this brute force solution? It will be pretty high, right? So we have to compare every string with every other string. So that is order of n square already. And we also have to check the anagrams, right? Suppose that we are using sorting to check if they are anagrams. So that will be an additional, let us say, not n, let us say k log k, where k is the length of the string. K is the length of the string. So no. So Shiv Kumar says that we can rewrite this as n cube. That is not correct, right? Because we cannot say that this is this is approximately n cube, because the length of the string is n, is k. Right? The length of the array, that is n. The maximum length of the string, that is k. The length of the array, that is n. Now this has not been given to us in the question. But we simply cannot assume that each string is going to be the same length as the size of the array. Right? That is not correct. We have to keep these variables separate. So that was one approach. Now once again, we can do better. Right? We can do better by using hash maps. So how should we hash the values? What should the hash function be? Suppose that I have this string s, then what should the hash of s look like? What hash function would I like to come up with? So that automatically, if I do hash by chaining, then automatically I get my answer. Yes, so Animesh has the right idea over here. Animesh says that let us store the sorted string in the hash map. So basically, given a string s, the hash of s will be the sorted representation of s. Sorted representation of s. So now things become very simple, right? So if I have, let's say, cat, dog, god, act, and fan, what I can do is I can look at the first string. And if I sort this, I will get ACT. Right? For ACT, I will store the string. I will store the value 1. Right? So this is index 1, 2, 3, 4, 5. Okay? And suppose that these are the indexes are starting by 1. Right? So for act, I will store that, okay, this string is sorts to act. Next, I will move on to dog. So what is the sorted value of dog? That is DGO. So for DGO, I will store 2. Then I will come to God. The sorted value of God is also DGO. So for DGO, I will also store 3. Okay, then I'll come to act. So the sorted value of act is just act. So I will also store 4 over here. I will also store 4 over here. Finally, I will come to fan. The sorted value of fan is AFN. So for AFN, I will store 5. Okay, and that will give us our correct answer. Do you guys agree? This is the final answer. So what we can do is we can sort each string and store it in a hash map, in a chain hash map. So this hash map stores. This hash map stores a string. So this is the key. The key is a string, and the value, corresponding value, is a list of indices, right? List of integers. Swapnil is saying, what if we take a map of size 26? It could be done in constant space. Well, Swapnil, you are assuming over here that the underlying character set is of 26 characters. Right? That might not be the case. It might be the case that the underlying character set has all the Unicode characters. Right? It could be Chinese, it could be Kanji, it could be Devanagari, all these different characters, right? Prakash over here says, instead of storing string directly, we can convert each character of each string into a range 0 to 25 as frequency. Yes, so Prakash over here says that instead of sorting the string, we can do an optimization there as well. Sorting a string of size k will take us order of k log k time. This will take us order of k log k time, but we can do better. Right? So if we will come to that. So if we look at the complexity of this thing right now, the complexity is how much? We have to go over each string, right, and hash it. How do we hash it? We sort the string k log k. Right? So this is the current complexity. Now, Swapnil over here, not Swapnil, okay, Prakash over here says that we can also optimize this k log k. Right? Instead of sorting, we can keep the frequencies itself. We can keep the frequency of character. Right? That is one other way of checking for anagrams. Right? The frequencies should match. So in that case, our complexity will be reduced to an expected order of n times k time. And then what will our hash map look like? So our hash map will have to store what? So the key will be the frequency array. The frequency array of characters. So the key will itself be a hash map, basically. The key will itself be a hash map, or basically a frozen map. Hash map of frequencies, with character frequencies, and the corresponding value will once again be a list of indices. Right? Now, when you actually try to code this up, things might get a little difficult because using a hash map itself as a key can become tricky. Right? If you knew that okay, you had the character set of 26 characters only, then instead of storing the hash map of frequency, you could have just stored an array of 26 different values. You could have stored an array of just 26 different values, but you don't know what the underlying character set is. Right? So you will have to store a hash map, and hash maps are not usually hashable. So it is difficult to use hash map as keys. Perfect. Vignesh is asking, why are we seeing Robin-Cobb method over here? Well, Vignesh, Robin-Cobb method for string matching is just another very simple. I mean, it's not that difficult. It is just another hashing technique. And that is the next thing that we are going to come to. Perfect. Animesh says, what happens if the number of characters in a particular string is more than k log k? Well, Animesh, that is not possible. Right? So over here, k is the length of the largest string, of the longest string. Right? So if k is the length of the string, then it is not possible for the number of characters in this string to be greater than k. Right? The number of characters has to be less than or equal to k. Yes, so Deepanshu over here is saying that if we go with this particular approach, if we go with this array approach, then the space complexity will be high. Exactly, Deepanshu. So suppose that our strings are Unicode strings. So how many different characters does Unicode have? Does anyone remember? How many different characters does Unicode have? Unicode has how many characters? It can support up to 65536 characters. Right? The number of characters in Unicode is huge. Right? So if we were to go with this array approach, if we were to store this array approach, then we will have to store an array of size 65536 for every string. That is very difficult. No, guys. ASCII has 256 characters. Unicode is much larger. Right? ASCII only has some English character, some English letters, some mathematical symbols, some accented letters, right, and some box string characters. But Unicode has a lot many letters. Okay, so this is not going to work, which is why we said that let us not keep an array. Let us not keep an array. Instead, let us keep a hash map of the frequencies. But once again, if we are trying to keep the hash map, then things will get tricky because hash maps are generally not usable as keys. Vignesh is asking a very good question over here. Vignesh says, sir, I have a doubt. When we are doing competitive coding online, will the online judge also check the space complexity of our solution? And yes, Vignesh, that is true. I mean, when you go to interview bit, when you go to Scalar Academy and interview bit, our online judge also checks the space complexity. Right? So we make sure that the memory that
You have to maintain
your program is using, the memory that is being used, they just monitor the memory that is being used. Right? And this memory has to be within a reasonable limit, depending on the programming language. So let us move on. I hope this solution is clear to everyone. All right, so the most optimized approach for this will be order of n times k. Right? If we do the hash map approach, so hash map of hash maps, it is not that simple. But otherwise, we can at least do it in order of n times k log k. Right? If we store a hash map of sorted strings. I hope that is clear. All right, now let us move on to the Rabin-Karp algorithm. So far, in both the questions that we have seen, we were trying to come up with our own hash function. So that we could simplify our life. Right? Now, Rabin-Karp algorithm is another such algorithm. It is basically used for string searching. So let us quickly define what the string searching problem is. Right? So the string searching problem is very simple. You have been given a large string S. Right? This string could be, let us say, a book, or this string could be Wikipedia, the entire text of Wikipedia, or this string could be the entirety of internet, perhaps, or this string could be all the products on Amazon. Right? It could be any such thing, and you have been given a pattern. Let us say the pattern looks something like abracadabra. And you want to figure out, first of all, you want to figure out whether this pattern exists in my string. Right? That is one of the most important things that we do while we are searching. But more importantly, I need to find where exactly. So suppose that I have this string over here. I have a large string over here. And suppose my given pattern appears over here, appears over here, appears over here, appears over here. Then I should be returning the starting indices of all these different occurrences. That is what the string search problem means. Given a large string and a small search pattern, search for that pattern in the entire string and report all the occurrences of that string. We have to report all the occurrences of the string, not just one occurrence. So, what is the normal way? What is the usual, most trivial way that you can solve this particular problem? Suppose that I have a string S of size n and I have a pattern P of size m. Then how should I particularly go about searching for this pattern in the string? I can use some sort of a sliding window. Right? So if I have this string, I can first check this particular thing for the pattern match. Then I can shift by one character and then check this particular string for the pattern match. Then once again, I can shift one character and search this string for the pattern match, and so on and so forth. Right? So I can keep a window of P size and I can slide it. One character each. I can slide it right, one character each. So how much time will this take? Well, let us look at the first window. So we are currently matching this particular portion of size. So we will have to verify each of these characters, right? That this matches this, this matches this, this matches this, and so on till the end of this. So each check will take us order of P time. And how many checks do we have to perform? We have to start from this index 0 and we can go up till the index n minus p minus 1. Right? Because this last character will be at location n minus 1. So this is the last occurrence where the pattern p could occur. So it will be p times n minus p minus 1, which is simply order of n times p. Yes? No, now this np is not that p versus np thing. Right? This np is not that. This np is just the string length of the strings. Now the question is, can we do better? So there are many string searching algorithms. Today we are going to discuss Rabin-Karp, but in the coming classes we will discuss more complex string searching algorithms. Right? So you can search string using tries, you can search string using automatas, you can search string using n different ways, and we will be covering most of them in the coming classes. But today we are going to talk about the Rabin-Karp algorithm. So the Rabin-Karp algorithm has one special insight. Right? The Rabin-Karp algorithm says that, all right, let us suppose that you have this particular string. Let us suppose that you have this particular string and you are matching for this particular pattern, P over here. Right? You will spend some time, you will spend P time to check if this is a match or not. Yes or no? You will spend P time to check if this is a match or not. Now, when you move this to one right, when you move this to one right, now once again you will spend P time to check if it is a match or not. Yes or no? That is what is going to happen. So can we improve this? Can we somehow reduce this time complexity? So what Rabin and Karp said was that, all right, instead of comparing the strings, let me instead compare the hashes. Let me instead hash the strings. Let me hash the strings and let me compare the hashes. Right? So suppose that we have this particular part of the string, right? And we have this string that we are looking for P. So if, let me call this string S dash, right? Let me call this substring S dash. So if the hash of S dash is not equal to the hash of P, right? If I have this hash of P, and if I looked at the hash of this, S dash, right? If I looked at the hash of this S dash, and the hashes do not match, then what can I say? Can this be equal to P? Can this substring match the same? Can this substring be the same as the pattern? No, it cannot be. Because if it is same as a pattern, then the hashes will have to match. So if the hashes do not match, then we are guaranteed that not a match. But if the hashes are equal, then what can we say? Can we say that yes, there are a match? Well, not really. Right? That depends on the hash function. Depends on the hash function. So basically, if the hash function is lossy, or basically if the hash can have collisions, then a match hash means a match may be possible, right? A match might exist, right? It is not necessary for the match to exist because it could just be a simple hash collision. On the other hand, if the hash function is lossless, or that is, it is guaranteed to have zero collisions, then yes, a match is same as a match necessarily exists. So depending on our hash function, we know that yes, if there is a match, if the hash functions match, then an actual match might exist or might not exist, but we are at least sure that no matter what the hash function is, if the hashes do not match, then it is guaranteed that the substrings do not match. All right. So what can we do over here is, once we are trying to compare this particular substring for the pattern P, right? If we choose a hash function that has a certain property, so there's something called rolling hash functions. There's a certain property of a rolling hash function. The property is that once you have computed a hash of this thing, if you have to shift it by one character, then you can easily do it. You can easily calculate the hash of this thing in order of one time. Does that make sense? If you have the hash of P, the hash of, let's say, the index I all the way to I plus P, right? Then to compute the hash of I plus 1 all the way to I plus P plus 1, right? You can do this in just order of one time. Provided you have this previous hash. Right? All right, but is this idea clear? That if we use a rolling hash function, then we can perhaps optimize our time complexity. Now let us have a quick look at one example of a rolling hash function. Right? So this is not the hash function used in Rabin-Karp. Right? Hash function. But this is just example of a rolling hash function. Suppose that we simply add the ASCII values of the characters. First of all, as we saw that this particular hash function can have collisions, right? So this is not a perfect hash function. Yes, we just saw that what sort of collisions can happen. Suppose I have the string A and D and I have the string B and C, then the hash of AD will be equal to the hash of BC. If my hash is just the sum of ASCII values, because this will be what? This will be 65 plus 16 or 68, and this will be 66 plus 67. Right? Both will have the same value. However, this is a rolling hash function. So suppose that I have this string. Let me call this A, B, C, D, E, F, G. Right? I have the sum of these, right? So I have 65 plus 66 plus 67 all the way till some value. Right? Let us say 72. Okay. Now, if I have the hash of this. If I want to calculate the hash of this, perhaps some character over here. If I have to calculate the hash of this, then what should I do? Should I start once again from B? Should I start adding once again from B? I need not. I need not do that, right? Suppose this value was S. Suppose this value was S. Now I can just do S plus the code of alpha minus the code of A, right? I can just do this previous sum. I can add the code for this and I can subtract the code for this. And I can very simply calculate the hash function of this entire chunk. Yes, how much time will that take? That will take order of one time only. A rolling hash function is a function such that in which it is very simple to calculate the hash of the next substring once you have the hash of some substring. Yes, so Vignesh, yes, this is similar to sliding window sum. Like this particular thing is similar to sliding window sum. However, this is not the hash function that Rabin Karp will use. Right? This is not the hash function that Rabin Karp will use. This is just an example of a rolling hash function. Right? So we will come to the decision of which hash function to use later on. We will come to the decision of which hash function to use later on. Let us first see that once we have this, what will be the time complexity of our total overall algorithm? What will be the time complexity? So I have this large string S of size n, right? And I have some pattern P of size n. So what I am doing is I am hashing. So first of all, I will calculate hash of P. How much time will that take? That will take me order of m time. Yes, because I have to calculate the hash of P. That will require going through each of the characters. Now I will start matching from here to here. Right? I will start matching from here to here. I will calculate the hash of this thing. I will calculate the hash of these things and I will check if the hashes match or not. If the hashes do not match, if hash does not match, then what will I do? I will slide right. I will slide my window to the right. And how will I slide my window to the right? To calculate the hash again, I will remove the value of this thing. I will remove the value of this thing and I will add the value of this thing. Right? And that will allow me to recompute the hash of this particular substring. Yes? So recomputing the hash will take me order of one time. So sliding right will take me just order of one time. Right? If the hashes do not match. But if the hashes match, if hashes, basically else, now what can I say? If the hashes match, as we just saw, that depending on the hash function, it is not guaranteed that the pattern exists, right? Because it could just have been a collision. It could just have been a spurious match. In that case, what do I do? In that case, I have to verify if my match is correct or not. So else verify. How do I verify? Verification is very simple, right? I look at the first character, second character. I check if all these characters match. Suppose my hash was same. Just to confirm that the string is actually the same, I can compare it letter by letter. So verification takes me order of m time, where m is the length of my pattern. Perfect. And so this is part of the inner loop. This is code of the loop. And how many times are we repeating this? We are doing this for every window. Right? We are doing this for every window. And how many windows are there? There are order of n windows. Right? There are order of n windows. So basically what will happen is our time complexity will look something like this. If hashes do not match, so basically if there are no collisions, then what will happen? If there are no collisions, then every match is a guaranteed match. Right? Every particular match is guaranteed to be correct. On the other hand, if there are collisions, if there are a lot of collisions, then every match, most of the matches will be spurious. Right? Most of the matches will be spurious. So can someone tell me what will be the worst case and best cases of this algorithm? So if there are no collisions, what will be the time complexity? Well, the time complexity will just be order of n. The time complexity will just be order of n plus m, because if there are no collisions, then I'm guaranteed that as soon as the hash functions match, I'm guaranteed that the pattern exists. I don't have to verify it. If the collision possibility was not there, then this verification step is unnecessary. I don't really have to do that, because every hash function match is guaranteed to be a pattern match. But if there is a chance of collision, then I have to do verification again and again and again. I have to keep doing verification. So in the worst case, as we see from this loop, this loop can go order of n times order of m. Right? So the total time complexity over here can be order of n times m. Right? And this time complexity, as we see, this is no better. This is no better than the brute force. If you look at the brute force solution, then the brute force solution was just order of m times n times p, right? So it is no better, Rabin-Karp is no better if the hash function has a lot of collisions. So the entire functionality of Rabin-Karp, the practical performance of Rabin-Karp will be based on whether you choose a good hash function for your use case or not. Alright, so Rabin-Karp basically, best case with perfect hash. This will take us order of n plus m time. Right? But in the worst case with imperfect hash will take us order of n times m time. Right? Now the question arises, what hash function should we use? Right? So can someone come up with a nice idea of a hash function? Well, we would want the hash function to be as lossless as possible. We want to retain as much information about the string as possible. For example, if we have the string ABCD, if we add the ASCII values, are we retaining a lot of information? We are not necessarily retaining a lot of information, right? Because the hash of this is the same as the hash of DCBA. Right? So we are not retaining a lot of information. So this is a very lossy hash function. What will be the perfect hash function? What will be the completely lossless hash function? Well, I can encode each string into an integer. Right? I can actually encode each string into an integer, right? Because every string, when we look at it, every string is just stored as bits and bytes in the memory. Right? Everything in the computer is just zeros and ones. So I already know some way of encoding a string into an integer. Right? But if we are not sure how to encode the string into an integer, I can manually do it. Right? Suppose that my character set was ASCII. ASCII can have 256 different values. Right? ASCII can have 256 different values. So I can just treat this as a number in base 256. Right? I can just treat this as a number in base 256 and convert that number into base 10. What is this number equal to? So what is D? D is 97 plus 4. Right? That is D. So this is 101. The ASCII code of small d is 101 times 256 to the power 0. Plus, what is C? It is 100 times 256 to the power 1. Plus B is 99 times 250. Okay. I guess I messed up. This is 100, this is 99. This is 98 times 256 to the power 2 plus 97 times 256 to the power 3. Yes or no? This is how I can make sure that I have the entire information of the string. If I have this hash function, then it is guaranteed that there are no collisions. Right? Because I'm not losing any information. I'm just encoding that string. I can go from here to here and I can go back. Right? So there's no loss of information. But would this hash function usually work? Is it possible practically to use a hash function like this? Not really. Because these hashes can get arbitrarily large. Right? Suppose that my pattern is of size 50. Right? My pattern has size 50. Right? So in my pattern, this character, the ASCII value of this character will be multiplied by 256 to the power 50. That is ridiculous, right? That is a huge number. So I cannot possibly store this in a 64-bit integer or even a 128-bit integer. Right? That is not possible. So I have to reduce the size of the hash. Right? I have to reduce the size of the hash. And one common way of doing that is to just take a mod. Right? Mod or modulus. Yes. What should we usually take a mod by? Well, we can try to take a modulus by the size of our hash. Right? Suppose our hash, we can store 64-bit integers as hash. Then we can simply mod it by 2 to the power 64 minus 1. Alright, we can simply mod it by 2 to the power 64 minus 1. Alright, usually it is still a better idea to use a large prime number for modding, right? Because if you use a prime number, it has a slightly better distribution for the hashes. Perfect. So Rabin-Karp says this. Rabin-Karp just says this, that given a particular string, if you are trying to find a pattern, first of all, find the hash of the pattern. Right? And this is the hash. Hash is just the encoding of the pattern. Hash is just the binary encoding of this pattern, right? With some modulus. With some modulus n. Right? With some large prime number p. Is that clear? Once you have calculated this hash, then compare the hash of each substring. Compare the hash of each substring with this hash. If it is not a match, then simply slide the window to the right. If it is a match, then please go and verify. Right? Please go and verify. Now, is this particular hash function rolling hash function? Suppose that you have the hash value of this, right? So you have A, B, C, D, right? And let us say that the character set is suppose 256, right? So this is 256 to the power 0, D times plus. So let me just rewrite this. This is just D times 256 to the power 0 plus C times 256 to the power 1 plus B times 256 to the power 2 plus A times 256 to the power 3, right? Where A equals to 97, B equals to 98, C equals to 99, and D equals to 100. So this will be my actual encoding, and I will also mod this with some value. Let us say M. Okay, this is the Rabin-Karp hash function. Is this a rolling hash function? Basically, if I add a new character over here, E, suppose 101, then can I calculate the hash of this part? Can I efficiently calculate the hash of this part? Well, yes, I can. Let us quickly see how. So what is the hash of this part? Right? Let us first write what the hash of this part is. The hash of this part is this: B times 256 to the power 3 plus C times 256 to the power 2 plus D times 256 to the power 1 plus E times 256 to the power 0. This is the hash of this BCDE. All right, let us see if we can convert this, if we can somehow get this value from this value. All right, so first of all, what we will need to do is we will need to subtract the value of this. So what we can do is, first of all, from this we can subtract A times 256 to the power 3. Now, whatever remains, so what part will remain? This part will remain. Right? This part will remain. But we see that this part has one less part. Right? So currently B is being multiplied by 256 square. We need B as 256 to the power 3. Similarly, D has been multiplied by 256 to the power 0. But we need D multiplied by 256 to the power 1. So we just multiply the remaining thing. With the base 256. Right? And then we just add this last value. Then we just add this E times 256 to the power 0. That is going to give us the new hash function. Right? This is the same as binary. Right? If you have this binary number, and you know the base 10 representation of it, or if you have the base 10 representation of it, then you can remove this and add something over here, right, to get a new particular value. That is perfectly valid. You can totally do that, right? So this is what the Rabin-Karp hash function is. And yes, this is a rolling hash function. Right? Now, there's one catch that you have to understand over here, that because this is a modulus, this is going to work, right? Basically, do you guys know that modulus distributes over addition equals to A mod M plus B mod M? Right? So notice that there is some loss of information happening over here. Right? Once you have calculated this, after that you are losing some information because of this mod. Right? But that doesn't really matter, because modulus distributes over addition. It also distributes over subtraction. So notice that we have to subtract this value, but we can do that because we are using mod. Similarly, we have to multiply this value, and modulus also distributes over multiplication. The only reason we can do this is because we are using the modulus operator. We are losing information in a manner that mathematically makes sense. If we had lost information in some other manner, we would not have been able to reconstruct it. Right? We would not have been able to have the rolling hash property. Perfect. So this is basically it. This is the Rabin-Karp algorithm. So this was just some string matching using the hashes. Perfect. Surit says, are we not going to do a modulus on the next window? Yes, we are going to take a modulus on the next window as well. Okay, so after we have done this, so basically, we have the hash. We have the hash of previous window. Right? Let me call this h. So what we are essentially doing is we are saying h minus what was the first character, right? Character 0 times base to the power the length of p, right? Base to the power length of p. So we will subtract this. Then we will multiply the result with the base, right? Then we will add what? We will add the new character. Character, let's say call this new, and let's call this character O. We'll add the new character, and then we will once again take the mod with the same value m. Length minus 1. Yes, my bad. Length minus 1. Thank you for that, Rajiv.
Okay, so guys, till now we have studied what is hashing. We have also studied an algorithm for string matching using hashing, right? Okay. Now, when we talk about strings, there is a vast majority of problems based on strings which can be solved using hashing. Okay, so hash map is a very, very powerful tool when it comes to solving problems of strings. Okay, so we are going to study a few problems today. We will be solving some problems based on strings which can be solved using hashing, and we'll also be solving a problem which will involve some other techniques. But majority of the problems can be solved using hashing. Okay, so let us start the class with a very easy type of a problem. Let us say that you are given a string. Okay, let's say that this string is interview bit. Okay, you have to find what is the first non-repeating character. Okay, first non-repeating character means in the given string, some characters might be repeating, some might not be repeating. So which is the character, which is the first character which is non-repeating? Okay, so in this case, we can see that I is a character which is repeating in this string. So this is definitely not going to be an answer, right? N is actually the first non-repeating character because there is no n after this n, right? So n becomes the answer for this case. Okay. Let us take another string. For example, let us say scalar academy free classes. If this is the string, what should be the answer? If this is the string, we can see that s is repeating multiple times in this string, so s cannot be the answer. C is also repeating, C also cannot be the answer. A is also repeating, L is also repeating. Okay, E is also repeating. R is also repeating. Okay, D is the answer, right? So in this case, D becomes the answer. Okay, Scalar Academy free classes. D is the first non-repeating character in this string. Okay, so we'll quickly discuss the solution. Okay, there are no white space. Okay, you can assume that there are no white space in this string. Okay, this string has no white space. Okay, so what is the minimum information that we need to return this answer? The minimum information that we need is, first is that I want, so I will just write what is the info needed. Okay, first thing is, since I want to find first non-repeating character. Non-repeating character means a character which is occurring exactly one time, right? A character which is present in this string exactly one time. So the first information that I need is what is the count of all the characters in the string, right? So what is the frequency of each character? Because only if I have the frequency of each character, then only I can comment whether the characters are coming one time or multiple times, right? So this is the basic info which is required. The second basic info is, since I also want the first non-repeating character, so this information will give me which all characters are repeating, which all are non-repeating. If for solving this problem, I also want which is the first such character. So I will also have to check the order, right? The order of character in which they are appearing in this string, right? So now, how can I compute the frequency of each character? Is there a very easy way to do that? Right, you can use a hash map, right? Or you can even use an array of size 26. That will also suffice, right? You can use an array or maybe a hash map for each and every character. If you are using an array, index 0 will correspond to the frequency of character A, index 1 correspond to the frequency of array B. So if this is a string of only let's say small case characters, then you can use an array of size 25. If you are including each and every character, then you can use an array of size 256. Or what you can do is you can have a hash map. Both of them are same thing. So a hash map of character and integer. Okay, this will also suffice. Now once you have a hash map or maybe a map array, what you can do is you can iterate over this array, iterate over this string, and you can count the frequency of each and every character, right? So let us say that A, B, C, A, C, B, D, E. If let's say this is the string that we have, okay. Now if I am if I want to build a hash map, after I iterate over this array and keep the count of frequency of each and every character, I will have something like this, right? A, B, C, D, E. All the unique characters will become the key, and corresponding to each and every unique character will be having a count. Right? So against A will be having 2, against B will be having again 2, C is also 2. Let us also have F and G. Okay, then and another C. Okay, so C, count of C will be 3, count of D is going to be exactly 1, count of E is 2, for F1 and G1, right? So now we have got the frequencies of each and every character. Okay, now what is the second information which is needed? The order of the characters, right? So now after building this array, we know that these are the characters which are appearing exactly one time in this string, but we want to return the first such character. So how can we return the first such character? We need the order. Do we have the order already? Yes, right? We already have the order stored in this string. So again, we can iterate over this string, and we can check for each and every character, right? So if you again iterate over this string, you can check character wise character whether this character is a character with single occurrence. No. So A is removed. Then you go to B. B is also not occurring exactly one time. C is also not occurring exactly one time. A again is not occurring. C can be skipped. B can be skipped. Then when you come to D, you see that D is such a character which is occurring exactly one time, and this is the first character that we have seen till now while iterating the string from left to right? So D becomes the answer. Okay, so how are we going to solve the problem? First we build the frequency array, or first we build the frequency hash map, and then again we iterate over this string, and character by character we check whether this character is a single occurring character or multiple times occurring character. If it is a single occurring character, we just return this. Okay, now some of you are suggesting that taking XOR can solve the problem. No, taking XOR cannot solve the problem, because it is not guaranteed that all the other characters are occurring even number of times, right? So XOR is not going to cancel each and everything. In this case, if you can just take what is the XOR of this, so A and A will cancel out, B and B will cancel out, right? E and E will cancel out, but then you will be left with the XOR of C, D, F, and G, and you don't get any useful information from here, right? So XOR is not going to solve this problem. Then second option that is proposed is, can we do it using sorting? Shubhadeep, if you sort the if you sort the characters, you lose the order, right? But you need the first non-repeating character first in this given string. So sorting again cannot solve this problem. You will have to solve this problem using this way only. Okay, is this clear to everyone? Okay, let us solve another very interesting problem. So now you guys should keep an eye on this thing, that how hashmap is enabling you to solve this problem very easily, right? Okay, let's move on to the next problem. The next problem says that you are given two strings, okay, and you have to tell whether the strings are isomorphic or not. So you are given two strings, you have to check whether the strings are isomorphic or not. In the context of this question, the meaning of isomorphic is that if you replace each and every character of string A by each and every character of string of the second string, you get the same string. Okay, so right, so there has to be a symmetry between these two strings. For example, if I have a string add and another string egg, right? So now if I just replace A by E and D by G, I get the second string. Okay, there has to be a symmetry between them. By symmetry in this case, we mean that there has to be a one-to-one mapping between the characters. Okay, so can I say that ABC is isomorphic to X, Y, Z? Is this correct? Yes, this is correct, right? Because you can replace A by X, B by Y, and C by Z. This is absolutely correct. Okay. Let us take another example. If I say that I will have, let's say, ABB replaced by CAC, is this correct? So in this case, I can replace A by C, then I can replace B by A, but to make it correct, I will have to replace B by C for the third character, right? But we already have a mapping for B, which is A. So I cannot have another mapping for B. So this is wrong, okay? So now is the problem clear to everyone? You have to have a one-to-one mapping between the characters of string A to characters of string B. Two hash maps for each string and their character frequency. Okay, Azim, do you need the character frequency here? Map of character string with each other? Yes, Akshat, that will work. But do you need a one-way mapping or a two-way mapping? First, check if strings are of same length. Okay, if they are, use a hash map and check if it already there in the map. Sai Kiran, you are saying that you will build a map or character to character map, right? If that is the case, then it's correct. Can we take ASCII difference between two strings? Heyman, just take some examples and check if that is going to work. Dictionary with each character mapping. Okay, Vignesh, that is in the right direction, but will that solve the problem? Okay, now the most commonly sent approach that I can see is that take a hash map, which is a character to character hash map. And in this hash map, we'll be keeping a mapping of characters of string A to characters of string B, right? So the key is going to be the characters of string A, right? So let's say that if I am creating the map for these two strings, I will map A to C, then I map B to A, and every time when I'm adding an entry to the map, I always check whether that key is already present or not. So when I add the last mapping, which is B to C, I see that B is already having a mapping, so I can return false. You can directly have a mapping of characters of string A to characters of string B, and while entering the mapping or while inserting the mapping in the hash map, you can just check whether the key is already present or not. If the key is already present and if the mapping is different, then you can return false, right? I can see it's clear to most of you, but is it correct? Let's take an example. What if I have string A is AB, second string is AA, right? What should be the answer for this case? Should it be true? Should it be false? This should be false, right? Because I am having a mapping from A to A. And then since this A already has a mapping with A, it cannot have a mapping with B. So this should be false. But if we go by this approach, what we will do is we'll put a mapping A to A, and then the next mapping that we are going to put is B to A. We will check the key. Key is not present, right? A is a different key, B is a different key. So we will insert this mapping as well. And according to our approach, this is going to give a right answer, which is wrong. So what do we need to do? We need to see whether there exists a one-to-one mapping. What does one-to-one means in terms of functions? One-to-one means that if A is mapping to this character, A should have exactly one mapping on the right side, and this character should also have exactly one mapping on the other side. So what we'll have to do, we'll have to keep both the mappings, right? So one hash map is not enough. We'll have to have two maps to store both the mappings, right? So both directions should be stored. So what you will be doing is you will be storing A to A. Simultaneously, you will also be storing this reverse mapping. Then you enter B to A, and then the reverse mapping is A to B. Now here you will see that this key is already existing, so this is not possible. So both of them are important. Okay. Why do we require two hash maps? Because in a single hash map, to check whether A is a value of any other key or not, you will have to iterate over each and every key, right? That is why that is not optimal, and hence we can use two hash maps to store both directions of mappings. Okay, cool. So now I think you should be getting a feel of how to solve string problems using hash maps or maybe using arrays of constant size, right? What is the time complexity here? What is the time complexity of this problem? So we are iterating all the both the strings exactly once, right? And then we are putting in the map, and then we are checking in the map. So whenever you use a map, especially if you are using an unordered map in C, or if you are using a hash map, we assume that the average time complexity of insertion or lookup in the map is order 1, right? So going by this assumption, the time complexity of this problem is nothing but order n, where n is the string length, the minimum out of the two strings. Okay. Will we code these problems on some code editor? Shrestha, you can code, or like there is an assignment based on strings as well. You can also attempt that assignment. Some of these problems are there in the assignment. Okay, let's move on to the next problem. Will this logic work for ABB and BBA? Yes, Pratyusha, check it yourself. Will this work or not? You store a mapping from A. So what Pratyusha is asking, she is saying that there is a string ABB and then BBA. Okay. So you store a mapping from A to B. Simultaneously, you store another mapping from B to A. Right. Then you store a mapping from B to B in this map. And here again, you try to store the mapping from B to B, but you check that this key is already present with a different value. So this is going to fail. Okay. Okay, let's move on to the next problem. The next problem says that you are given a string and you have to remove pairs of duplicate characters placed together. Okay, remove pairs of duplicate characters placed together. For example, what do we mean by this is, let's say that this string is A, B, C, C, D. So now we can see that this is a pair of duplicate characters and it is placed together, which means that these two duplicate characters are placed next to each other. So you have to remove them. So the output that you are going to get is going to be A, B, and D. Okay. Then the next example could be that A, B, C, C, B, D. Okay. Not D, D, it should be B, D. Okay. If this is the question, then first what you do is you remove these two. Okay. So let me add something extra here. You have to recursively remove. Okay, recursively remove pairs of duplicate characters, which means that here if you remove C and C, then the string that you get is A, B, B, D. Now even in this string, D and B forms a pair of duplicate characters. So you will have to remove this as well. So the final output is going to be AD. Okay. In some of the cases, it might be possible that you will have to return an empty string. For example, if you have A, B, C, C, B, A. In this case, the first removal will remove the two C's. So you get A, B, B, A. Then you get A, A, right? And then finally you get a empty string. Okay, now we have a test case. What if the input is A, B, D, G? Okay, if this is the input, then in the first attempt you can either remove these two B or these two B. Okay, whichever pair you remove, you will be getting A, B, G. And now there is no duplicate character, right? No pair of duplicate characters. So this remains the answer. Okay. Okay, so one very commonly, or the first approach that comes to the mind is that you actually remove all these characters one by one, right? So what you will have to do is you first remove this pair, and then you get this intermittent output, and then again in this string you check whether there is a pair which is operating together. Then you remove this, right? This is one of the approach, but I think this should be obvious to everyone that this is going to be very unoptimized approach, right? So what should be done? Now, if you notice in this example, let's say that we have A, B, C, C, D, D. Okay, if this is the case, right? So I check A and I check B. These two are not same, right? Then I check C. Again, B and C are not same, right? So what we can do is once we reach C and this C, correct? So now we can see that these two C's are same, correct? So now they have to be removed. But if you are removing this pair, there is a lot of chance that you will get another matching pair before and after these two C's, right? So if you get this pair, what you can do is you can maintain these pointers. So what is the character that you need to check on the left side? On the left side, you need to check the character which occurred just before this pair. On the right side, you need to check the character that occurred just after this pair, right? So you can just maintain 2 pointers and you can check this thing. And a very, very easy way to do the exact same thing is if you use a data structure that supports these operations very optimally. Do you guys know about such a data structure which can solve this type of a case very easily? You always, so if you are moving from left to right, you are always concerned about the last seen character, right? So if first you see A, then you see B, then you see C, then you see another C. Now you know that you have to remove these two. So these two can be removed. And then comes another B. So what is the character that you need to check? The character which was entered just before C. Okay. So now you remove these two. And then comes, let's say you also have A, then comes A, right? So now you have to remove these two. So you always require the visibility of the character which was seen last, right? Or which was seen just before the character that you have removed. So stack is one such data structure that provides us this functionality, and it can be very easy to use. So what you can do is you can maintain a stack, right? And now whenever you get a character, you insert it in this stack. So you get let's say A, you insert it in the stack. Then you insert it in the stack if the stack is empty, right? Now if you get a new character, you first check it with the previously seen character. If these two are same, then you remove both of them. If these two are not same, then you enter this inside the character. So you will be pushing it. Okay. Now comes C. Again, you check whether this new character is same as the previously seen character. No. So you can again push C as well. Okay. Then comes another C. Now you can see that this C is same as the last pushed character. So you can pop this out and ignore this new C as well. So these two are removed. Now you get a B, right? So as we have seen, the concerned character is this B, which was last pushed in this stack before we pushed C, right? So now you check this B with the top of stack. You again see that these two are same. So you can remove this B as well. Then you get D. So now you can see that D is not same as the top of the stack, so you can insert it. Once the complete string is visited, whatever is remaining inside the inside this stack is going to be the answer. What if it was A, B, C, C, D, B after removing C while checking previous character and next? Okay, let's take the example proposed by Akash. Akash is asking what happens if we have A, B, C, C, D, B. First of all, what should be the answer in this case? The answer should be A remains as it is, B, D, B. This should be the answer, right? These two B will not be removed because they are not together, correct? So if you take a stack, first you enter A, then you get B, B is not same as A, so you enter, then you get C, C is also not same as B, so you push, then you get another C. Now these two C are same, so you pop this C. Then you get D, so you push D, then you get another B, you push D. Whatever is remaining is same as the answer. So it is going to work, okay? Can we do through recursion? Yes, Ankit, you can do, but that is going to be unoptimal because after you remove one pair, you will again have to iterate over the complete string to check whether there are such pairs or not, right? How can we do it using maps? Okay, so guys, again, all the questions of strings cannot be solved using maps. There is a fixed set of pattern that you can use to where you can use map. For example, any problem where you see that frequency is being talked about, or you're being asked about what is the first occurrence or the last occurrence, right? All those types of problems can be solved using maps, but not all the problems can be solved using maps. So this cannot be solved using a map. A stack will be a better data structure to solve this problem. So let us solve one more problem before we end the class. So now this is a very, very interesting problem. The question says that you are given a string and you have to check if you can form this string, or you can construct this given string just by repeating a substring of this string. Okay, by repeating any substring of this string. For example, if the given string is ABC, ABC, ABC. Okay. Now, if this is the string, so first try to understand the problem. The problem says that you are given a string. You have to check that whether you can construct this given string just by repeating any substring of this string any number of times. For example, in this case, ABC is a repeating substring, right? So what you can do is you can just pick ABC and you can repeat ABC 3 times and then you get this complete string. Okay. Another example could be that you have AB, 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 right? So in this case, you can just repeat AB 5 times and then you get this correct, this original string, right? Or you can also have something like, let's say B, 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 B. So in this case, you can just repeat this substring of size 1 again 5 times and then you get the original string. Okay. Is the problem clear to everyone? So for this case, you return true. For this case, again, you return true. For this case also, you return true. And let's say if you have something like this. Here, there is no substring by which, by repeating which we can form this string, right? So for this, you will be returning false. Okay, Prakash has an observation that frequency of every character should be multiple of k. That is absolutely correct. But is that sufficient? Is that a condition that is sufficient to solve this problem? Sai Kiran is also saying, okay, let me take another example. What about A, B, B, B? What about this case? Do you return true here or false here? What is the substring by repeating which you get this string? So frequency of all the characters is same. A is appearing 3 times, B is appearing 3 times. Is there any substring by repeating which I can get this original string? No. right? So this is not going to work. Reverse the string from half of the string, then make a new string. If it is palindrome, okay, that is a very interesting approach, Rajiv. Let us try that out if it's going to work or not. Okay, so I can have something like, let's say, ABC, ABC, ABC. So you are saying that we should reverse this string from half, right? So first of all, from where should I reverse? There are 1, 2, 3, total 9 characters are there. So either I can reverse from here or maybe I can reverse from here as well, right? So let us reverse the last. If I reverse this part, what is the answer that I'm getting? A, B, C, A. B remains as it is. I get C, B, A, C. This is not a palindrome. If I reverse this complete part, then I get A, B, C, A, and then C, B, A, C, B. Again, this is also not a palindrome, right? Can we do it using 2 pointers? I don't know, Akshat. If you are able to do it, you can just propose your approach. Sliding window, Dikshit Garg. Sliding window, how are you going to use a sliding window? You don't know what is the size of the substring. The substring can be of size 3. This substring can be of size 1. This substring can be of size 2. This substring can be of size of any size, right? Check if repeating pattern as in Rabin card. Okay, so Tuhin, you will be checking for substrings of each and every sizes, right? LPS using KMP algorithm, yes. Ajay, that is J, that is going to work. But what is the logic behind using that? Find minimum substring and then check. So minimum substring is going to be of length 1. So how are you going to use this? And guys, there can be repetition inside the substring as well. I can have A, B, B, A, and then again A, B, B, A, B, B, A. In this case, I have a substring of length 4, which is A, B, B, A, which is repeating. There is no condition that the repeating substring should have unique characters. You can have repetition inside the substring as well. The difference between two occurrence of character must be equal. Again, Prakash, can you see this? This is violating your observation, right? Check for all the substrings which are having length that is a factor of original string length. So again, Arun Kumar, you are going to check for each and every possible substring, right? Any substring that can be a contender, you will be checking for that, right? Can we use stack? Komal, you can definitely use anything that you want, but the problem has to be solved, right? So you are free to use any data structure. Find the distinct character in the string using math, then use sliding window of size equal to number of distinct character. Okay, so in that case, Dipanshu, if I talk about this example, you will be using a sliding window of size 2 because there are exactly 2 distinct characters, right? But if you use a sliding window of size 2, you will get false, whereas the answer should be true because this string of size 4 is repeating. Identify repeating string and push. Azim, that is the question, how to identify the repeating string. You are starting your algorithm from the question itself. Is this problem NP hard? No. This problem has a linear solution. Okay, guys, let us discuss the solution. So if the string is formed by repeating the substrings, what if I join the end to the start? I have AB, AB, AB. Okay. What if I create a circular list? So AB, AB, AB. Right. So if a string of size 2 is repeating, this is my original string AB, AB, AB. If a size 2 is repeating, then from index 2, I will again have the exact same string, right? From here again, AB, AB, AB. I have another string which is exactly the same. From index 4 again, I have exactly the same string of the same length, right? If you just join the end to the start and you create a circular string, And if there is a pattern which is repeating, currently we don't know whether the pattern is repeating or not, but if there is a pattern which is repeating, then you will find the same string again and again in that circular string. We can take another example. Let's say that we have A, B, C, A, B, C, A, B, C. Okay. Now here you can again observe that this is your original string from A to C, right? And again you get same string ABC, 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 right? Starting from index 3. And then you can get another same string starting from this index, ending here, right? So you will be getting multiple copies of the same string inside that circle if you just join the end and start. So you can also assume this thing that let us say that you have a chain, right? If you have a chain, what is a chain? Chain is nothing but this is a sequence of similar type of things, right? You have a ring of gold and you attach another ring of gold to it and you keep attaching, you get a chain, correct? Now if you join these two, correct, then which is the start, which is the end, you don't know, right? You can actually say that this part is my start or this part is my start. All of them are going to give you a chain of the exact same length. Similarly, here you can assume this whole string as a chain. If you join these two, now which is the start, you don't know. From any start, you can get the exact same string of the same length, correct? Now, actually adding the end to the start is going to be difficult and that is going to be hard. What we can do is, we can add the same string. If we add the same string at the end of it, so let us say that I have AB, 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 right? Now if I add the exact same string, append the exact same string after this, so I have made an observation that if there exists such a case that a substring is repeating and then forming the complete string, then in the circular string, I will be getting multiple copies of the same string, right? I'm not able to create a circular string. Hence, I have added this same string. I have appended this string to itself, okay? Now if in this complete string, if I am able to get a copy of the original string, can I say that a pattern is repeating? If I am able to find the occurrence of AB, AB, AB inside this string, can I say that a pattern is repeating? Okay, so I have created this string just by doubling the original string. So this will definitely be searched here and here, right? So we should make sure that we are not searching the original strings. So what we will do is we will try to search in this box. Okay. Now, if in this box, if I am able to identify an occurrence of the original string, can I say that a pattern is going to repeat? Yes, no. Let's take a generalized example. Let us not take specific example. Let's say that I have a string A1, A2, A3, A4, A5, A6. Okay. If this is the string, what I am proposing is, let us append itself to itself. So I will be having A1, A2, A3, A4, A5, A6. And now try to find the occurrence of the original string. The original string is A1, A2, A3, A4, A5, A6. If I directly try to search it, I will definitely find it here, right? Because this is the exact same string. So I will have to make sure that I'm not trying to search in the original string. So I will search in this box. Now, if we are searching in this box and if we get an occurrence, let us assume that I get an occurrence here. What does it mean? If these two are similar, right? In this case, you can see that this is the actual case, right? If you are searching for an occurrence of this string, you get it here. This means that if these two are equal, this means that A3 is equal to A1 and A4 is equal to A2 and A5 is equal to A3 and A6 is equal to A4, right? Because if these two strings are similar, then character-wise character, they are going to be exactly the same, right? So A1 is going to be equal to A5 and A2 is equal to A6. I have written this string here and this string here, correct? Now I am able to see that A3 is equal to A1, A4 is equal to A2, and A1 is equal to A5, A2 is equal to A6. What does this mean? Let us also join these two. If these two equations are correct, then A3, A4 is going to be equal to A1, A2. Similarly, A5, A6 is going to be equal to A3, A4. Similarly, A1, A2 is going to be equal to A5, A6. Now you can see that these two are equal and these two are equal and these two are also equal. This means that each and every term is same. Now does this make sense? What have we just proved? We have proved that A1, A2 is equal to A3, A4, which is equal to A5, A6, which means that this is a substring which is repeating, right? Let's take an example of a size 3 substring, right? So if we have ABC, 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 and okay, let's take a smaller string. Now if let's say this is the string, first we just append it to itself, so we get ABC, ABC. Now we'll be finding the occurrence of the original string in this new string, and just to make sure that we are not searching in the first occurrence of this string, we are removing the first character and the last character. Okay, now if we search this string, where are we going to find it? This string can be found here, ABC, ABC, correct? Let us write a generalized version also. So this is nothing but A1, A2, A3, A4, A5, A6, and we have appended A1, A2, A3, A1, A2, A3, A4, A5, A6, and now we are searching for A1, A2, A3, A4, A5, A6. We are searching this in this part, okay? And as per this case, we are finding it after the third character, right? So we are going to find it here. What does this mean? This means that A4 is equal to A1, then A5 is equal to A2, then A6 is equal to A3, then A1 is equal to A4, A2 is equal to A5, and A3 is equal to A6. Okay. Again, if you just combine these two equations, what do you get? You get that A4, A5, A6 is same as A1, A2, A3. Right? This is also showing the same thing, which means that this is a substring which is repeating. Okay. Take example of ABC, BAC. Okay. ABC, BAC. Okay, this is the string which is given. We just append the same string. We append ABC, BAC. Now we remove the first character, we remove the last character, and we try to find the occurrence of ABC, BAC in this. Are we able to find an occurrence here? I can search that A is here, but then B is not there. Then A, B, C is here, D, A. So this string is not being able to find. So I am not able to find the occurrence of this string inside this this given string, right? Which means that if you join this string, if you create a circular string, you are not going to find another occurrence of the same string, which means that there is no such pattern which is repeating. Why to specifically remove first and last character? Okay, so why are we removing the first character? See, this s dash, this is the string s dash. This is created by concatenating the string s and s. This means that you have this string s, you have this string s, and by concatenating them, you have created s dash. Now you are searching for an occurrence of s, correct? If you don't remove any character, don't you think that you will directly find a match here? The first n characters are going to be exactly the same as this string because these two are exactly the same. To make sure that you are not matching it with the original copy here, we are just removing one character. Now similarly, since this is also the exact same string, we don't want S to be matched here with this second copy. So that is why we are removing this character as well. Now what we are proposing is, if you find another occurrence of S inside this part, then that means that this string, if you join the strings end and start, then you will be able to find the occurrence there, which means that there is a pattern which is repeating. Okay. Bhavya Sai, is it clear why we are removing the last and the first character? XXKS creations XX, is it clear now? Santosh, you think about that yourself. If you remove any random character, first of all, what is the purpose of removing the character? Okay. Second thing is, if you remove any random character, does our initial observation holds true? What was the observation? The observation was that if these parts are repeating, then you will be able to find another occurrence of the string inside this circular string. If you remove a random character, right, you break the link. Now these two links are not exactly the same. Right? So first try to understand what is the physical significance of removing the characters. Then you yourself think, just think that will removing a random character make sense here. Okay. You always want, what are we trying to emulate here? Right? We want to have a circular string. Right? If you can create a circular string, then we will go with that. Else, just to make sure that we are having a circular string, we are just adding the same string after it. Now this is also representation of the same string in a circular way. Okay. What about just B? Okay, so Agat has another question. What about just B? If let's say the string is B, 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 B. Okay, now what is the first step? Just add the exact same string. Then you can check in this string, are you able to find the original string? Are you able to find? Yes, this string is found here only, right? So you can say that A2 is equal to A1 and A3 is equal to A2 and A4 is equal to A3 and so on, right? So this means that you have got a repeating substring which is of length 1. Okay. Given string is B. Okay. So you are saying that given string is only B, correct? So now for this you can directly check. This is something that you can do on your own, right? You can directly check that the length of the string should at least be 2. Then only a substring will repeat, right? So I will not discuss this. You can add this to your code yourself.
Okay, let us begin with the very first session on dynamic programming of 21 days of code. This is not going to be a theoretical session. I'm just going to solve 3 problems that you guys had suggested over the LinkedIn page. Let me just give a brief about what DP is. DP is very similar to what recursion is, or divide and conquer is, so as to say. Basically, when a solution to a problem can be achieved by solving the same problem with smaller inputs, and then you solve the original problem by combining the outputs of the smaller problems, that is what is known as DP. In DP, there are 2 important properties: that the problems should be overlapping. What is meant by overlapping is that one state can be reached from multiple other states. And how to identify a DP problem? The best advice will be practice as many DP problems as you can. It's only practice with which you will easily be able to identify that, hey, this is a DP problem. And then in a DP problem, the different possible states are almost fixed. As far as my experience goes, no more than 8 or 9 different states exist of DP. Okay. Akhil, how to find number of states of DP is also dependent upon the question, and the intuition gets clear to you only when you practice. There are some very nice articles about DP that are present on Code Forces or Top Coders, so do read them. They will also help you identify what are the possible DP states that are generally asked. Okay, but without practice, you won't be able to identify that, even if you have studied a lot of theory. Okay, so for DP especially, I suggest you to solve as many problems as you can. Okay, so today we will be taking one problem from simple array DP, one from 2D string DP, and let us say one from greedy or DP. Okay. So one question is by Debarun. The difficulty that I face most about DP is that how to convert a memorization solution to a bottom-up solution. That's a very good question, Debarun. What I personally do, since the time I have started solving DP problems, I always solve them from beginning in a bottom-up fashion. I don't do it this way that, hey, first I code a recursive solution, a top-down solution, and then memorize it and then convert it to bottom-up code. I never do that. I always try to create DP state in such a way that I can directly start with a bottom-up code. As I told earlier, there are no more than 7 or 8 popular states of DP. So do read those articles that are mentioning that, okay, what are the different possible DP states, and then things will get clear to you. Okay. So what I will suggest to you is, when you are solving a problem, solve it anyways, and then at least see the solution of it in a bottom-up fashion as well. Okay. So because when you have seen the solution to it in a bottom-up fashion, then you can remember it for always. And then when a similar pattern comes, you can directly apply that. Okay. So let us start with, so first people ask us to solve the longest increasing subsequence problem. Okay, let us do that. So this is the longest increasing subsequence problem, and let us solve it. So the problem says that we have to find the longest increasing subsequence of a given array of integers A. So basically we will be given an array of integers. The length of the array will be almost 2500 in worst case. And we have to find a subsequence of an array in which the elements are in strictly increasing order. Okay, strictly increasing order means the next element should be greater than, not greater than, equal to, right? Okay. And as this is a subsequence and not a subarray, so it need not be contiguous. So that is also fine. And we are only asked to find the length of the longest increasing subsequence and not generally what the exact subsequence is. So we are just asked that what will be the length of the longest increasing subsequence. For example, in this array A, we can choose 1, 2, and 5. So this is the longest increasing subsequence. 1 is smaller than 2. Similarly, 2 is smaller than 5. And what is the length of this subsequence? It is 3. So we are just asked to return 3. By the way, this is a very popular problem. This is a very well-known problem. And there are 2 different kinds of solutions possible to it. This problem has one order of n square solution that is quite easy and is based upon what we say dynamic programming. And there is also an order of n log n solution to this. Okay. This is based upon what I think it is more like binary search solution. Okay. As today's class is a DP class, I won't be discussing the second order of n log n solution, but I can just send you guys the link to resources where you can study about that. Okay. But do try this because the binary search solution, once it hits you, is very good for you. Okay. Or actually, let us try to solve it in order of n log n way as well as today. Okay. Let me answer what the other questions are. How much time should I give on DP? Like 1 month? Akhil, yes, 1 month. I mean, like 1 month of solving only DP problems is fine. I mean, like it depends upon how many different problems you solve of different difficulty. If you keep on solving easy problems, you are never going to improve, right? Try to solve those problems that you were not able to solve initially. Try to grow with every problem. Okay. And other than practice, any other thing can we do? Harsh, I mean, like for DP, your mind works like a machine learning model. The more practice you will give to it, the more accurate it will get with DP. Okay. I mean, like practice is the best thing. And you see a solution, always implement it, and then also read. I mean, like then also make sure that your mind is totally able to visualize that solution. Okay. Okay. Let us start with this problem. So we are asked that, hey, we are given an array A and we have to find a longest increasing subsequence of this array. Awesome. So how can we do that? Okay. Suppose I know that, okay, I want to see that, hey, can I include, let me actually rewrite this array again. Let me rewrite this array. Okay. 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 So now at every iteration, I will try to see if I can include that particular element, in my longest increasing subsequence. Okay. Let us see how we can do that. So suppose, can I include 0 in a subsequence? I can include this 0 in a subsequence only if there already was a subsequence in which the last element was less than 0, right? Okay. is there any subsequence before it that has the last element less than 0? No. That means this 0 will create one more subsequence, will create another different subsequence of size 1. Okay. Then I go to the number 8. Now I try to see if I can have a subsequence that can have 8 as the last element. When is that possible? That is possible only if before this I had a subsequence that had a number less than 8 as the last number. Okay. What are the subsequences before it that have a number less than 8 as the last number? This is a subsequence that has what we say 0 as the last number. So I can put 8 ahead of it. So what will be the length of subsequence that will be at 8? It will be 1 plus 1, which will be equal to 2. Great. Now I go to 4. Now I will try to include it. When can I include? I can include it only if there was a subsequence before it that had a number less than 4 as the last number. There is only one subsequence that was ending with 0. So the answer will be 1 plus 1, so which will be 2. Okay. Then you go to 12. Now, how many subsequences are there before this number 12 that end with a number less than 12? There are 3, right? This subsequence ends with a 4. This subsequence ends with a 8. This subsequence ends with a 0. So, either I can add 12 after the subsequence that ends with a 0, or I can add 12 at the end of a subsequence that ends with 8 or that ends with a 4. As we see that this is the largest length of a subsequence that ends with a number smaller than 12, so I will add 12 after this. So my answer will become 2 plus 1, which is 3. Now I go to 2. This is the only subsequence, so my answer will become 1 plus 1, which is 2. Now I go to 10. What are the subsequences? This is a subsequence, this is a subsequence, this and this. Out of these, the largest is 2. I mean, like the largest one has a length of 2. So my answer will become 2 plus 1, which is 3. Great. Now I go to 6. What are the subsequences that have a number less than 6 as the last number? This, this, and this. Out of these, the length of the largest one is 2. So this one will also become 3. Great. Then I go to 14. Then I will see here, all these subsequences have the last number as less than 14. Then out of all these, which one has the smallest length? Which one has the largest length? This has the largest length of 3, right? So my answer here will become 3 plus 1, which is 4. Okay, I hope now the intuition is clear. So what we can do is, we can create a DP table. Let me just write the size of A. Then I will create a DP table of the same size. What is the value of the first index going to be? The value of the first index is always going to be 1, right? So I can say DP0 is 1. That is the base case. Now my answer is, initially it is 1. Then what I do, I say for int I equals to 1, I less than n plus plus I. Now I try to find all those DP states in which the last number was less than the current number. So what I will do, I will say for int j equals to 0, j less than I plus plus j. If array j was less than array I, that means the increasing subsequence at that number ended with something lesser than the current element. Then I can say that dpi is equal to max of dpi, comma 1 plus dpj, right? Basically the length, what was the length of this subsequence at that particular number plus adding the current element. Okay, great. So now my answer will become max of answer, comma dpi, because I have to find the largest length. And finally, I can return answer here. What is the time complexity of this? This is order of n. This is also order of n. So the time complexity will become order of n square. I think the answer should be correct. Let us test it. What is the issue? Is it less than or is it less than equal to? 0, 4, 6, 9, 13, 15, 0, 4, 6, 9, 11, 15. Return an integer in longest increasing subsequence or unique, and in which the subsequence is as long as possible. Okay. Here I am returning 14, but the expected output is 15. For int j equals to 0, j less than I. Max of dpi. Initially it will be 0, comma 1 plus dpj. That is also fine. Is it less than or is it less than equal to? Because it says find the longest increasing, find a subsequence of array in which the subsequence elements are in strictly increasing order. So that means the elements are always increasing. I mean, like, equal to is not allowed. But in this particular question, the answer is coming out to be 15. Why will that be the case? That will be the case when int I equals to 1, I less than n plus plus I say if aj is less than, let us say, what if aj is less than equal to, what will be the output then? Then also my question returns 14. Okay, so that is not the issue. There is some other issue then. I created a TP of size n. Initially my answer is 1. Then I say for int I equals to 1, I less than n plus plus I. Okay. Then I iterate over each the element of array I. And then I run a loop from j equals to 0 to j less than I. Okay, that is also perfect. Then I say if array j is less than array I. Okay, then I update my TPI, so which is this TPI, to max of TPI comma, I mean, like, what was the value presently there, and 1 plus TPJ. So that is also fine. But the answer here is 15. Let me try to debug this code as to why this is happening. Let me say that I output my TPI at each stage. This is coming 14 and 14. This is correct. So this should be 14 and 14. That is perfectly correct. And I'm not getting 14 anywhere else. So that is also fine. But I am getting this as 0. Okay, now I got the issue. Initially, the stage of dpi will be 1, right? So initially, each of the elements will be dpn comma 1. That I have set the default value should be 1, right? If it is the only element of dp, then the answer should be 1. So I always had actually off by 1 error. I forgot that. So I mean, like, if that element is the smallest element, like in the case of, suppose, what if say that -1 would have been here, then -1 would have been the single element. There would have been no element smaller than this, right? So the dp state here should be 1 and not 0. So now we will be correct. Correct. So we got this as well, and let's move to the next question. That was wildcard pattern matching. Actually, there are 2 questions like that as far as I remember in interview bit. That is the regular expression match and regular expression match 2. Which one do we want to solve? Let us try to solve the regular expression match 2. Okay, let's try to solve this. Okay, so I'm not sure if any one of you has ever seen regex before, but what regex allows you to is basically to find all the strings in your directory that match a particular pattern. Okay, so basically we are asked to implement a very similar function to how regexes would be working, where the possible values in a regex are fixed. Like here we are told that we have to implement a regular expression matching algorithm that can support a dot and a asterisk. What dot means, a dot can match any character, any single character in my in the whole string. So basically, let me say that, does dot match A? Yes, that is true. Okay. Does dot match B? Yes, that is also true. But does dot match AA? No. Okay, so a full stop can match only one character, any character. Okay, a full stop can match one occurrence of any character. Okay, then the second unique character given to us is asterisk, and asterisk can match 0 or more of the preceding element. What it means is that, suppose we have A star can match A, it can match AA, it can also match AAA, and so on. Okay, so this is what asterisk means: one or more than one, 0 or more than 0 occurrences of the previous character in my regular expression pattern. Okay, so for example, does this string AA, does this pattern match A? No, because though this A is equal to A, but then there should also be a second A, but it's not present in the string. Okay, so the very first one is a string, the second one is a pattern, but the same thing holds. This matches. This doesn't match because the string is AAA, but the pattern is only two A's, so it doesn't directly match. Now, double A, does it match A star? Yes, it does. Why? Because A star is equal to single A, it is also equal to double A, it is also equal to triple A, and so on. So, does AB match star asterisk, dot asterisk? It does. Why? Let us say, what can this dot represent? This dot can represent A, this dot can also represent B, right? And similarly, this can also represent C. That means, what can dot asterisk represent? Dot asterisk can represent AA, it can also represent BB, it can also represent CC, right? So that is why dot asterisk is true, right? Matches 0 or more of the preceding element. Yeah, preceding element is a full stop, so it can match precede 0 or more than 0 occurrences of previous character, which is anything. So it can match 0 or more occurrences of anything. So basically anything can be A, so it will match A, it can also match AB, it can also match AC, and so on. Okay, cool. Now let us try to solve this using dynamic programming. So we are given a string. Let us say that this is the string and this is the pattern. Okay. Now let us try to, I mean, like whenever a string problem is given to you, there are multiple string problems like longest, I mean, like even any 2D array DP problem, you have to, I mean, like normally what happens is that, or even longest common subsequence problem as such in strings. So what you always do, like let us say that we have a string like A, B, C, D, A, and also another string like B, C, E, F, G. Suppose you are given two strings and you try to apply a 2D DP problem. You always try to apply 2D DP in the form of prefixes. That what is common between the prefix of the string A up to index 4 and string B up to index suppose 2. Okay, you always try to compute this. What is common between the first string for up to index X and the second string up to index Y? That is the common pattern in all the 2D DP problems. Adil, yes, a star can match an empty string also, right? I think it should be. I'm not really sure. Let me see. Can star match an empty string? But I think star is, I mean, like if there is only a star, then that means there is no preceding element. Okay, so Adil, if there is only a star, that means there is no preceding element, then the pattern is invalid actually. Okay, because a star is valid only if there is a preceding character. Okay, so I think then the string, then your pattern will actually be invalid. That is what I hope, but let us see. Okay, now, so I will like following this pattern, we will try to create a DP state of two things. That means string till I satisfies the pattern till j. Okay, so I will try to create a DP state where I will say dpij represents true if the string till index I satisfies the pattern till index j. Okay, ठीक है? Always, I mean, like this is one suggestion. I mean, like whenever you are trying to solve a problem using DP, try to represent your DP state in some English sentence. Okay, after you have represented an English a DP state in English sentence, then you can easily find what we say. I mean, like DP. I mean, like the state relations. Which states will it depend upon? Does A match C star A star B? Yes, it actually does. Why? Why? Because there can be zero occurrences of C. Okay, because I mean, like B is nothing but zero occurrences of C. Then two occurrences of A and one occurrence of B. So then it will match. Because a star can also represent zero occurrences of the previous character. So C star will basically just change to an empty string. So that is why it will satisfy. Okay. So now I will try to create a Boolean DP state. How can my DP state be? Let me say that the length of my string is n, and my length of the pattern is p dot size. Okay. Now I will try to create a 2D DP matrix. So I will try to create a DP matrix of vector of bool, I can say, because I only have to represent true or false, dp, which will be having number of rows equal to n plus 1. Why n plus 1? While doing dp problems, I personally like indexing by 1 to avoid like out of bound array checks. Okay, that is why I always create a dp array of size n plus 1, and this will be a vector of pool of size m plus 1. For those who are not familiar with what we say the C++ syntax, this is creating nothing but a dp matrix of n plus 1 cross m plus 1 dimension. Okay, this is doing nothing but this. Great. So will okay, let us say that let us talk about two strings, and let us say that we have a string like this, and this is my pattern. Okay, does nothing match nothing? I mean, like when there is nothing in the character and nothing in the string, does nothing match nothing? It does, right? So what I can say is dp0 0 is true. I mean, like nothing matches nothing. So if I talk about indexing, I'm starting 1 base indexing, so 0 will be here, 1, 2 and 3. So basically 0 0 is representing does nothing match nothing. Okay, great. So now we have taken care of the base case. Now I will try to solve the whole question. Okay, and let us take care of other scenarios as well. The others will always be false. Now I will try to see if the string till index I matches the pattern till index j. Now, what are the different scenarios? The very first scenario is character at index I, at string I, is equal to character at pattern j, right? Okay. First of all, before that, let us take care of the special characters in the pattern, because that is where an issue can happen. Okay, so I can say that if pattern j minus 1 is equal to dot, then I will handle it separately. Else, if this pattern is b, right? Yes. If bj minus 1 is equal to dot, then I will handle it separately. Also, if bj minus 1 is equal to, what do we say, a star, then also I will handle it separately. Else in this case, pattern j is a character, is an English alphabet. So that means it should match the si, right? It should directly match the character at string at ith index, right? Okay, so that means I can say that if string I minus 1 is equal to pattern j minus 1, then only I can say dpij is equal to 2. Sure, Adil, I will try to draw it after I have coded it, and then I will try to rerun with a test case. Okay, cool. Acha. So now once the character that I'm trying to match in the pattern is not a wildcard character, then that means I can only match it with a character, right? Why? I can match this A of the pattern with only an A of the original character, correct? I mean, like I can match this A only with an A from here. Is that correct? So now let us try to see. So that is the one thing. Now let us see what we will do if bj minus 1 is equal to a full stop. If it is a full stop, then what I can do? A full stop can match with one occurrence, with exactly one occurrence of any character. Let us assume that the pij will be equal to nothing but dp of I minus 1, j minus 1. What this means is, let us say, the jth character of pattern matches ith character of string. Suppose if the jth character of the pattern matches the ith character of the string, then basically I have to see if whatever the characters were there in the pattern before the jth character match whatever the string was there before the ith character. Okay, nothing else. The problem becomes interesting if we are taking the wildcard character into consideration, right? because wildcard character can actually match 0 or more than one occurrence of the previous character, right? Okay. Now let us try to see how we can do that. First, we try to find that what is the character that came before P. Okay. What is the character that came in the pattern before this star? What I mean is that for this case, it should return me a C. For this case, it should return me a full stop. For this case, it should return me a full stop. Similarly, for this case, it should return me an A. Okay. What I can say is that I think actually the previous element with the first character, right? Yeah, it will always be the previous character. I'm like, we assume that the patterns are defined. So I can say that previous character is equal to what we say, the B J minus Q. Okay. Okay. So what are the cases now? The first case is that if the string at ith minus 1 is equal to the previous character. What does this mean? This means it matches one occurrence of the preceding character. Okay, so what the problem reduces to, the dpij will be equal to nothing but dpi minus 1 j minus 1, because it has matched one occurrence of the previous character. Okay, awesome. Then what are the other cases? The other case is that it is not equal to the previous character. Then that might happen that ai minus 1, it might actually happen that if the previous character is equal to dot, if previous character is a full stop, like in this case, the previous character was a full stop. So that means it will definitely match it, right? In that case, it will definitely match it. So in that case, I can say that dpij will definitely be equal to dpi minus 1 j minus 1. That thing is clear. Then I will say else if a minus 1 is equal to the previous character, then also this is correct. But is there any other case in which this can be true? In this case, dpij should be false, right? Because it should not match with anything else. Else dpij should be equal to false, right? Can it match with something? What if there are multiple C's and then there is a star? Let us take care of a case like, let us say that there is a C, there is a star, and then I have this C, 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 C. So now when I will be computing this and this will match. Now when I will be computing this and this won't match, okay? Then when I will be computing this and this will be equal to dpi minus 1, this matches till this is also true. When I will be computing this and this dp state, then I will get this is equal to this matches this, which is false, right? This can also match this. So actually I should return dp else if a minus 1 is equal to the previous character, dpij is equal to dpi minus 1 j, because this will take care of the second occurrence of it as well, right? Take care of multiple occurrences. Star can match multiple characters. This thing will take care of this, right? Am I missing anything else? And finally, I will have to return dpnm. But is there anything else that I seem to be missing? So I can say that if there is a full stop, then that means the particular characters definitely match, and then the only thing reduces to a smaller sub problem. So that is fine. If it's an asterisk, let us take care of this case at the end. Else, both are English characters, then they should directly match. There is nothing better that we can do, right? Because there is an English character there, there's an English character there. So then they should definitely match. So dpij will be equal to actually dpi minus 1 j minus 1. Why? Because these characters definitely match, and whatever came before this should also match whatever came before this. So this will be the state here. Now let us take care of this important thing. If the previous character is a full stop, then it will directly match. It will definitely match, right? Yes. Okay, else if a minus 1 is equal to the previous character, else if a minus 1 is equal to the previous character, that means these both are matching, then this problem reduces to, I'm like, multiple occurrences of that, right? Yes. And okay, suppose then I am saying dpi minus 1j. Okay, this matches this. So let us actually try to create the dp table for this thing. This cc matches this c star. Now when I try to match this thing with this thing, I will say that this C matches this C. So the problem reduces to if this particular thing matches this particular thing. That is true, and then it will be true. Now when I say that if this matches this thing, okay, now this thing is matching this thing, so that is good. And now I will try to check if this thing is also going to match this thing. But then here I will be having an issue. How should I make sure that this is true, right? So I should make sure that if there is a previous occurrence of a character, then that can also be a 0, right? An asterisk can also be a previous occurrence of a null character, because this asterisk can also represent that there was no occurrence till here, right? Yes. Then dpij will be equal to dpi minus 1 j minus 2. If the previous character is a full stop, that is correct, but that can also be a previous occurrence of nothing. So that is true, then that is true. What are we missing here? This particular case is a very difficult case to handle, so as to have all the cases. The bj minus 2 will be the character that was just preceding the asterisk, right? And that character can be a full stop. That means it should match with any character, okay? But I might or might not want to match it, right? If I try to match it, if I try to match the ith character of string with this full stop, then the problem reduces to this problem. Or I might not like to match it. If I don't like to match it, then the problem reduces to dpi j minus 2, right? J minus 2 will make it 0 occurrences of the pattern of this character and the string till now. This makes sense. Okay. Now in this case, I say if a minus 1 is equal to the previous character, then either I will like to match it, and then the problem reduces to this, or I will not like to match it, right? Or I will say that I don't want to match it, or this is equal to dpi of j minus 2. In that case, if we take care of this string, this problem will be equal to either I match this C with this C, then the problem reduces to dpi minus 1j, which will be equal to matching this C with this C star, okay? Or if I match this C, or this reduces to dpi of j minus 2, which will be false. Now when I try to match this and this, either I will match both of these. If this is equal to this, the problem reduces to dpi minus 1j. dpi minus 1 will be this and dpj will be this. How can I match this? I should somehow make sure that this is true, right? I think that is the only case that is left. I mean, like, if we match this, how should a C star match a C? Because this can mean a one occurrence of C. So as this matches this, the problem can also reduce to matching dpi minus 1 j minus 2, right? Or dpi minus 1 j minus 2. That will be one thing. dpi minus 1 j minus 2. Why this? This will mean this is non-occurrence of this. This is the second occurrence of this, or more than second. This will mean this was the only occurrence of it. Okay, and this thing will mean what? This thing will mean 0 occurrence. Correct. Now this should be correct. Now the only question comes, can our pattern be something like this? C star 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 star. Then I can also say that while, first let us say that can that case happen? Wait a moment. And previous index is equal to what we say j minus 1. while previous index is greater than equal to 0 and pattern previous index is equal to star, I will try to minus previous index. So now my previous character will be nothing but b of previous index. Now, if the previous character is a full stop, the problem reduces to either I will match it. Now this j will be nothing but, I think let us actually first try to see if what all cases does it pass. Let us then try to see. So we are failing at this case, and why? Because this is a zero occurrence of this and this should match, right? And A, B star C means zero occurrence of this. So this should return true. Let's actually take this case and then see how we are going to create a string. So our 2D table will look like A, and this will be C, and then this will be A. Just let me declare a 0, 0 as well. This will be a A, this will be a B, this will be a star, and this will be a C. Does an empty string match an empty string? Yes, it does match. Now I try to see if all rest are 0. If I try to see does A match A, this will go into this particular scenario, right? Does A match A? This will be the scenario when AI minus 1 is equal to BJ minus 1. So this will be nothing but equal to this. So this thing will become 1. So that is fine, right? Now the problem is, does A match A comma B? No, it doesn't, because B is also a character and B is not equal to A. So this will not match. Then the question is, does A match A B star, right? So here we will try to see that we have a star, we have an asterisk here. So the previous character is a B, Yes. We go into this case, else case. Correct. We found where the issue is. dpij is either equal to dp of I minus 1. Okay, so I can match none occurrence of that. I mean, like, then it will be equal to dpi comma j minus 2. What it means is that it will only match 0 occurrences of previous character, right? And it should match the 0 occurrences of the previous character. So now this particular case should be correct. Let me take it as a custom input. Yep. So that case we have handled now. That thing is perfectly correct. This can only match 0 occurrences of the previous character. This means this will match dpi minus 1j, which will match more than 1. I mean, like, first or second to greater than 2, greater than equal to 2 occurrence of the previous character. This will match 0 occurrences of the previous character, and this will match the first occurrence of the previous character, only one occurrence of the previous character. Now this makes sense, but if there is multiple stars, then it might fail. But first we have to see if there can be multiple stars, right? Rest all should be fine. Yes. And now the question is, will it pass submit case? Can there be multiple stars together? There should not be, but can there be? I mean, like, it's not specified in the input. Let's try to submit it. A, B, C, D is not matching A dot star, C dot star, and this. Interesting. What are we following? Here we have told dpi minus 1. Okay, we have taken care of this case. We have also taken care of this case. We didn't actually improve this, right? This was the dpi minus 1, j minus 1 means one occurrence of the previous character. Okay. dpij minus 2 means more than one occurrence of the previous character. This can also be 0 occurrences of the previous character, right? Or not. If previous character is equal to this, then the problem reduces to either I will match the previous character with this, then that is fine, or I will reduce the problem to matching this with something else. Let us try to take this case and then see where we are failing. A, B, C, B, C, D, and A dot star, C dot star D. In this case, this dot star is representing this B, and this dot star is representing this B and C. Okay, if it is a dot, if the previous character is a dot, then it can match any number of previous characters, right? Yes, then it can actually match any number of the previous characters. So then we just have to find one of the previous indexes where it can match. So that means this is equal to another order of n loop, right? This will be another order of n loop where I try to see if anything matches till here. I mean, like if there is any part of this substring till here that matches this particular index, because baki sabko, because other things I will just satisfy with this stuff, with this full stop. That makes sense. So the only question reduces to this, that if there was any star here, right? So then the answer will be to false, let us say. And I can say that for int I equals to 1, I less than, let us say I is equal to 0, I less than what is my current character, I less than, for int L is equal to 0, L less than I plus plus L. That means if there was any character where dp of L k minus 2 was true. So was n is equal to tp or equals to tp L comma k minus 2. What I mean by this is, was there any pair like this, that hey, I mean, like when I'm trying to match this ABCBC with this thing, okay, I will try to see if there was any pair that matched till here in this particular string. After that, everything I will match with a full stop. Okay. So TPIJ will be nothing but was any. This has increased my time complexity, but hopefully should satisfy this case, right? This should satisfy this case. Correct, it does. So now, is there anything I'm missing? Because then I haven't still found that if there can be multiple characters. Interesting. Can there be? First, let us try to submit it and then we will know. Let's first try to test and then we'll submit. Am I missing any other case? I don't know. Cool. I got it correct. There is not a case of any character, any star, any multiple stars together. But I mean, like, I hope you guys were able to find, I mean, like, how we actually found the approach. What were the different test cases that we had to see? Okay. And still we missed out on some of the edge cases. Okay. I will take up the doubts on this question as well as at the end. But let us solve one more question for the day that people had requested, and then we will take on doubts. Okay. What is the next question? The next question is the max sum path in binary tree. Let us do that question and then we will take the doubts. So in the max sum path in binary tree, we are given a binary tree that is rooted, right? I think we are given a, yeah, we are given a tree node. So I mean, like if you are given a tree node and then it's a DP problem, that is still an easier problem. Why? Because you know the root of the tree and that helps you in some things. So we are given a binary tree T and we have to find a path in the tree of the maximum sum. Okay. And the path can start and end at any node. So by the way, I mean, like, what is the definition of a path? A path is a sequence of nodes such that no node is repeated more than once. So there is no cycle. It's a simple path. Okay. So now let us try to take care of, I'm like, let us see the examples first. In this example, the largest path starts from this 2, goes up to 1, and then comes down to 3. So the weight of the path is 2 plus 1, which is 3, plus 3, which is 6. So 6 is the answer. In this case, what is the maximum sum path? The maximum sum path is only this node minus 10. Okay. The maximum sum path is nothing but only this node, which is minus 10. Okay. Acha. Now let us try to see that, hey, let us try to see, can we include a particular node in the path? How can we know? I mean, like, what will be the weight of the path if we include that node in the path? Okay. If we include this node in the path, that means either I will have a path from the left side that will join it and a path from the right side that will join it. What I mean is that suppose there was some tree like this, that here is a 1, and here's a 2, and here's a 3, then here is a 4, and then here's a 5. Okay, so when I try to include the upper wala 1 in my path, then I will join it with one path that was coming towards upside from the left hand side. What was the weight of that path? That path was 3 to 2 with having a weight of 5. Similarly, I will also join it with a path that will start at 4 and will end at 5. That will only be in the right hand side of the subtree. This is also a very popular problem, by the way. So I will also join it with a path that is from 4 to 5 and having a weight of 9. Okay, suppose the path on the right hand side, these nodes were -4 and -5. These nodes were -4 and -5. Would you ever want to include these nodes in the path? No, right? Why? Because their sum will be less than 0. And that will be bad for me. I mean, like, I don't want to subtract anything from the path. That is a very bad thing for me. So I will always add the maximum path on the right side with weight greater than equal to 0 and the maximum weight path on left side with weight greater than equal to 0, because otherwise it's going to reduce something from my weight, so I don't want to do that. So let me say that I can make a recursive function that will return me the maximum weight of the path from the left side node and the maximum weight of the path from the right side node. So what I do is that a max path node, which is past a tree node. Okay, in this case, I always try to write the code along with the solution because that makes more sense. I will say, the base case is that if a is null, in that case I can just return 0 because there is nothing, it's a 0. Okay, else what I will try to do, first thing I will try to find what is the maximum path on the left hand side, which will be equal to max path node on a left. Similarly, I will try to find the right path, which will be equal to max path node on a right. We will always try to have the paths have a weight greater than or equal to 0, right? So I can make it the left path is equal to max of 0, max path node of a to left. And similarly, max of 0, max path node a right. Interesting. Now what should I return? I should return the value at a plus left path plus right path. That is the maximum path weight that will end at my current node A, correct? Great. So that thing makes some sense. In fact, if I know this thing, then I don't need to do anything else, right? I can just paste this thing here. I don't need a separate function as well. And I think this should work directly. Oh, this is max path sum now. So, and then let's try to test it. This doesn't work. Why doesn't this work? Given a binary path tree, we have to find the maximum path sum. The path may start and end at any node in the tree. Okay. The number of nodes are 10 to the power 4, so the integer overflow will never happen because the maximum path will be 10 to the power 7 something, so that is fine. If a is null, I'm returning 0. Here I'm returning something very big. That is also not going to happen. Interesting. A eval plus left path plus right path, right? That I am not doing wrong. That is correct. If left path is this, I have to say max of 0, this. I think I did return correct, right? I think yes, this was an addition issue. What happened? The expected return value is 7347. Okay. And I'm returning something 93,096. Okay. If A is null, I return a 0. Else I try to find what is the max path sum on the left side. Okay. and I also try to find what is the max path sum on the right side. Okay, and then I return the value at that plus left path length plus right path length. That also seems to be fine. But why my answer is coming as wrong? Can I have a path from up to down? Yes, I can have that. And what I will return? Yes, I got the issue. What we are, I mean, like, what is the issue with this is, suppose your tree is like this, then what we are doing wrong is this thing. I mean, like, we can't have it in this function. We should have another function which says int max path ending here. Okay, int max path ending here is this, given a tree node value at a. So now I try to find what is the maximum path in both of those subtrees. So this, okay, I try to do the exact same thing. Now if a is equal to null, I do this, and this is the same thing. Okay, now I will have a global answer variable which will be initially, let us say, int min, and I will say that answer is equal to max of answer, comma, what I got from here. I mean, like, that is a triangular path, right? That is a triangular path. But now I can't return this path. For example, suppose there was a 2 here. There was a, let us say, a 7 here. Okay, this 7 needs to know a very straight path that will be ending at 7. So it can't include a path that will be 3 to 1, -4, -5. It should be one straight direction path, right? So I will return the a plus max of these two, max of left path, comma, right path. Okay, because now I need only a one direction path. I don't need a cross and a straight line path, right? That is wrong. So answer is equal to int min. So I will always have to set it in when I start the function. So answer will be int min. That makes some sense. Then I will compute the left path, I will compute the right path, and I return this. Great. So I will just do a what we say, max path ending here of a, and then I can finally do return answer. That should be correct. That should be correct. Earlier I was passing this thing completely there, which is totally wrong. Answer is equal to max of answer eval plus what is the issue here? Okay, I missed a semicolon. Did I miss anything else? No, seems fine. Return a val plus this. This is quite fine. I think this was the answer that was supposed to be written. I'm not really sure, but this seemed to be one. Yes. Yep. So I hope you guys were able to understand that what my function was returning was a path that could be like this and then something here. So this was a triangular path, which is not correct. So then it will cause an issue up on the upper side. Okay. So then I try to let me submit it and it should be working. Okay. We got 389 out of 400 points. Interesting. Let's briefly watch the n log n solution of the longest increasing subsequence and then we will end the lecture. Okay. Acha. Now suppose you are creating a subsequence. Okay. Now let us say my subsequence is like this. I mean, like, I'm not going to explain that solution in a lot of depth because we can discuss it in the section that we will be discussing. I mean, like, we can have a separate video on discussing this as well. In fact, that will be a very good thing. We can upload a video there to the channel. But I mean, like, I will still try to give a kind of an intuition to this. Okay. Suppose we get, I mean, like, we are trying to create a longest increasing subsequence. Okay. When we get a 0, our initial subsequence will be only 0, right? This will be the initial subsequence. Okay. Now, when we get a 8, where would you like to put this 8? You would, I mean, like, it makes total sense to put this 8 here. Correct? Okay. Then we get a 4. Now, we try to see where can we put this 4. this 4 should, replace a particular number, right? This 4 should replace a previous number. This 4, by the way, do you guys, guys, try to see that this particular array that we are creating is sorted, is always sorted, okay? Now we try to see which 4, which 4 can go where. Out of these two, 0, 8, 0, 4, which is a better thing to take? 0, 4 is always a better thing to take, right? Because 0, 4 can later be expanded to 0, 4, 7 of size 3, but 0, 8 won't be able to. So 0, 4 allows us more scope to expand it, right? So what we do is we try to find the first number in the current increasing subsequence that is greater than 4. Okay, so we find this 8, we replace this 8 by 4. And what is the length of the current subsequence? It is still 2, right? What is the length of the current largest subsequence? It is still 2. Great. Then we go to 12. We try to find the first index that is greater than 12. There is no index. So that means we put 12 here. Now what is the length of the largest subsequence? It is 3. So basically try to see that the array that we are maintaining is storing the length of the largest subsequence. That will be our answer. Now we go to 2. We try to find the first index that is larger than 2. We find this is 4. We replace this 4 with 2. What is the length of the largest increasing subsequence till now? It is still 3. And by the way, if you would have seen till here, the length of the largest subsequence is 3, right? Great. Now we try to put 10. We put 10. We find this is the best place. We replace this by 10. And what is the length of the largest subsequence till now? It is still 10. And also, if you would have seen, the length of the largest subsequence till this place is also 3, right? Okay, now we go to 6. We replace this 10 by 6. Now we go to 14. There is no number that is greater than 14, so we put 14 here. And what will be the length of the largest subsequence now? It is 4. And you also see that the length of the largest subsequence is 4 here. Okay, now let me try to write the code, and then the other things will start becoming more clear to you. Okay, so let me comment out this code. This was the DP code. And let me write the binary search code now. Initially, my current array will be empty. Okay. Then I will say for I equals to 0, I less than n plus plus I. First thing I will check if array I, if current array dot empty or array I is greater than what we say current array dot back. If any of those two cases is true, what does that mean? If these two cases is true, that means I will push the current number, right? Because here 14 was larger than whatever was here, that means 6. So I just pushed back 14. I increased the size of my current array with 1. Okay. Then what is the other case? In the next case, I will try to find first index that is greater than or equal to the value greater than equal to AI. Okay. How can I do that? As the current array is always being maintained in a sorted order. If you would have observed this above thing, this would have always been maintained in a sorted order. I can binary search this. I can say L is equal to 0, R equal to 0. Then I say while L is less than equal to R, mid is equal to L plus R minus L by 2. If array mid is greater than equal to array I will say index is equal to mid, R is equal to mid minus 1. This is normal binary search. Okay. Else L is equal to mid plus 1. I'm basically trying to find the first index that has the value greater than or equal to mid. Okay. So I will say int is equal to minus 1. And what I do after this, I just change my current array int to array I. Okay. What should R be? R should actually be equal to current array dot size -1. Awesome. And finally, I can just return my current array dot size, because that was always storing the length of the largest increasing subsequence till now. Let us try to test it. Yep, and this is correct, and this is submit. Now what did I do? Shit. Okay. Again, I am failing at this case. Oh, I have a runtime error. Why do I have a runtime error? I say current array dot empty or array I is greater than current array dot back. That is fine. Am I anytime in? Yes. Okay, I have to find the very first index that is greater than or equal to the current number. Okay, can the index be -1? Can it happen that all the numbers are greater than or equal to the current number? In that case, I will just return 0, right? In that case, I will just return. Okay, when can index be -1? This can be -1 if all the numbers in the array are smaller than. So yes, if all the numbers are smaller than that. So I can say if index is equal to -1, that means all the numbers in the array are smaller than that number. Then this will be happening, right? If index is equal to -1, when can that happen? That can happen only if all the numbers are smaller than that. All the numbers are smaller than that, because if there was any one index that was greater than or equal to AI, then I would have changed my index to that mid, right? And I'm saying that all the numbers, all the indexes are smaller than that. Else if array mid is greater than equal to array sorry, we have to actually check else if current array mid. Okay, so this is the issue. It should be current array mid. Let us test this. So we just had a naming issue, and if we were checking array mid, we should have checked current array mid. This, I mean, this is running wrong. That is another issue. I say that okay, and I can then set the current array mid is greater than equal to AI index is equal to mid. If current array mid is greater than equal to AI, then that might or might not be the first index. Then I try to reduce it. Okay, current array dot pushback is correct. My current array is the array. L is equal to 0, R is equal to current array dot size -1. That is perfectly fine. I say while L is less than equal to R, I try to find mid. I try to see what is the number at that mid index. Is it greater than or equal to the current number that I'm going to add? If it is greater than, for example, suppose I was going to add 15 here, I go to 6. Is 6 greater than or equal to 15? No, it is not. So I will have to search here. Is 14 greater than equal to? Yes. 14 is also not, so I will go here. So let us say that we were trying to add a number 3. Let us say we were trying to add a number 3. I try to see here. I'm like, is 6 greater than equal to 3? Yes, it is. So it can be the answer, or the answer can be somewhere here. Correct. So, and I'm returning the current array dot size. That makes some sense. That makes the sense. But why is the answer 14 in? Why is the answer 4 in this case? The answer should be something like 14. So I try to find the first index, then index is equal to mid. If index is equal to, this should not be happening. Oh, this is correct. Yep, you're correct. Because I had added that if condition while debugging, I forgot to remove that. That was the issue. Correct. We got all the points correct. I think many people don't know that this problem can also be solved in n log n in this small code only. Okay. So in this small code, so that was a new thing.
So today's session is on the dynamic programming day 2. So here I have the questions, and the questions demand that has been made is of buy and sell stock 2. So let's dive into that question. Okay, let's get started. Say you have an array A for which the ith element is the price of a given stock on day I. Okay, you have to design an algorithm to find the maximum profit. Now you may complete as many transactions as you like. That is, buy one and sell one share of a stock multiple times. However, you may not engage in multiple transactions at the same time. That is, you must sell the stock before you buy again. Okay. So let's actually see the example and let's see what it means. So we have an integer array which represents the day-wise stocks that are available. Now the output is 2. That means, so here it says that we have bought the stock on day 0, that means 1, and we have sold it on day 1. Okay, first of all, let me name them. So let's utilize this space. Let's say we have so this is index 0, 1, 2, and index 0 we have 1, 2, 3. So we bought the stock on day 1, on day 0, and we sell it on day 1. So we get the profit of 1, right? And if we buy it on day 1 and sell it on day 2, so that will be again a profit of 1. So that means total profit is equal to 2. So that is what this example is saying. And if we look at the next example, so we can buy the stock on day, so it says that buy the stock on day 1, that is cost is 2, and sell the stock on day 2, that is at this, right? So that means the profit is 10 minus 2, and that is 8. Now the thing it says is that we can buy and sell multiple stocks, but the constraint is that we cannot keep on buying the stock and keep storing it with us and with the intent of selling it later. We cannot do that. So please understand this problem. Many people feel confused with the problem. So it says that once you have bought the stock, first you have to sell it, and then only you can again buy it and then sell it, right? So that's what the problem is. So let's say we have 7, 1, 5, 3, 6 and 4. Okay, these are the prices of the stocks on days. So 0, 1, 2, 3, 4, 5 are the days. Now let's talk about the brute force solution first. Okay, now the brute force solution would be that I can buy the stock, right? So I can buy the stock here, and then I can see that when can I sell the stock. Okay, so if I buy the stock at first at 0th day, then can I sell the stock at any day? No, right? Because this stock is greater than, has a greater value than any of the stock, right? So therefore I cannot simply sell this stock. Let's move to the next element. Now on the next element, if we buy the stock, then we can sell it on day 2, we can sell it on day 3, on day 4, day 5, right? So now the possibility is that let's say I sell the stock on day 2, so that will give me a profit of 4, and plus now there is a sub problem, isn't it? So I will add the cost to the sub problem, and the sub problem is of 5, 3, 6, 4, isn't it? Now this is the sub problem that I can try buying this stock and sell it on the further days. So just what I have discussed now will be applicable to all the sub problems. Okay, so this is the case when I have sold my stock of 1 on day 2, that is at the cost of 5, that will give me a profit of 4. Now if let's say I sell the stock on day 3, so that will give me the profit of 2, and I have a sub problem which is 3, 6, 4, right? Likewise, if I sell the stock on day 6, so that will be a profit of 5, and that will be giving me the sub problem of 6 and 4, right? And if I sell the stock on day 5, so the profit is of 3, and I will get the sub problem of 4, right? So this is it. Now this will happen with every element. Okay, so as I move to 5, this will happen with 5 as well, that I can, so first of all, when can I sell this stock of 5? So I can sell it on day 4, right? So that will give me a profit of 1, and the sub problem is of 6 and 4. So for 5, that's it, right? Then we will move on to the next element, and 3 can be sold on day 4, so that means give me a profit of 3 plus 6, 4, and I can sell it on day 5, so profit is of 1, and the sub problem is this. right? So likewise, I can keep on going on, and that will give me these sub problems for every element. Okay. Now the thing is that there are n elements, and if you see from this visualization that I have created in here, so if you see on the first level, we are for n elements, we are having n iterations, we are having n possible cases. So that will give the time complexity of order of n square, right? Yes. So Goyal TY, yes, you can. So if you are buying a stock on first day, and if you are selling the stock on the second day, then you can immediately buy the next stock on the second day. Okay. So if you see from the problem that has been given on the platform, then you'll be clear. Okay. Cool. So now for n elements at the first level, we are having n possibilities. So the time complexity is of n square. Now this is happening n times, isn't it? For every element, this could happen n times in the worst case. So that is the first level, right? And now such that I'll be having the next level having n elements, n possibilities for n elements, right? Then again at the next level, I'll be having n elements and so on. So that will be like n into n into n and so on. So it will be n to the power n. The time complexity is of n to the power n, which is very huge, okay? Which is very huge. So now let's see how can we optimize this using DP. So this was the brute force approach. Now let's see. So we have 7, 1, 5, 3, 6, 4. Okay, let's say this is my DP array, and here this I'm going to do in bottom up fashion. Okay, I have a 1D array. Now, if let's say I have only a single stock, then is there any point of so there won't be any profit, right? Will there be any profit? No, right? Can we make it 0? So here we can put the value 0. Okay, we can put the value 0. Now, so basically at DPI, I will say that it will be nothing but maximum profit we got by doing transactions only till that ith position. Okay, so if let's say I am here, then this is the, let's say, the last point where I will be calculating the profit for, and that I'll be doing for every element. Okay, cool. Now I am at this index, I am at this position. Now the thing is that either, so basically we are actually taking it in a way that what profit can I achieve on this ith day. Okay, so I can either sell a stock or I don't sell a stock. If I don't sell a stock, that means whatever is present over here will be my answer. Okay, but if I sell a stock, then I'll be actually moving from the first location till the I minus 1th location to check if there is a value which is lesser than this value on which I can, so let's say I am at index this. Okay, now for this index, let's say this is I and J is at this position. So basically either I do not sell any stock on this day, or let's say I sell a stock this on this day. Why am I able to sell stock J on this day? Because J is lesser than I, right? Element at J is lesser than I. So that I have to keep on checking. So there are two possibilities now, that I can sell a stock on one day, on that particular day, or I cannot sell a stock on that day, right? So here what we'll get, so the idea is that for I which goes from 1 to n minus 1, okay, and let's say this is our DP array, and DP0 will be initialized to 0. Now we'll be doing for J which goes from 0 to I minus 1. Okay, what we'll be doing? So also what we have to take, so we have to take that when we are not considering the element, so in that case whatever is the answer at DP I minus 1, we will have that. Okay, we will have that. Now this is the case when I am not selling the stock on that particular day. Now when I have to sell, so I'll be moving through this loop. What I'll be doing is DP of I will be equal to maximum of dp of I, okay, comma d ai, that is the so wait a minute, it will be whatever the profit is at dp of j plus a of I minus a of j. So this is the additional profit that I have got while selling the stock on day I that I have bought on day j. So this is the profit, and this will be added to whatever was the profit on dp of j. Is that clear? Is this thing clear? That whatever was the profit on jth day, that will be added to the profit that I have achieved now. Okay. So this is what the idea is, and this we'll do for all the elements. Cool. And the time complexity would be order of n square, right? We have two loops. So from order of n to the power n, we have actually come to order of n square. Are you guys able to relate that why it's order of n square now? How are we processing through this? How are we moving through this? Is it fine, guys? Cool. So let's code it quickly, and then we'll move on to the more optimized solution. Okay. So let's quickly code it. So we are taking an array, right? So int dp, first of all, let's consider the size as well. Okay. So here I have int n where I'll take the size. Then if n is equal to 0, or if n equal to 1, then we'll return 0. Okay, cool. Now let's move ahead. Let's create our dp array, and let's initialize all the elements to 0. So dp of I is equal to 0. Now moving forward, so we are going to all the elements starting from index 1. Okay, so starting from index 1, we go to all the elements, and what we'll do, we'll put the dp of I is equal to dp of I minus 1. That is when we are not selling the stock on day I. Okay, but when we are selling, so we have to check that when that stock was bought. Okay, we will go from 0 all the way when j is less than I and j plus plus. Now, so it will be nothing but dp of I is equal to maximum of dp of I comma dp of j plus a of I minus a of j. Okay, and then we'll simply return dp of n minus 1. Let's see if this works. Cool, it worked. Okay, so we have actually got the partial points. Now this can be further optimized. Okay, let's see the optimized case now. So here, let's move forward. Now this can be further optimized if we make some observation. Okay, so what I'm doing over here, I am actually, whatever was the profit on day j, I am adding it to my current profit, right? Okay, so here we have this solution. Cool. Now dp of j plus dp of I minus ai minus aj we have. Now if I tweak this a little, so what will I get? I will get ai plus dp of j minus aj. Can I write it like this? Can I write it like this? Okay. So now so basically we have to increase our profit. Okay. To increase the profit, I want this to be increased, and for that I want this to be increased, right? So to increase this, that is the difference shall be increased. Okay. So for that we can maintain. So we were just iterating through the j loop to get this difference so that this could be maximized. We were checking for which j value is this difference maximum. Now instead of iterating through that j array, we can actually keep on storing the maximum value of this till now. Okay, till now. Does that make sense? we were only moving our j loop for checking that for which value of a j are we getting this, are we getting this as the maximum, so that our complete the complete value is maximum, right? So instead of going to each jth position, we can actually store this particular value in a variable, and then we can keep on updating that variable. Yes, the greedy method is of order of n time complexity, and we'll also see that how this can be changed to order of n time complexity. Okay, Ankit, does that make sense? So let me just code this thing now, or let me just code it. If you guys still have any issue, we can discuss it, okay? So let's just proceed now. So here basically we have to change, we have to remove this loop, okay? So for that, basically we have to keep on storing this particular value, as in we have dp of j plus, we have this here. Now I am changing it a little to get a of I plus dp of j minus a of j. Now I am trying to store this value. So here I can maintain a maxi variable, let's say, which is initially is equal to 0 minus a of I, a of 0. Okay. So basically this will be gone. This will be gone. And we have maxi is equal to, sorry, first we have to update the dp of I. So dp of I is equal to max of dp of I, comma, a of I plus maxi, right? So basically here this value has been replaced by maxi, okay? And also we have to update our maxi variable, max equal to maxi, comma, dp of I minus a of I, okay? And here we go. So now we will simply, so here we have actually eliminated the jth loop. Does that make sense to everyone? Now let's see if this works. Let's see it, and here we go. Cool, we have actually got the solution correct. We have got all the points. So now this is the solution of order of time complexity is equal, is so time is order of n square, right? Sorry, order of n, and space is order of n only, right? Order of n. But the space can also be optimized in this case. The space can be optimized. If you carefully notice over here, then we have, so basically dp of I is equal to dp of I minus 1. For every ith position, we are actually, we are reliable on this dp array because we want dp of I minus 1. So if we store somewhere this dp of I minus 1, and if we utilize it in some way, so then we can, actually do it in just order of one space. Now I want you guys to try that thing. So here we are at time of order of n and space of order of n. So let's move on to the next question, and the next question is minimum jumps array. So this is a very very important question. So given a array of non-negative integers a of length n, you are initially positioned at the first index of the array. Each element in the array represents your maximum jump length at that position. Return the minimum number of jumps required to reach the last index. If it's not possible to reach the last index, then return -1. Okay. So the first and the only argument that we have here is of integer a. Now let's see what the problem says with the help of an example. So we have 2, 1, 1, and the array is 2, 1, 1. So the output is 1. Why? Because the problem says that from index 0, we have to reach the last index. So we can take simply the jump of 2 to reach the last index. So the element at that position signifies that how many jumps we can take at max. Okay, we can take the jump of 1, we can take the jump of 2 for this particular variable. Here we can take just the jump of 1, again we can take the just the jump of 1. So let's say I have 2, 1, 2, 3, 1, 1, 4. Okay, now let's maintain the DP. So here we are going to do the DP thing. So this is the bottom of DP that I have taken. So basically, if I talk about the brute force approach in this case, then what we'll do, we will check till all the, so whenever I am at some position, I can go to, from here, this is 2. So I can go jump to here, or I can jump to here, right? Then I will again call for this part as well as this part. Okay, till the position that I can jump for the first element. Then after jumping to, let's say 3, I will call for rest of the sub problem, and after jumping to 1, then I will call for rest of the sub problem. So this will go on for every element, right? So this is the brute force solution. Now let's talk about the DP solution. For DP solution, we have created the DP array. Let's name it 0, 1, 2, 3, 4. Okay, so basically the DPI signifies that till that particular position, how many minimum number of jumps we can take. Okay, so DP of I tells the minimum jumps we can take from 0 to I. Okay, so if we are standing at this position, then we don't have to take, so considering this position as the last index, we don't have to take any jump. So this will be 0, right? Now if I am at index 1, then from index, so so to calculate the number of jumps to reach index 1, that means, so let's name it here 1, 0, 1, 2, 3, 4. Okay, if I want to go to index 1, then I have to start from 0 till I minus 1. Okay, I will check that from index, so let's start J from here. I will check that if from this position I can go to this position or not. How to check that? We will do it in a way like 0 plus, that is the index J, plus A of J. If it's greater than equal to I, that means we can move from index J till index I. So this is 0 plus 2, that is 2. It's greater than equal to 1. Here 1 is I. So we can move from this element to this element, and we will get what? We will get nothing but the cost, the jumps we need to reach at this position plus 1. Does that make sense? Now we come, we are done with these positions. Now we go we place our I at here, and J will again be placed at 0. Okay, so from 0, can we move to this? So this is nothing but 0 plus 2, and that is 2. 2 is greater than equal to 2. We are at index 2 now. So yes, so that means there will be nothing but 0 plus 1. So 1 will come over here. Now our J will move to this position. Let's see if we can from J till I. So this is nothing but 1 plus 3, that is 4. It's greater than equal to 2. So yes, we can jump from this position, that is from this position to this position, and that will be nothing but whatever is present at this position plus 1. So we have to check that if dp of I is equal to max of dp of I, comma dp of j plus 1. So right now dp of I is maximum, then dp of j plus 1. So it will remain 1. Okay, and this we will go on till the loop is completed. Okay, let's first code it up, then we will complete the array. So we have, so we'll take the size of the array, and if the size of the array is equal to 1, that means only one element. So we'll return 0. If the size is equal to 0, but if the first element is equal to 0, in that case we will return 0, right? We will return 0. Sorry, if n equal to 1, we will return minus 1, because if we cannot take, if we cannot reach to the end element, okay, sorry, this will be minus 1. That means we cannot go, right? Now let's move on. Let's dp is equal to dp of n. Now dp of 0 be 0. So for int I equal to 0, So sorry, we'll start with 1. I less than n I plus plus, and dp of I shall be initialized to int max. Cool. Now what we have to do, we have to run our second for loop, that is int j is equal to 0 till j is less than I and j plus plus. Then if, okay, so dp of I is equal to maximum of dp of I, comma, we have dp of j plus 1, okay, and we will at the end return. So if the last element was reachable, that means if dp of n minus 1 is equal to int max, right? So that means it was not reachable. In that case, we will return -1, else we will return dp of n minus 1. Okay, where did it fail? Okay, so we actually didn't check the condition here. The condition needs to be checked, that if a of I, if j plus a of j is greater than equal to I, and also we have to check that if dp of j is not equal to int max. Why? Because it's a possibility that we could not reach dp of j, right? So in that case, but if we can, so we will calculate, right? Now let's see. Okay, sorry, this should be minimum, right? Okay, we actually have got the partially correct solution, because the thing is that this is also possible. This the solution to this problem is also possible in order of n. That is the greedy approach. I want you guys to explore that approach. Okay, here we have discussed the so if anyone has any doubt, you can ask in this particular solution. So Alind, we are adding aj to j because we are checking that if from jth position, if we are able to go to I or not. Okay. Why are we doing j plus a of j? Because we are checking that if from some position, will we be able to go or not? Okay. So if we are at this position and we are trying to jump to this location, we won't be able to go because we can only take at most 2 steps. So that's why we are checking j plus, that is, this is 0. So 0 plus 2, that is 2. It's lesser than the index I. Let's say I is here, and therefore we cannot jump till here, and therefore we are checking the condition. Okay, is that clear? Sure. Let's move to the next problem. And next problem we are taking is of edit distance. Okay. The problem is, first of all, it's very important. So the problem is important because it is asked in many interviews. Okay, it's very common, and you should definitely understand it, like how it works. So let's dive in the problem. So it says that given 2 strings A and B, find the minimum number of steps required to convert A to B. Okay, each operation is counted as 1 step. Now you have the following 3 operations per word permitted on a word. The first is, it says that insert a character, okay, delete a character, and replace a character. So to convert a string A to B, I can do these 3 things, okay, and I have to find the minimum steps that I can take to convert one string to another string. For example, in the input, let's say we have ABAD, and we want to convert it to ABAC. So here we can simply replace D by C, right? And that will give the cost of what? 1, right? Now here in this case, it says that the cost is 2. Why? Because here we are replacing S with T, that adds to the cost of 1. Then here we are actually inserting. So after converting this S to T, we will be inserting I. Okay, so that will add up another 1, and the cost will be 2. Okay. So is the problem clear to everyone? So basically we have to convert given 2 strings are there, right? So we have to convert string A to string B. We can make 3 possible conversions with each character, that we can replace a character, we can insert a character, we can delete a character. Okay, so we have to do it in minimum possible time, minimum possible steps. So let's see. So let's say I have Sunday over here and I want to convert it to Saturday. Cool. So what can we do here? Day at the end are same. So now we can actually convert this sun to Saturday. And what we can do? We can, so this is also same, right? So that means we are left with UN and ATUR. So we can insert what? So guys, here we are going to do it using 2D DP, the bottom up approach. Okay. Here I have actually, so we are trying to convert this string to this string. Okay. Let's see how we'll proceed. Here we are going to convert this string to this string. We have to consider the empty cases as well. When let's say this string is empty, so this is that case. And let's say this string is empty, so this is that case. Now, if we want, so this is what we have to convert in. So let's say if we want to convert this to this, what we'll have to do? What should be the output here? It shall be 0, right? I don't have to do any operation. Now, if I want to convert this empty string to S, in that case, I have to add one character. If I want to convert this empty string to S and A, for that I have to add 2 characters. Then 3 characters, 4 characters, 5 characters, 6 characters, 7 characters, and 8 characters. Right? So that's what I have to do. Now, what if we have to convert this string to just an empty string? In that case, we have to delete one character. Then we have to delete 2 characters, right? To convert Sunday to empty string, we have to delete 3 characters. To convert sun, we have to delete 3 characters. To convert SUND to empty string, we have to delete 4 characters, then 5 characters, and finally 6 characters. Okay, so this is the base case. This is the base case. Now, the point is that whenever, so at some, if we are standing at some position, right? Let's say we are standing at some position, then we are actually trying to do what? We are trying to see if I want to get the answer till that particular position. That means I want to get the answer for this and this, right? Answer for this and this part. Then what should I do? So please note that this is, let's say, the box and we are standing at here. Okay. Now this is the case. So this is the case when I'll be ignoring the current characters. Okay, when can I ignore the current characters? When the character at this place and this place are same, then we can ignore them and we can take whatever the value was previous, right? Whatever the value we had, so we can take this value. We can take this value, okay? We can ignore and we can, so let's say I have, so this and this are same, right? This and this are same and the corresponding block is this. So we can ignore this and whatever is the result from till here and here, we can consider that. Okay, we can consider that. So I hope it makes sense that why are we taking this position if there is a match? I minus 1, j minus 1 when there is a match. Okay, now this is the case. So just the position above the current cell, this is the place when we can insert an element. Okay, so this is for inserting an element. So when we have not found a match and we want to insert an element, so we will pick up the, so that means, let's say here we are, okay, and we want to insert an element. So we will be checking this particular location. Okay, we will be checking I minus 1, jth position. So here we have I minus 1 and j, and then for deletion, we will be checking I comma j minus 1. Okay, why? Because if let's say, so let's say we are at this block only and or let's say when there is not a match, let's say this block. Now this is deletion. Why? This signifies deletion, that when we are not considering this, so when we are just considering, so we are ignoring this character, and that means we are just checking what was the result for this and this string. Okay, So then at that point we can take this value. Okay, makes sense that we are ignoring this character, we are deleting this character, and we are checking that what was the maximum when we have ignored this character. Okay, because if we are ignoring, that means we don't have to check for this particular position. Whatever will be the value ignoring this character, we will take it from its left cell. Okay, now let's proceed with this. Let's see what we'll get. Let's try run the approach. Cool. So here S and S match, therefore we can ignore them and take whatever is present over here, that is 0. That means we have to make no changes and therefore the steps are 0. Now we go to this S and so we go to this S and U, they don't match. Whatever is minimum at this location or this location or this location, we will take it and we will add 1 to the cost, because now we are considering these elements as well. Okay, so 0 is minimum, we will take 0 and add 1 for the current operation. Now let's move on. So we have, now we will be checking for, so let me fill it. So S and U, so we are at S and N, they don't match. We will take the minimum of this and this. So 1 is minimum, this becomes 2. Now S and D, so S and D also don't match. The minimum is 2, this becomes 3. Now S and A don't match, minimum is 3, this becomes 4. S and Y don't match, minimum is 4 and this becomes 5. Now we are at this element and we will check again. So A and S doesn't match, minimum is 0, we will take 1. Then A and U don't match, so 0 is minimum, we will add 1 to it. A and N doesn't match, 2 we'll get. A and D, for A and D what we'll get? We will get 3, then here we will, this match, right? So we will take this cell. So add 1 to it. Sorry, we don't have to do anything, we will just take it. Okay, we don't have to add to it. Cool. Now A and Y are there, so 4 will come over here. Then, so likewise, shall I fill the complete table or it makes sense now? Is it clear that we have to take the minimum of the 3 cells, that is the above, the on the top left corner, so either, so if you are standing at this, so minimum of this or this or this. Okay, so let's code it, and finally we'll get our result at this location. Okay, because ultimately we are considering the complete string. The single cell actually tells that what is the value, the jumps till that particular position. Okay, the last cell will tell us the final result, so we will return the last cell. So we have the, let's take the string length in some variables. So let's say m is equal to a dot length and n is equal to a dot b dot length. We will take a 2D DP where it will be of a size of m cross n, right? And the first cell will have a value of 0, right? Because that will signify the empty strings. So to convert an empty string to empty string will cost us 0. Now what do we have to do? So basically we have to do the base cases thing, right? So I is equal to 1, you will start from 1, I less than, so rows is m, right? And okay, so string A is equal to, so we have string int I equal to 1, I is less than equal to, okay, so here the string length n, we will be going through all the, let's say all the columns, so that is n, okay, and I plus plus, so that will be dp of 0 I is equal to dp of 0 I minus 1 plus 1. What are we doing? We are actually initializing our base cases. Okay, we are just adding the values from the previous cell on the top rows and the top row and the top column. Int j is equal to, let's say 1 and j is less than equal to m, j plus plus. Now dp of, so dp of j 0 is equal to dp of j minus 1, 0 plus 1. Okay. Cool. Now let's move through all the cells. That is, it's equal to m and I plus plus. Then for int j equal to 1, then j less than equal to n j plus plus. Then int, let's say we are storing the distance like this. So q1 denotes the cost. C1, let's say cost is equal to dp of I minus 1 j. Okay, so this is the cost when we are inserting an element. Int C2 equal to dp of I j minus 1. This is the cost when we are deleting the elements, and this is the cost of replacing the element. Okay, I minus 1, j minus 1. By replacement, it means that we have changed the character to the character that we want. Now, if the current character, if it's same, right? I minus 1 is equal to b of j minus 1. So at this point, dp of ij is equal to dp of I minus 1, j minus 1, right? We don't have to add any cost because the characters are same. Else, what do we have to store? So we have to store dp of ij is equal to 1 plus minimum of q1 comma minimum of q2 comma q3. Okay, and finally we will return dp of mn. Oh, these are not q1 q2, these are c1 c2 c3. Cool. Okay, dp of int m is equal to a dot length, perfect, mn dp of m plus 1, right? Sorry, so it should be m plus 1. Okay, let's see now. Cool, we have got the solution. Cool, so let me actually make you go through the question that we discussed previously. I think few of you had doubt in that. See, we are doing DP and we were doing it in bottom up manner. Okay, notice that what DP, so you should know that what the state of the DP is, right? What these cells represent, and that actually tells what's the state of the DP. So this is the DP array and this is the given array. Now the state of the DP says that DP of I is equal to maximum profit by doing, we have got by doing the transaction till that particular point. Okay, if we are standing at here, then from 0 till this point, what is the profit that we have achieved? So that's what the DP of I tells. Is that clear? Now moving ahead, at position 0, we cannot sell this stock even if we buy. So therefore the profit is 0. Now if we go to the next position, so here we have to check for, we have two options. Either we can take this up, we can sell the stock on this particular day to get the profit. So that is one, sell the stock. Second is don't sell, right? So these are the only two options. Now, in case of sell the stock, we will start. So let's say we are at position this, and for selling the stock, we will start from this position all the way till this position. Okay, till I minus 1, this is I, till I minus 1 we will go. We will check if the value of jth element is smaller than this element, right? And also what we'll check? We'll check that whatever is the value at, let's say j is here, actually let's say j is here. Okay, now whatever is the value till this point, we will add to the profit we have achieved by selling stock 1 on by selling the cost of 1 on for cost of 3. That means dp of j plus a of I minus A of j. Make sense? Does that make sense that why is this condition for? Now this is why we have taken this thing. Okay, so this is the case when we are selling the stock. We will check for every I. We will check for every j, starting the j from 0 all the way till I minus 1. We will check for this condition. And there is some other case as well when we don't sell the stock. If we don't sell the stock, then we take whatever is present on its previous day. So let's say we want to see the cost of this. So if we are not selling on this day, then we are actually checking whatever is present on here will come over here. Okay, so whatever is maximum from whatever is maximum between this, that is when we are selling the stock and when we don't want to sell it stock. So whatever is maximum, we will take that value in here. Does that make sense? So that's essentially what we are doing. Okay, so that's what the DP solution is of order of n square. Okay, the pseudocode says that we'll take the DP array, then DP of 0 will be initialized to 0 because of the condition I told over here, that we can, if we even buy it, we cannot sell it, and we will go to all the elements starting from position 1 all the way till n minus 1. And if DP of I is equal, so here we are actually taking the previous DPI. That means we are actually not, this is the case when we are not considering selling the stock on day ith. So therefore we are taking the cost till I minus 1. We are taking the profit till I minus 1 day. I hope that makes sense. Now moving ahead, if we want to sell it, so we are going from j, j equal to I minus 1, right? And we will be taking whatever is maximum between DP of I minus 1 and this condition that I told you. Okay, so this is the condition when we are taking stock, when we are selling stock, and this is the condition when we are not selling. Okay, now this will do for all the elements, and that will take the time complexity of order of n square. Now I said that we can optimize it. So if we see this particular condition, right, in this condition we want to maximize this condition. I have actually changed it to this. Okay, I have changed it, and this I have got now. So to maximize this should be maximum, right? Now we are actually iterating in this j loop to find that for which value of j this is maximum. Okay, so instead of going through every element and checking for which value of j this thing is maximum, we can actually keep on storing it from the start. Okay, so that's what we are doing over here, that we are storing it from the start. We can actually maintain a max variable. Let's call it max var. Okay, and this can, so initially it will be initialized to DP of j, which will be nothing but 0. Initially the DP of j is 0, right? And we will be doing 0 minus a of j. Okay, minus a of j. So we will get DP of 0 minus a of, let's call it variable only. Okay, let's call it variable, equal to a of 0. Okay, this will be initialized. Now whenever we'll be moving in a loop, right? So let me write it. So for I DP array, DP of 0 initialized to 0, variable, let's call it maxi only. Okay, now it will be initialized to DP of 0 minus a of 0. Okay, so for I, which goes from 1 to n minus 1, DP of I is equal to DP of I minus 1 when we are not selling the stock. So we are taking the stock of the previous day. Now if we are selling the stock, so we will do DP of I equal to maximum of DP of I, comma, what we want, a of I plus maxi, and then we will update this maxi variable to max of maxi, comma, dp of I minus a of I. So essentially we have done it in just order of n.
So today is the third and the final day where we will be solving particularly DP problems. So we will start with the road cutting problem, and if there is any other request for a problem that you want us to solve, please do mention in the comments, or I will pick up any two randomly. Okay, great. Let us begin. The problem says that there is a road of length n, okay, on x-axis. So basically it's an horizontal road with its left end at x is equal to 0 and right end at x is equal to n. Okay, so basically n plus 1 points are there. Now there are m weak points out of those n plus 1 points, denoted by positive integer values all less than n. So basically there are m a1 to am weak points. Okay, we have to cut the road at all these weak points. Okay, so we have to make a cut at these points such that you can perform these cuts in any order. After a cut, road gets divided into two smaller subroads. Yeah, because it will be divided. Okay, cost of making a cut is the length of the subroad in which you are making a cut. Cost of making a cut is the length of the subroad in which you are making a cut. Okay, your aim is to minimize this cost. Okay, return an array denoting the sequence in which you will make cuts. If two different sequences of cuts give the same cost, return the lexicographically smallest. Okay. Okay. Basically, we have to give the sequence of points in which we will cut, right? And the points should be lexicographically smallest. And we have to basically we have to denote the sequence as well. Okay, that what will be the sequence in which we will cut. So basically, there is a road 1, 2, 5. So that means I will first make a cut at. So this is the I have to minimize the cost. So minimum cost will be here in those two. And out of these the minimum will be 2, 1, 5. So I have to return 2, 1, 5. Got it. Okay. So I mean, like, the problem to find the minimum seems to be a simple DP problem that, hey, I mean, like, DPIJ can represent the minimum cost to what we say to cut from index I to index j. That can be a possible thing, but let me say that what is the value of this n. Okay, the n can be up to 10 to the power 9. So basically we can't create a 10 to the power 9 DP table anyway. So we have to do something in terms of m. So if I have made a cut here, then let me think of the DP table. I mean, like, in any DP question, when it comes, I try to first find that what the state relation can be. And I haven't seen this question earlier. So let me think what the DP state can be. So for example, n is equal to 6 and a is equal to 1, 2, 5. Okay. Let me, I mean, like, when the values are not given, is m always less than n or less than n? Okay. By positive integer. So a1 will be greater than 0 and am will be less than n. So let me say I add 0 here and I add 6 here, because padding often helps in such DB problems. And then if I create a 2D DP, I'm not really sure if I should create a 2D DP, but if I create a 2D DP, then the answer should be, let us say that the indexes are 0, 1, 2, 3, 4. So my final answer should be in DP 0 to 4. Okay. Which will represent the minimum sum of costs to split roads, right? Okay, let us say that we save this. So Abhishek has asked to please explain the question. Sure, Abhishek, let me explain the question again. So basically, we are given a road of length n. On these roads, there are some points. There are m points like a1 to am, where we have to make cuts on the road. Okay, the cost for a cut is equal to the present length of that particular road. For example, suppose there is initially the road of length 6. Suppose you make the cut 2. Suppose you first make the cut at position 2 or position 1 or position 5. The cost that will be added will be 6, because that is the current length of the code. Now, suppose you had earlier made the cut at 2. Now, when you will make the cut at 1, the length will be 0 to 2, right? The length will be 0 to 2, which will be 3. So the cost added will be 3. So that is, I mean, like, then you have to find the minimum permutation of cuts such that the total cost is minimum. So suppose that is the minimum cost or minimum sum of cost to split roads from index I to index j. Okay, then that means I can make cuts from index what we say I plus 1 to j minus 1. Let us say that we say this. I mean, like I can make cuts from index I plus 1 to j minus 1. Let us say I can make cuts. Suppose that particular index is k. Okay, suppose that particular index is k. Then after this, the problem will reduce to dp of I to k, because I have already made a cut at k, plus dp of k to j, plus what is the current length of that, right? So, okay, I mean, like I can say the minimum sum of cost to split roads such that, then I think I should change that, such that the current road is of length I to j, is of length I to j. I mean, like j minus I plus 1, or what we say ai to aj. This seems to make some sense. Okay, then I will add what basically what is the current length of the code of the road. That will be aj minus ai plus 1, right? Aj minus ai plus 1, or will it be equal to aj minus ai? So this dp relation seems to be fine. I'm not really sure. Let me say that, okay, I will first, I have to, okay, first let me actually put this 0 and this n in the array p.
Make a smaller.
Add it. Okay, if I pad it, then I will have to say that b dot pushback. Let me actually make it a comment. B dot pushback a is the length of that. Then I will say reverse b, and I will b dot pushback 0. Then I will again reverse it so as to bring it to the correct position. Okay, cool. This seems to be fine. And now if I have padded it, now I have to create a dp table. I have to create dp table of this length, right? The new length is what we say the new b dot size. So I will create a dp table of n cross n, vector of n, dp of n plus 1, comma vector of n, dp of n plus 1. One thing is that it is not given to us that what is the value of this m going to be. So I hope an order of n square solution passes, order of n square solution in time as well as in space, but I don't really know. Okay, so this will be the dp matrix that I will create. What will be the base case for this? The very first case will be of length 3, right? All the length 3 cases I have to handle, because that is where I can make a cut. Okay, so I can say for int length equals to 3, and the maximum length will be n, right? 1, 2, 3, 4, right? So n will be, in this case, n will be 5, so it will be less than n. For int length equals to 3, length less than n, plus length. That will be the base case. Then I will have to put an I. Okay, then what will be I for int I equals to 0? I mean, like what the start position should be. I plus length should be less than n plus I. J is equal to I plus length, right? Or will it be I plus length minus 1? It will be I plus length minus 1, right? I plus length minus 1 should be less than n, because for index 0, length 3 ends at 2. Index 2, okay. So some people want the problem link. This is the problem link. Okay, now I know J. Then I have to have another loop. So it will be an order of n cube time complexity then. For int k equals to I plus 1, k less than j. I mean, like that is where I will split at plus k. Initially, I will set the value of dp ij to be int max. I set the value of dp ij to be int max. But I have to finally return what we say the sequence. But I'm firstly trying to see if I can, if the algorithm that I'm coding up has the correct answer, then I will be able to create the parent array to that. dpij will be equal to min of dpij, comma array j minus array I. That will be the length of the code. That will be the cost that will be added, plus dp of I to k plus dp of k to j. That is a sub-problem that should be there. And then finally, I will return dp of 0 to n minus 1. That should be correct, but that is not returning the original answer, right? So let me first see if this is returning the correct cost. Then we will try to, create the answer thing, right? Okay, so suppose let us take care of this test case only. For example, 6 and 1 to 5. Let us try to see what it returns there. Is it A? It is B. Bj minus Bi, and then there should go. Returning 0. Why? I say dpij is equal to int max and length is equal to 3. dpi will be 0, yes. So I plus length minus 1 should be less than n, so that is fine. Is bj minus bi min of dpij, which is initially int max, comma bj minus bi plus dpij plus dpkj. Okay, so I should be returning the correct answer, right? Let me try to see what dpij is coming for each index. Just if I suppose do that, what is this? I j and then I say dpij. I just first want to clarify if my algorithm is correct. I'm just trying to see it. So then it will give me, yeah. So from 0 to 2, the cost is coming to be 2, which is correct, because that is the only thing. I never do 0, 1, 2, 3, 4, right? I never do 0. So this array will change to, this array will change to 0, 1, 2, 5, 6, right? So the answer will be at 0 to 4, but I'm never computing 0 to 4 here as such. Okay. I'm computing 1 to 4, but I'm not computing 0 to 4. I plus length minus 1 should be less than equal to n, right? N is 4. N is 5 here, so this thing is coming out to be correct. My length should be less than or equal to n. My length starts from 3 and my length should be equal to n, right? Length is less than equal to n, then it will be computed, I think. So that is the thing that, yes. So the answer is 12 and the 12 was minimum. That thing we also knew, right? So at least we are getting the correct TP answer. I mean, like correct numerical value. The issue now comes, how will we, how will we create the lexicographically smallest permutation? Okay. One thing that is not probably given is that is the array of B1 to BM sorted? It is not given, right? It is not given that B1 to BM is sorted. So we have to sort that. Sort of B dot begin to B dot end. Okay. Great. So that thing we already know. And now we also know that we are able to come to the correct answer. Okay. So now the problem remains as to how we will create the lexicographically smallest permutation. Okay. So to that, suppose I'm also storing that what was the index that gave me the minimum value. Suppose what was the index that gave me the minimum value? Suppose that I also had this. Rather than doing this, I would have told that if command x is less than dpij, okay, that means dpij is first equal to this, and then I can also say that this will be min index. Then I can say that min index of I to j will be nothing but k. Okay. So once I have this, I know that dpij is going to return to the correct solution. So now I have to just probably process this matrix backward. That in which order will I make the cut? So I can say that vector of int answer initially will be empty. Okay, currently my endpoint is 0, int start 0 and end is equal to my end will be n minus 1, right? So till when should I find the sequence of cuts? I should keep cutting on. Okay, then I know that there are two problems in which that I have to find. Okay, the dpij and dpkj. Right. So first, the very first cut will be actually what we say answer dot pushback min int start comma end. But then there will be sub cuts, right? Then there will be multiple other cuts that will also be there. So how should I compute that? Because otherwise I will have to do that recursively, right? I first compute that, then I compute that. Or can I do a recursive function to do that? Probably if I do a recursive function, then it will automatically handle it, right? So let me say that suppose my void recurs to what we say start comma end, and this is the vector of end at answer. Okay, when do I know that this is done? I know this when if start minus end is less than 3, right? If end minus start is less than 3, less than 2. If end minus start plus 1, that is the length, is less than or equal to 2. That means I don't have any answer. That means I don't have to put anything. So in that case, I can return. Else, I will say answer dot pushback min end of ij, min end of start end, and then I will recurse for start to min end of this with this answer, and I will also need to pass my min end, right? And min end, okay. Similarly, then I can recurse from this plus 1 to, sorry, this only to end, and I will need to pass it answer and min end. Okay, and here I will have to have this min end. Okay. I will actually need to have the B of that particular base, not min end, but okay, let us say that I have this. Then I will say recurse of 0 to n minus 1 to answer to min end. But now I will have to change everything in the answer to reverse of that. So then I will have to change everything in the answer to reverse of to basically what was the value in this B. So I will have to say for auto and iterative index in answer, index will be equal to P of index, and I can return answer. This should probably work. Because I'm calculating it in the correct sequence, it should be correct probably. What am I missing? I don't have a semicolon here. Anything else? Probably no. So I'm returning 2, 1, 5, which is absolutely correct. I hope I'm not missing any other test case, but let us test it. Yes, and let us try to submit it. I hope the time complexity passes because we are not given the constraints. Yeah, so we are told that we are failing for the partially correct. Okay, so we have some wrong answer for larger test cases. Why? Okay, so probably the time limit is exceeding, right? Because there is no other reason why it should fail. The time limit can be exceeded because this is order of n cube. Can we bring this to order of n square? When I am computing this dpij, I need to know this thing is always going to be fixed. So I need to know the minimum value of dpik plus dpkj, right? So if somehow I know from I to k, which is the minimum k that stores that. But that I can't do. Currently, I'm at an order of n cube solution. And probably because I'm failing this, I have to get it to order of n square or anything else. No, probably the answer is there some modular arithmetic issue? Yes, there can be modular arithmetic issue, right? Because n can be up to 10 to the power 9. Then if n is up to 10 to the power 9, and all these numbers are 10 to the power 9, 10 to the power 9 minus 1, 10 to the power 9 minus 2, in that case, I will overflow, right? Yes. In that case, I will overflow. So then I think I will need to have this vector as a vector of long end, long end, and then probably this should work. Because there doesn't seem to be any other issue then. If I'm failing for the large test cases and I know that there is overflow possible, then probably that is the thing. And then this dpij will also have to be something larger than integer max, right? Or not. Eventually it should not, but it can be. So I have to let me make it. I have taken it as a long 10 to the power 17. Then let me first test for the normal cases if I'm doing some compilation issues. I think I will be doing this matrix. Yeah, because min index is k, but bj minus bi can be larger, right? So yeah, this seems to be fine. Okay, so this seems to be fine, and then let us try to submit it if that is the real issue, because that is what seems to me as to be the issue. And yes, let's try to do it. Correct, that was the issue, and we fixed it. Okay, great. So basically, how I identified that that was the issue, that was an interesting thing. That here I saw that the value of n can be up to 10 to the power 9. So when we were calculating the cost of the last three indexes, they can be 10 to the power 9, 10 to the power 9 minus 1, 10 to the power 9 minus 2, which will be equal to 3 into 10 to the power 9 minus 3, which is greater than integer max. So there was a chance of an overflow, and we fixed it up. Okay, great.